All right. Thanks, man. Get there. Okay. So, what we're going to do today is we're going to go ahead and start it with more basic course, a little bit slower, and kind of go through things of the basic fundamentals of acquiring these data and then also analyzing them in the afternoon session. We're going to try to make sure lunch is here on time with plates. So I think that happens. That'll happen around noon to 1, ideally, and then we'll again start with the afternoon session at that point. Okay, so any questions or comments or anything before we get started with this? And then has everyone actually acquired data with MindWare or at all? Or any couple? No, for you? Okay, awesome. First thing we're going to do is I'm going to do a overview on BioLab, sort of covering all the things that I believe are relevant to everybody here. If there are any other questions that you've had about BioLab that you're not sure about, please let me know. And of course, you can interject right in the middle of my presentation, ask any questions as soon as you have them. So anyways, I'll go ahead and get started here with going through BioLab, and then in the meantime, we do need a volunteer. So if someone is willing to do that, let us kind of hook up. We already got one. Okay, cool. Then I guess we'll hook you up there a couple different ways, and we can actually look at your Visio data live and everything. And then you can take the recording home with you. But awesome, thanks for doing that. Okay, so as far as connecting the mobile device to BioLab, is everyone pretty comfortable with that, or should I start the process? Everybody need to see that? No, we're good with that. Okay, awesome. So I'm already connected to the mobile device. And just want to, again, run through a couple of settings here before we actually hook up our system here. So one thing to notice here with BioLab is we can actually open a file that you can see up here. So if you've already collected a file, you can actually load that same one back into BioLab. And there are a couple different reasons why you might want to do that. One would be if we need to look for any sort of electromagnetic interference. We can actually load that file into BioLab. We can see these time domain data pass through the Fourier transform. We can look at the spectral components, and we can see if there's any sort of spikes of interference, essentially, expecting most of them to fall at around 60 hertz here in North America, which would likely be 50 hertz anywhere else in the world. So we can actually look at that, detect it, and then apply a filter here that we see in the middle if we do have interference such as that. If there are any events in your file, these are either keyboard strokes or a different sort of stimulus system that's sending these events in. We can view those events on top of all the different physiological waveforms. We can also edit them, move them around. So if you have something like a video acquisition that's in synchrony with the physiology, you can a lot of times align the video with where the event marker should have occurred. So let's say that somebody sneezed, or there was a door slam, or somebody fell asleep during your protocol. That actually happened to me when I did eye tracking. Little hard to get over, but something like that, you can kind of see when those things occur and move those event markers after the protocol has ended. So yeah, and you can also relabel them if one of them was mislabeled and it happened 1,000 times. You can come in, relabel that, and then save the file as to correct all of those. Last you can see here, if we actually open a file, the export events will highlight, and that'll actually let us get those events out of the MindWare file structure ecosystem if you needed to run that text file into a different system. Great, so the settings here are the configurations. So just like the analysis software that we'll see in a little bit, I highly recommend that everyone uses configuration files. What this will let us do is go through initially, set all of the configuration settings to how we want them, and then we can save that configuration. The sort of order of operations for the protocol moving forward would be we connect the mobile device, go up to settings, and then we're going to open the configuration for that study. So it's especially helpful if on the same data acquisition PC, there's multiple studies being run at the same time. And yeah, I guess it's just sort of another efficiency step there, so we don't have to go through and check all these different boxes within these steps. Okay, so other than that, just one more additional setup here. So there is an ASCII, this is a plain text, tab delimited text file, and it turns it into essentially a MindWare converter. So I think there were some questions earlier about getting different data into the MindWare system. And so essentially we'll just load the plain text file here, and then a wizard will appear that'll essentially walk you through. It'll look at your text file that you're trying to upload. It'll say where your columns, headers, rows, all that kind of stuff. You hit OK, and it'll then make the MindWare file for you. So you can do this in BioLab. You can also do that same setting in the analysis software. So yeah, either way, if that's a little bit more easy for you. Okay, this is our logo. So that's what that is. That's all I have for you. And actually, this right here is a little bit of a hidden button, which I'll let you all in. So if you actually just collected some physiology and you want to immediately view that file, certainly you could go file, open file, and go find it. A little bit more efficiently, you can actually, as soon as you get back to the screen, you can double click on this and it'll actually automatically open that file for you. So then you can go down view. This will turn to view at the bottom here. And yeah, check that out right away if you need to. See here. Yes.
When you get a chance, I was really curious if you could actually like do a demo of like making a change to an event marker that was like previously recorded, just as like a demo. Because I think typically like we note it down like externally for studies if like the wrong one was pressed or something like that,
right?
The notes, but it would be cool to like be able to like know how to actually go back and that.
Okay, sure, right, absolutely.
Just whenever you can fit it in, but definitely don't want to interrupt the flow.
No, totally fine. Let me just leave it out here. Yeah, and there's actually I'll cover. I think I might have briefly showed in the analysis software, but we can actually do it in a couple different ways. By that being one, and sort of manually copy and pasting events into a MindWare event file in the analysis. So also for both methods, but usually the BioLab method is a little bit less prone to user error because we actually get the visual guide of where the events occur and stuff like that. But we can definitely cover that. Awesome. So going over to some of these more important settings over here, we do have two major modes that I want to bring to everyone's attention. So one being continuous mode here that we see available. And in most cases, this is what you're going to want to have selected. What continuous mode is going to do as soon as we start the acquisition or it's started for us via some sort of trigger pulse from a different system, such as EEG or a stimulus presentation software. Regardless, the continuous mode is going to start recording when we hit acquire, and then it's going to just continue to acquire data until we hit stop on the next frame. So yeah, anyways, this is usually best because it allows the protocols to sort of float around in time if there's any sort of extra timing that is following some sort of acquisition, say conversation that wasn't quite completed. And yeah, anyways, the other one that is available is this Epoch or Epoch mode. What this is going to do, I'm actually going to jump forward and just show this real quickly because it's a little easier to understand the visual guide here. But if I follow, once I go to Epoch mode, I can also go over and hit the edit file. We have an example task in here. And we can edit these. We can come in and we can just right click, edit that, insert one above, remove it, those kinds of things. And what we can do is we can build our study within here with a predetermined amount of time that it'll last for each segment. And when we hit acquire, or again, it's triggered by a different system, then the first session, the baseline in this case, will run for 120 seconds exactly. And then it's going to automatically stop acquiring data. So only in a time-dependent study where you're like, I only want them to have this amount of time to complete this task or finish the discussion, what have you, would we want to use Epoch mode? Another consideration if we do decide to use Epoch mode is that as it stops, it's not going to automatically start the next task. That is something that you'll mainly do, and that's sometimes very nice because if you're moving from one condition to the next, you don't necessarily want that physiology in the middle that occurs. One consideration if doing so that is there is going to be time in between the stop of one segment and the beginning of the next. So when we want to ask something like, I want to see continuous read in a physiology for the entire protocol, we can't exactly do that because it's not proper to just kind of spline files together because there is time missing in the middle, and we could certainly have some sort of physiological change that we wouldn't be able to observe in there. And things for like a frequency-based metric such as RSA, it needs a continuous stream of data. It can't have any interruptions in there. It'll just be seen as noise injected into the file. So someone asked me about the ASA, so I just want to spend a little bit of time on that. But yeah, anyways, a lot of times Epoch can work for you, but just kind of be aware of it. And I think the last thing to just kind of note on it is, in so doing that, what it's going to, BioLab is going to do is going to save a separate file for each one of those epochs. So when you go do analysis, you're going to have to load a separate file for each one of these. So certainly that can take a little bit more time, and you're going to then create additional output files for each segment. But again, in some cases, it's still preferred over a continuous mode. Okay, we're going to come back to the Wi-Fi channels in a little bit. And once we get a participant hooked up here. So I'm going to go through some of these other tabs. So first thing here we have is keyboard tabs, events. I have some sort of basic events typed in here on an example of a very simple protocol if we wanted to use events in this way. Essentially what we can do is we can start the experiment manually by hitting acquire. And then as we move through the protocol, we can hit the function keys on the keyboard to actually say when these different events occur. There's also a blue sort of ribbon on the right side of the acquisition screen, so we can click there if we don't want to press the key on the keyboard. But anyways, this would be a way in which we can actually use these events to sort of delineate when these sort of conditions begin and end, for example. A lot of times you can also simplify this by having something like F1 baseline onset, and then F3 being task 1 onset / baseline offset, right? If it happens right away afterwards, we can create more events available to us by doing something like that. Mixed analysis may be a little bit less, a little bit more confusing, but certainly something you can do. But anyways, the idea is that we're having the experimenter kind of keystroke these different function keys as we move through the protocol. Obviously, in so doing that, you're going to have some drift on, exactly when those things occur, such as like the experimenter could be a couple seconds late on pressing that key. In most cases, this is perfectly fine for what we're looking for. I mean, if we had like a 5-minute baseline, normally what we're doing is we're going to average across all those different scores. And so if we have a couple more seconds extra, it's usually not a problem. In looking at the analysis software and our events and modes, we can also say something like, well, show me the first 5 minutes of baseline and exclude everything after that if it's a couple extra seconds. So a lot of flexibility there, so this could be utilized. And another thing of note here is that we have the F11 key that's at the bottom, which is a user-defined event. And so in a live acquisition, if we hit F11, a dialog box will come up, and we can literally type in anything we want that occurred. And there's an unlimited amount of events we can do at that point. So if we needed something like this, but then a lot more, F11 is available. The F11 dialog box has a dropdown as well as being able to type next to it. A drop down, let's say the last 25 entries that you had in there. So let's say that we wanted to pretty much always just use the drop down for any sort of additional events. You can just click on those instead of having to type it in and potentially make any sort of typos. Another way that you could be using events is, let's say that we had a stimulus presentation program, SuperLab, Uprime, PsychoPy, whatever it is that you're using, and it's actually sending these event markers to MindWare through some sort of TTL pulses or network pulses. And that's what's actually defining the different segments of the protocol, for example. Then we don't need to keystroke them in manually. That's going to be done for us as the participant, let's say, walks through a computer task. Every time we present some sort of stimuli and end that, we can have that program automatically send those triggers. So in that case, we don't necessarily need to have these up here. What we can do then is we can use these function keys for some sort of behavioral markers, even if it's just a sort of rudimentary, any sort of behavior aspects that we want to look at a little bit later, or potentially see if there's any sort of change in their physiology due to that sort of stimulus. So usually these things involve sort of external stimuli or something that the participant is doing that is not necessarily part of the protocol. It's not a sort of unplanned thing, but you do want to notate it in case, again, there's some sort of physiological change due to that sort of stimuli. So for example, let's say that we're acquiring data here and there's a very loud hallway out here, everyone gets out of class, and then let's say if someone also slams the door or something, that participant hearing that it's going to do something, at least at the very minimum to their attention. And so kind of putting that in there, that there was a loud sound, and within some degree of like within 5 seconds or something, and then we can always look back and then see if there was any sort of change within there. That is something that's nice to look at with the pre and post analysis mode that I showed you all earlier. We can go through again. We can kind of see where that event occurs. We can look at something like 30 seconds before the event, 30 seconds afterwards, and we can see if there's any sort of major statistical difference between the two. And if not, then we can kind of continue on and move forward through the analysis. If that makes sense. Okay, network events. So on the mobile device, which I will show, but it's probably a little bit small for everyone to see from that. Oh, there's a cell phone down here. Is that pink? Maybe that yours?
Oh, yeah. Yep, mine.
Here. This is why I can't reach you. Okay. So on the mobile device itself, there is an A and B button here in blue. And so actually during the protocol, what you can do is you can actually have a participant, if they're holding this, it's on their side, what have you, they can actually use this to give some sort of feedback. It's accurate to plus or minus 2 milliseconds, so it's something you can certainly do for some sort of reaction time studies. It's also very nice if, let's say you're doing a parent-child interaction, and you wanted the child to be able to answer a sort of question sort of with a binary answer without necessarily saying it out loud so that the parent hears what their answer is. You could essentially say that every time there's a question that you would like to say discreetly, we're going to press A button and then for yes, and then the B button is no. A button is stress, B button is relax, like whatever the kind of things that you want to learn about. And you can actually just go into the A and B button fields and then type in whatever you want at that time. If they can't remember, you can always, of course, put some sort of label maker on there, such as yes or no, or whatever it is that you can kind of imagine that you want in there. It also makes an audible beep as soon as they press it, so they kind of get that feedback that it worked correctly. Other people will use these for something like a Likert rating as well, how stressed they are. So you can actually say, from 0 to 5, from 1 to 5 clicks, how stressed do you feel? And they can kind of just press A that many times. Okay, last thing, just to cover real quick, actually 2 more things here. So the Bio2 event here, if there is any sort of other system that you're using in tandem with the mobile device you would like to have synchronized, let's say that this is occurring offline, it's just the mobile device, and let's say like the Tobii eye tracking glasses, for instance, there's a cable that goes between the eye tracking glasses and the mobile device, and then they essentially can trigger each other and synchronize. So if this is something you're doing, especially in the field, it's a nice way to, again, get these kinds of things paired together. And then lastly, the UDP commands. So with the mobile system we have here, which is pretty typical of a laptop, a router, and a mobile device, there is a couple different ways that we can be triggered, synchronized with a different system. One would be that there is a network communication protocol, which is UDP, and we can have these sent or received from BioLab, and then another system can either be sending or receiving those events from us as well. Another method, which is, and this is going to be, I think the standard deviation is plus or minus 13 milliseconds or something. There's a little bit of a drift just because network communication is not perfect. If we need something that's millisecond accurate, there is a USB to sort of parallel port connection. We can just plug in through the laptop. And then if we have, like, let's say PsychoPy, it has a parallel port, it's sending those events out. This device receives those, turns the USB, and then we can receive those markers. We can also send markers out. So let's say if we don't have someone's presentation program, it's just physiology, and let's say an EEG or eye tracking device, BioLab can send a pulse out to that other device and then synchronize both at the same time. Any questions on this stuff? All experts?
I'll just say for anyone who hasn't used it, the UDP is really useful when you're doing any kind of behavioral tasks that have different blocks within them, like a go no go task and stuff like that. So where it's really not going to be possible for the counter to be marking the onsets and offsets as people move through the jobs. So we've been using those It's reliable.
Okay, awesome, great, yeah, and there is a, I'm gonna say this probably 1,000 times, or less than 1,000 times, but there is a support article, which I will go to. So if we actually just type in UDP to our search bar here, forget the number of times. So KB0059, this is sending UDP commands from BioLab. BioLab from E prime, which can also be done the other way, but and this will essentially walk you through with pictures on how to set this up between two computers. And this is using E prime as an example, but this right here is the chart that you would really need to know to characterize like what those byte strings should look like as far as start, stop, the port that you need to open on your network, and then how to actually code the events source, where they're coming from, such as psychopy or a different system. Event value is just a count up number. And then, yeah, it'll go through on actual E prime to show you how that's put in there. So this framework as well can be used and easily applied into SuperLab, but just so everyone's aware. Okay, great. So next thing, audio video. So if anybody is collecting or wants to collect a synchronous feed of audio video with BioLab, this page will help you set that up. There are a couple different options we have. The MindWare video encoder no longer exists, but people are still using it from something like 10 to 15 years ago. So we're going to keep those settings in there for them. But as of right now, we can synchronize with either the Media Recorder or Mangold's Video Sync Pro. So those are essentially just independent audio video recording softwares that we can automatically synchronize. And a lot of different cameras can be used in them, but it's usually of a particular brand. So if anybody's interested, certainly let us know, and we can provide you an estimate or at least point you in the right direction if you already have a set up. Okay, last thing we're gonna do here, and then we can kind of go for participants and custom physiology, is just the trending screen. And so if anybody is interested in sort of biofeedback, this is a nice place to start. It is a sort of a light version of biofeedback. It's the sort of free implementation of it all, but it is a very simple sort of line graph that'll be changing and modulated depending on the person's physiology. So for instance, we can actually show them in a line graph fashion their heart rate going up and down. More commonly, it's respiration. We can actually show them respiration if they're doing some sort of paced breathing task. And we can actually have them try to control their breathing, or something as simple as also like controlling their heart rates, trying to slow that down, something like that as well. So certainly helpful if you're doing a lot of interoception studies and similar things like that. We can show this in little bits. I can turn on some, just a heart rate, for instance. Respiration rates are, again, most popular here. I can turn on as many of these as I want, so I could do one such as heart rate and respiration rates. Then when we go to hit acquire here, say a few times, going to ask me where I want to save the data. I think it's just still in Epoch mode. Okay, so then this screen is additional sort of screen is populated once we have the trending options connected. And then it's a little bit hard to see here, but this one in red here is the respiration rates. And then this one right here is going to be the ECG function here. So again, it's just a sort of simple line graph here, but it is something that someone could interpret, and you can actually see in a lot of cases, the correlation between the breathing out, heart rate increasing, and breathing out and respiration decreasing. I'm sorry, heart rate decreasing. So certainly something can be used. If there is something more complex that you're interested in, or maybe essentially you're piloting with this just to show the sort of efficacy of it, then we do have something called the BioLab data stream module. It's a paid upgrade to BioLab. What that'll let you do is utilize the UDP communication that we've been talking about. We can actually send the live physiology that's collected out of any sort of network port. So similar to what we're doing with E prime there, we're sending out port 1776. And then you can have another PC essentially plugged into the same network, into this router, that's receiving these these live data streams from BioLab, and then making some sort of interpretation based upon it. So if we, for instance, wanted to have their ECG output sort of streamed into a network port being received by a separate PC, something like E prime or SuperLab or some sort of custom script can then be doing something like creating a heart that is actually beating every time that we get an R peak that's detected within BioLab. We have done a really quite a few cool things like this, a few for NASA, and then also there was one of my favorites is that we actually set up that exact example of a heart that's beating. There was a projector that had essentially just the heart that was sent into two mirrors. And so it would refract off of one mirror into the other. The person looking into the second mirror could actually see the heart overlaid on top of their chest that was beating just a couple milliseconds after theirs was. So a couple cool studies that we've done with that, but just an idea of some of the applications you can do with that data streaming. But this being the basic version, so you can certainly test this out before you kind of jump into that extra step. Any questions on this trending screen thing? Biofeedback? Good? All right, awesome. I guess we'll leave that on. Would be interesting. Okay. So then setting up our main channels here, and then we'll go ahead and hook this one up here. So the Bionex slots here, these are essentially just the channels that we selected on the previous screen. I didn't actually show that, but when we're protecting the mobile, you can say that we want Bio1 turned on, or Z0 and GZDT, that's impedance, or GSC, which is our skin conductance channel. Once we do those, then they will populate up here. We can't change them at this stage. If we needed to, because we made a mistake, we're going to redetect the device, select the new channels that we want, and then we'll jump back into the configuration screen. The viewing scale here, so if I'm going to focus just on mobile for today here, if we have the mobile device, essentially scaling would be what is the system receiving in volts for MindWare, for instance, and then how is that going to be viewed or reported during the acquisition or especially during analysis. The mobile device automatically scales everything from volts to what you want to receive it in, so you really don't have to worry about it and just leave that on none. If you have our wired system, the Bionex, there are some scalings that will want to be applied to the Z0, GZT, and skin conductance. And that essentially is just so that we're receiving volts, and then you're seeing the impedance in ohms and the skin conductance in microsiemens, for instance. There's a support article, of course, again, if you just type in scaling, that'll help you with the Bionex. But again, for today, we're just going to focus on the mobile moving forward. Last thing on here is, or not the last thing on here, the most important thing on here maybe, is the right way to say it, is the gain setting. So we'll go through a sort of brief example on modifying this. I almost hate to bring it up because the reasons why you would change the gain are slim to none and going to be very, very rare. In some cases, if we're collecting data from a participant that has a higher BMI, again, something that would exceed 40 on average, then sometimes recording that ECG signal on a surface electrode can sometimes be attenuated by those additional lipid layers. And so by increasing the gain, essentially what that's doing is amplifying the circuit, and we can then see that signal a little bit more clearly. So even in participants that are of a high BMI, it's still not necessary in a lot of cases it changes, but I do want to draw everyone's attention to it because if there is an issue such as that where we're not getting a lot of clarity on our ECG signal, this is happening repetitively, we ensure we use fresh electrodes, we're abrading the sites with alcohol pads, we're doing all the proper things, but we're still seeing a sort of fuzzy, indistinct ECG signal. This can be a good time to try to modify the gain to see if we can increase that quality. anyways, with mobile device, I would recommend that you keep it at 1 and always keep it at 1, unless you're looking at a different non-human model for acquisitions. So if we're looking at something like a mice or something, then we need to amplify this by quite a bit. But if for humans, again, mostly the setting of 1 can be done. So even when we're looking at the opening the configuration files and our setting of gain as 1, if there was one cell that I would visually check on after that, it would be still to check on the gain and make sure it's on the setting of 1. So gain, okay, everybody got it? All right. Filter types. So in a lot of cases, especially with the mobile device, we don't really need any sort of filters unless we have something like the electromagnetic interference. I'm just going to call it EMI from this point forward. So if we had something like that, and again, if we're in North America, we're expecting that 60 hertz because of what I talked about yesterday, of sort of acoustical harmonics from alternating current. Then we would want to turn that filter on, which would then remove those noise live for us. We don't need to do this. So other than the gain, we can change all of this stuff post-acquisition. So if we made an error to the events that are being labeled, we even pressed the wrong key for the events, we wanted to turn a filter on that wasn't, we had the wrong channel name over here on the right. Anything like that, we can actually open the file afterwards, change those settings, and then file, save as. And then all of those things will be applied for us. The gain is the exception to that, so that's what I'm kind of driving it home. It will be grayed out. We can't change that post-acquisition. But anyways, yeah, so that is something we can do. So let's say that we did have something like that 60 hertz EMI that's present in our file, and we failed to turn the filter on live. That's fine. We can do that analysis later on. It's just that your data reductionist is probably not as happy with you if you just completely forget to do that all the time, but it certainly can be applied later because it's a software setting. There's also some other filters on here that can be used for all the different waveforms. You can see we have all the different sort of options that can be listed through MindWare. And so we could do something like having an ECG filter on, a Z0, DCG, and GSC filter. What that's going to do is hit normal, plausible physiological ranges for all these different measures. So if I were to turn the ECG, the low cutoff in hertz being 0.5, and then the high being 45. So that is where we really expect any sort of oscillation or change in the ECG signal. So by turning on that low and high cutoff, we're essentially attenuating and ignoring all the frequencies outside of it. I am a proponent of not just blindly filtering data without any reason. I would say, like, if we have something, especially after a few sessions, and we see that there's a common interference that's always going to be in this data acquisition lab site, if you will, then we might want to turn that on. But it's also the case that we can do this afterwards. So if we're having our sort of inexperienced experimenters and they're collecting this stuff and we don't want to stress them out with like, look for this, look for that, then do this, and it's this whole 3-page protocol they have to run through. We can have them say, open the configuration, make sure the gain is set to 1, and then maybe have somebody else look at that, at their convenience after acquisition occurs. But yes.
If we were to change the filters after the data acquisition, is that mainly just kind of like a filtering thing? Does it actually change the file, or is it just kind of like a find, sort, filter?
Yeah, it's a really good question. So in just a second, I'm going to go and cover the file types that you're going to be expecting, but just to answer your question right now, there are 2 main file types that are created for every data acquisition with the mobile. It's going to be your de-identified subject identifier, whatever that name is you're going to come up with, and then a .mwx. Another one's going to be a .mwi. So those are both sort of tandem files that are created every time we acquire the data. And the MWX is the raw data. So that's an uneditable file. It's always going to contain that raw information that we're recording. It doesn't have any sort of influence from filters and things like that we might be applying, other than the gain. And the MWI is an index file. So what that does is actually draws the information from the raw file. It's actually what the MWI is what will load into the analysis afterwards. And then any sort of filters you're applying would be done to that MWI file. So if we ever needed to, we can always just delete the MWI, load the MWX into this feature here, which is in both BioLab and the analysis of build the MWI. It'll ask you to load the MWX, and then you're back to normal. So I guess that sort of answers your question there, but yeah, as far as the filter is done, it's sort of on a layer on top of the raw data. So if we ever needed to, we could look at both. And when sending those files, you'll want to make sure that you always send both to somebody. If you sent the MWX, they could create their own. It wouldn't have those filters and stuff you used. If you send just the MWI, they're not going to be able to do anything with it. So just make sure you're always sending the companion files together. All right, two more things here. So the channel name, as I've gone over a couple times, this is called Giraffe. There's an actual giraffe on here. It was on giraffes in Serengeti. So I got really into it when they were used there. Learned a lot about them, and just sort of like a lot of questions that I couldn't came to my head. So sort of a giraffe expert. Just kidding. But this is why this is giraffe. So I'm not gonna let anybody take it. That's my giraffe mobile. So we can label that wherever we want. That's my point. So in the mobile device, we can go in, we can go to settings, and we can actually say this is parent mobile, and then we have a separate one which is child mobile. It's sometimes nice to have that consistency and have the same device for each participant. And if we go to the settings and we actually say this is parent-child, then every time we go to acquire data, then it'll pop up on that screen, sort of first section here of what that mobile device is. This can help with ordering effect errors that could occur if you're loading multiple mobile devices or multiple channels for multiple subjects, such as that if we start the parent mobile first, or let's just say we start the giraffe mobile first, and then we synchronize the second one, or that's the second one we turn on, then it will populate the channels 5 through 8 down there. But if you do it the other way, the second mobile, we'll call it zebra mobile, that'll show up first, and then the last 4 channels are going to be the giraffe mobile. After that, what we can do in addition to that is we can relabel these channels to something if whatever is our preference. And so normally these are pretty good to go across. The ECG, we could do EKG for German, then we could certainly change that. Z0, GZDT are usually good for those channels as well. The last one here, the EDA, the electrodermal activity. This has Conductance has a lot of names on it. GSR, GSD, EDA. And Synchronization itself, and there's more. So our actual analysis is called the EDA application. So in a lot of cases, that's what I like to have on there. The channel, when we're actually selecting the electrodermal activity, is GSC. It's galvanic skin conductance. So if you want it to be easier on the person doing the analysis, you may want to actually change this last one to GSD when they're mapping the channels later on, saying this is ECG, this is Z0, so on and so forth. It's kind of a one-to-one. They'll see GSC, they map GSC. So we can do that, or we can just, everyone understands that EDA is also GSC. So anything like that, for example, can be modified by you here. Last thing that we're going to look at here is waveform math. This is pretty rarely used. We really added this for sort of a few specific protocols that were sort of common enough to where we would actually feel like it was good enough for the group to add them to our software. What these do is we can add, subtract, integrate, or differentiate one signal from another in real time, and then we can kind of see that change, sort of convergence or divergence, summation, or sort of there's the raw difference between them by selecting one of these options. It doesn't change the way the files are saved in any way. So the implementation of this was, again, for very specific protocols in which if we're looking for something like biosynchrony between participants, we can actually see points at which their ECGs will become closer together, align, or start to spread apart, for instance. And again, this is something that is done via visual inspection by the experimenter, and then there is a adaptation to the protocol in real time. So it's pretty intense kind of thing with very specialized training on those people that can do it, but it certainly can be done, and this is an application which we use. So usually only done when we have multiple devices connected where we might be looking for that kind of thing. Okay, that is it for all the different settings I went through. Does anybody have any kind of questions about that stuff before we go? Yes.
On the waveform. So when you say it can be used for synchrony, but then there needs to be a visual analysis, is that setting like annotating something in the data file to suggest like, hey, let's say I'm measuring mom and child. Mom and child are very similar right now, but then someone else has to visually review it and be like, yes, that looks like synchrony, or how does?
It doesn't change. It does not necessarily setting or anything. It's just strictly a raw visual that's streaming across. And again, it's a little bit more difficult to see in a lot of cases, but with the trained experimenter, you can, with a lot of accuracy, actually see when like something like the art peaks are combining
Okay.
between two signals. If we look within the BioLab screen that we're going to see in a second with the acquisition, we have all these different rows that are populated with the different waveforms. But if we have ECG on channel 1 for mom, and then channel 5 is ECG for child, it's hard to kind of see them for there.
Yeah.
Whereas this will show them right on top of each other.
Okay, thank you.
Yes.
I have a follow-up question to that. What setting would allow you, I know that there was a drop down and then it had different like add and things like
Yeah, yeah.
what are how does that change the way that the data is visualized?
Yeah, so what it's going to do is it's actually going to show you like the raw difference between these things, not necessarily the waveform itself, and you can actually see if we subtract one from the other, it will show you the difference between them in real time. If that makes sense. Yeah. If we were doing differentiate, it's going to see how much apart they are from each other. Kind of keeping like these placeholders in real time so they can actually flip. And then you can subtract, which would be the absolute raw difference from those, from like essentially like a baseline that you've created, or from like, let's say 0 volts, for instance. So applications like that. It's a little hard to think about in real time. I don't have 2 mobile devices, unfortunately, here, but once again, if you needed to, you can go into the manual for this, and then it'll have a little bit more additional information with like visual guides and screenshots and stuff like that. So yeah. Okay.
Clarification.
Yes.
That it has to be the same signal type for 2 participants, let's say mom and child.
No, it doesn't have to be the same signal type.
Oh, it can
Yeah.
be across for the same participant.
Yes. Yeah. So you can do that as well. If you're looking for a sort of synchrony between, I mean, that's a little dicey there. I mean, you could look at something like impedance cardiography and then skin conductance to see if there's any sort of like agreement or sort of global stress reaction that's happening between multiple organs. It's a little bit hard to interpret though, as far as what you're doing with that. So normally it's just done for multiple participants in the same waveform, but you totally can. Yeah, absolutely. One nice thing that can be done with there, if we want to do something like we're going to do a little bit later, where we're having alternate sites for the same measure. So if we're doing something with the hands, which is traditional, we can actually take it from the wrist, the shoulder, and the bottom of the feet, all these different places. So if we wanted to, we could hook up the same participant with 2 skin conductance things, and we can actually see if there's any sort of agreement between the sites. If there's a reason as to why we want to go away from, let's say we're doing everybody on left hand, we want to see if there's any sort of difference between the left and right hand in our piloting testing. This is a nice application for it.
I have another question in terms of like if we use 2 mobile devices. I'm assuming just the bottom rows would just be turned on. Is that how we would check?
Oh, what do you mean?
So if we're using 2 mobile devices, how would we be able to like if we wanted to change the filters and things like that? Is it also on the screen?
Yeah. So if you had 2 mobile devices, so this is channels 1 through 4. You can see on the left-hand column, and if you had connected another mobile on the previous screen, 5 through 8 are gonna be highlighted.
Oh, gotcha.
And then so essentially from here you can click this, and you'll have all 8 waveforms in that case available to integrate and whatnot.
Okay.
So okay. So I think without further ado here, if you're ready, we can start to give us some of these different measures. It's normally helpful if someone else does it instead of me, because I'm pretty good at it. Is anybody want to hook them up for this, or any volunteers on that end? There's a prize for volunteering for stuff, just so everyone knows.
Yeah, but I've done it before. I want to.
Does anybody not have one? Want to try it out? Okay, you guys are kind of together there, but
Yeah.
okay, awesome. So what I'm going to do is I'm going to, I think it'd be safe here to sort of go the normal way of the electrode collections, and then after we're kind of done with that and everything's settled, if we have some extra time before lunch, or we can even like after lunch, we can put on these different sites and look at the data quality there. But okay, so what I'm going to do is I'm going to open a couple different things for you. This folder and files within it, I'm going to go ahead and share with everybody here afterwards so that you have the actual files we're looking at. That'll correlate with the videos. You can look afterwards. But what I have here to begin with is electrode placement. I have our sort of normal placement here, and then I have a couple different publications, pictures, and guides on the alternate locations that are available. So I'm going to go ahead and open this one up, and then this will give us our guide on where these this array of electrodes should fall. And yeah, that's a good spot there. So if you guys want to jump up here, we can start to run through actually picking them up. Okay, awesome. So yeah, we'll have you kind of both stand here, and then we'll kind of manipulate you maybe a little bit as we go along. Should we go have this?
Do you want me to remove that questions?
Nope, you can leave that. Okay, how's the reference? And a couple notes maybe before we get started with this, or we can cover a little bit more if there's a ton of questions about it. As far as the clothing, there was a good question there. As far as recruiting participants, having them come in, two-piece clothing, so no dresses, rompers, things like that. If we have to put a sensor right here, you have to make a tough decision. How are you gonna get there? So yeah, definitely make sure that we have two-piece clothing if available. And as far as things like belts, any sort of metallic jewelry on them is usually not an issue in any way. The only thing that could be a problem if you had a very thick gauge, like necklace around your sort of neck and everything that's going down your chest, that could actually conduct some of the electricity from the impedance signal. It's not going to hurt them in any way, but it would certainly degrade the signal a little bit. So other than that, you're pretty set on this. For one of the measures that we're going to do, skin conductance, prior to actually having them hooked up, what we're going to do is want them to have them wash their hands to make sure we remove any sort of dirt, oils, lotions, things like that that might impede the signal. Before they come in, if you can have them just explicitly state, like, please don't use any alcohol and sanitizers at least 30 minutes before you come into acquisition so they don't dry out their pores. And yeah, I think that's probably it for that. When you're sending out that reminder, before, I said this yesterday, hydration is extremely important. So in there, I would certainly bold mark that prior to coming into the session 24 hours before, please drink plenty of water. You can actually label how much water they need to drink, but no one's going to do it. It's actually kind of crazy to look up. But certainly that's helpful to drink plenty of water. Don't use alcohol in excess, things like that. Sure. Any questions on any sort of acquisition reminders, participant stuff? Okay, awesome. So this guy here, we can certainly have our electrode lead array ready for us, so we're not sort of fumbling around while participants are in here. I'm going to do that just to kind of go through the protocol here a little bit closer, but as far as data quality here, I'm going to go ahead, and I think everyone's pretty experienced with this stuff, but I'm going to pass two of these around. I'm going to show you a method here to kind of see if electrodes, if you could pass that around. There's a center which has a gel, it's sort of a darker portion. You can actually take your thumb and see if you can move some of that gel around within that little pouch there. If you can, you see that gel dispersing, and the electrodes are probably fine and fresh, you can use them. If you can't and it seems really dried out, then you'll certainly want to open up a separate bag of the sensors. And just kind of harping on this a little bit is extremely important. I would say by and large, the most common reason why fuzzy or bad data are collected is because the sensors are dried out. It's almost always that. If we're doing a good job and experienced with actually electrode placement, those kinds of things. So putting a lot of attention into that will certainly help you later on. When the electrodes are actually sent, if you buy them from us, there is an expiration date that is on the bags. So when it's unopened, the date is perfectly fine. Try to keep it in a cool dark location. And once the bag is opened, what I normally do is write the date that is 60 days from that date. And then at that point, they become just training sensors or something at that level. 60 days has some error bars on that because of different climates and humidities and stuff like that, but it's usually pretty safe. So once we open it, zip, and then put it into some sort of air container, it's like a cheap Rubbermaid or something that you can get. But yeah, anyways, other than that, if we did run out of sort of good quality sensor that don't have the gel and we need to apply more, as talked about yesterday here, we do have this sort of Signa gel, and this can be applied into each of the individual points there, back of the sensor. It's not the easiest thing to do in the world, especially when you're stressed and you have a family and things like that. But if you needed to and you were sort of preparing ahead of time, you can put some of this gel in there, and essentially just making sure that you don't put too much to where when we put it on them, it sort of squirts outside. But anyways, let's try to prevent that if at all possible. But electrodes are also not super cheap, so there's something said about that as well. So cool. We have two sets of those out. We're going to be using 7 of the ECG sensors for today. 3 of them are going to be on the ECG signal that's identified here by the brown leads, the negative on the right clavicle, positive on the lowest left rib, and then we have our ground sensor there, which is again creating that Eindhoven's triangle that I'm pretty jealous about still. That Nobel Prize they got for a triangle, pretty cool. And then the impedance is going to use the same ECG sensors, and it's going to be, we're going to be essentially putting one on the regular notch here and one on that cyclosternal notch. And again, as I said yesterday, there's a lot of speaking in our task, which usually is. This location is not ideal because if you put your finger on top or home, you can see that it vibrates constantly. That's going to induce noise into the system. And so what we can do is we can just essentially offset that usually to the left clavicle and right on that bone. Bony structures are actually ideal when we're putting the sensors on because they're less susceptible to move as the participant moves around. Maybe their clavicle's broken, but they're probably not in a protocol. So anyways, that's actually a nice site for that. If someone's especially bony, we can just tape the micropore tape over the sensor to make sure it's on there. Yeah, but anyways, when we're actually taking the measurement with the measuring tape after that, we're not going to take the straight line distance between the two. We're just going to look at where the cusp of that interior electrode site is to the top of the lower one. That's sort of shorter distance between the two. If there's any sort of curvature in the chest, we're going to just bring the measuring tape out and then estimate. Usually within a centimeter is all we really need. So it's usually something you could get without a sort of extreme error. So in addition to the ECG sensors, there's a type of different sensor, which is the Conductance ones that are usually going to be done on the palmar sites on the hands. So sort of these large sites here that if we put our finger to our pinky, they're the ones that don't really move so much. We don't have those folds in. We're putting them there for that reason, so that we don't sort of reduce the amount of motion effect. A better site that will actually have the most of those eccrine sweat glands we were talking about yesterday are going to be on the ends of these fingers here. But of course, especially if you're studying children, they're going to move around a lot. You're going to see a lot of motion effect from that. If we are designing a study, let's say with adults, or most importantly, adults that are going to listen to you, then, the finger site can be helpful if they're, also getting blood pressure, something like that, everything's static. This can also be a nice way to get data from essentially different races and then age groups that might have a higher sort of dermis layer there. So you're going to see naturally older people, you're going to have a lower skin conductance levels by putting on a sort of thinner layer of skin, such as the fingers or the back or something like that, or the wrist that we talked about. You can actually get reportable valid ranges for that measure. The question.
Yeah, so other than the hand, so you mentioned the estimated the feet, but also the shoulder.
There's a lot of different sites I'm going to show you. Once we have time for that sort of alternate sites thing, there's a bunch of different sites that we can do this from. Of course, the considerations are as we move away from the hands, bottom of the feet, we do have those 2 twice the sweat glands. The second being the Cochrane, which are just thermoregulation, trying to cool us down. That's probably not something we're exactly interested in. So when we pick these other sites, we do need to sort of think about that a little deeply and maybe control for things such as like the temperature in the room, so they're not having any sort of that sweating too cold themselves down, essentially. So the sites I just talked about, such as the wrist and the back of the shoulder, are sites in which we don't really see a lot of those Cochrane glands. So it's usually a safe bet on that. But if it's really hot outside and people are sweating, then it's something you want to take into consideration for that. Cool. All right, so anyways, what we can do is we start to get these sensors laid out here. And what I like to do is I actually like to take these out and have them ready. If you have a rolling cart, little 3M hooks, it's nice to actually take these out about maybe 30 minutes to an hour is fine before the participants or family comes in for a session. And then I even will a lot of times cut these with the hard plastic still left on them. Snap the cable bead on top of them and have that just sitting there ready to go. So again, you can have a chair if you're in a static location, and then those sort of 3M hooks all sitting there. The leads are setting over it, so we can just very quickly apply the sensors without having to sort of fumble around, if you will. Okay, so And one more note here before we hook everything up is pay attention to make sure we're using the right sensors. This is extremely helpful for those that are collecting data here. They are different. There's circles and rectangles. There's certainly a label on here. I mean, it's almost difficult to do anything if you put a marker on that says, skin conductance, and people are going to see it every day. They're going to be blind to it. So in some ways, let's ensure that we're using the correct sensors. With the ECG ones, as far as with MindWare ones, there's a 7% silver chloride electrolyte, so the AgCl. With the skin conductance ones, it's about 0.5. So the idea with those is that is the average conductance of sweat. So we're trying to not amplify or degrade the signal. We're essentially trying to continue that conductance on from the sweat glands. So if we were to do the wrong ones, we're going to amplify skin conductance by, like, let's say something like 14. It's not an exact number that we can sort of use a constant to apply from later. It's just unfortunately not usable if you do that kind of thing. So just kind of paying attention to that. Okay. So I'm going to go ahead and put these in here. As a visual guide, all the leads are color labeled here, which way you can then use with the chart to see where they'll actually plug in to the mobile device or on the BioNets. But again, the skin conductance being the green ones will plug into the rectangular skin conductance sensors. If you have a lead that's broken, what we normally do in most shipments, especially with mobile devices, you'll get 2 extra, which are these orange leads. There are orange ports on the bottom of the mobile. So in theory, you can use these for collecting a different measure at the same time. So what we're going to do is brown is going to be for our ECG array. And so we do have the Bio2 channel available. So if we wanted to, let's say, get another deflection of the ECG, we can do that as well. We can also use things such as EMG at the same time. So if we wanted to get an idea of a large muscle group, such as, like a bicep or something like that, we can actually put these sensors in a lot of cases, just the ECG ones on the bicep, and get a sort of that electrical reaction from muscle contraction on there. If we're looking for a very small muscle group, such as like a face or something like that, we use a different type of lead, sort of radio translucent lead, and then applying those sensors to a more sensitive location. So one of the more common applications for that is if anybody's doing any sort of startle protocols. Certainly we can look at different sites such as the Bicularis, corrugator for negative affect, the Zygomaticus, Bicularis maybe being the most popular for that. However, if there's something where people need to sort of act natural, if they're doing any sort of interaction, having cables on their face is a little bit difficult, both for the person looking at them and then just, telling them to act natural for behavior is a little difficult. So another thing we can actually look at too is the post-reticular reflex, which is behind the ear. And then it's actually activated a little bit quicker actually than Bicularis during sort of startle protocols, not just acoustical. So that's something that you could look at in addition to the rest of your waveforms here.
If you want to do an EMG, the ground, you want to use the ground?
You're going to use the same ground here.
One ground
Yeah.
for everything.
Yep. This is a direct current device, so we don't need like a ton of ground all over the body. Yeah. Okay, cool. So my color thing. So we can use this for that. If we're not doing that, we're just doing the normal collection of ECG, impedance, and skin conductance. Then these can just be stored as backups in case one of these other ones break down. You can certainly, recolor them, nail polish them, whatever you need to do to the different color. Something that's an all super cheap as well. They're like $32. So, but more in like sort of emergency mode if one of them broke. They're all mechanically the same. They're just different colors to assist you. Okay, so I'm going to continue plugging these all in. The green one's going on the rectangular skin conductance, as we can see here. And then the rest of it is going to be plugged into the circular ECG, ICG electrodes. Okay, sweet. I am missing a couple, so we might use those orange. First. Okay, so I have all the leads connected to our ECG. We're gonna have 7, so there's 5 on here, 2 on the other. And so now what we can do is reconnect to go across and start to put through the electrodes. So spin here. Okay, so as I said before, sort of the minimum amount of time that we want to have these skin sensors on them is going to be about 5 minutes. And so that's a nice thing to apply first. So we can actually put these on their hand. If that's going to be in the way, then we can take the lead cable off and just put the actual sensor on their hand while we're working on the rest of them. But we definitely want to do that before the actual baseline. So if you don't have a sort of waiting period before your baseline, let's just go ahead and apply this first. With skin conductance, unfortunately, during the COVID pandemic, the two manufacturers that made the paste for skin conductance decided to stop making it. And so globally, they're kind of impossible to get pre-wetted with the gel in there. We are working on it. We have been working on it for a couple of years now, but it is difficult, as you might imagine. So for now, what you're going to get, these are actually some of the last pre-gelled ones I have here, but they are a little dried out at this point. So what you're going to do if you purchase them is going to be just the actual sticky component of the electrode. And then we're going to take the electrode paste, which we have manufactured ourselves, along with Florida Institute's Research Center. And, actually just going to apply the paste manually. There's a guide on, if you actually go to our support site, the electrode paste is a keyword you can use, or paste. It'll go through with visual guides on exactly how much we want to use for this. And what your job would be here is to actually go in with a syringe, and we're going to extract that gel out of there. Again, this is something that I would certainly do before the participant comes in, as far as getting the gel into the applicator. But we're going to go ahead and do that and just ensure that we're getting enough gel in there. It is 0.28 milliliters on here that we want to apply to each sensor, which is in with the guide. And again, we're going to just pretend you just wash your hands. Hopefully you did that at least one thing. Yeah. We're gonna go ahead and apply it. So what we would normally want to do is we're gonna ask for your non-dominant hand. So which one do you write with?
This is my non-dominant.
Okay. I don't know how to answer that. Okay, so then we're gonna ask for the non-dominant hand, and then we're gonna place the sensor there. There are some bilateral differences between the left and right hands as far as skin conductance goes. That's not always constant between people, but if you want to standardize that, you can certainly pick something like a left hand, which is pretty typical. And yeah, you can kind of go from there. But the idea here on why we're actually wanting to put on their non-dominant hand is if they were to grab something somewhat unconsciously, or they're going to sneeze or something, they're probably going to use their dominant hand to do that. And we don't want to have that happen, so the motion artifacts in the data. But other than that, we can sort of standardize pick one site. So what I'm going to do here is just place them right on those large sites there that we talked about before. And so, yeah, if you put too much here, we actually just happen to kind of squirts out the side. So we definitely want to make sure that we wipe that down and put a little bit less on if that keeps happening for us. And if you can turn your hand a little bit towards the audience here. So when I'm actually pushing this down, I'm taking these 3 fingers and I'm rotating them. I'm moving that lead cable around and actually pushing down at the same time. And this will ensure that that sticky is on his hand as much as possible, not just kind of pressing on a single location. And you can put it down straight again. And they still have a little bit of gel in there, so a little bit too much of it.
So it's 2 different kind of gels. It's not the same.
Exactly right. If you remember the Sigma gel, also the gel that we have in our MindWare electrodes, it's a 7% silver chloride, and then the other ones are going to be a 0.5%. So yeah, different conductance levels. Guess this is just my pants with I have a ton of pants with the electrolyte. Hold on a second. Okay, cool, awesome. And then what we're going to want to do is we're going to want to put these lead cables, show everyone again, back sort of towards the wrist. The idea here is that we're going to create a little bit of a service loop or tension loop here. So something like a little bit of a bubble so they can actually move their wrist around without tugging at leads. And then we're going to tape across so that when they're doing stuff, if they were to tug these leads on something, it's going to tug on the side with the paper tape, leaving the actual electrode site alone, so it's not getting the motion artifact. So I'll go ahead and do that. And then I will tape up this hand kind of extra. There were a couple of requests from before about the sticking of the sensors falling off the hands, which does occur just because of how much movement there's in the hands. And yeah, pretty much channel on it. There we go. Put back just a minute. Sorry. And if you want to show everybody that, so essentially we have the one that is necessary here. So if I'm tugging on that, it's actually keep it on this side, leaving this side alone. And then I've taken two additional strips that go over the actual electrodes there, wrapping around their hands. The micropore tape does stick to the skin very well, but it sticks even better to itself. So if we want to wrap it around and actually make a connection with the other side, sort of similar to a Band-Aid, then that holds on a little bit better. Awesome. So then we're kind of done with that. So we have at least our 5-minute clock here, which is probably going to take us that amount of time to put these sensors on. And so if you want to come up and actually come up for the rest of these, they're a little bit simpler. And so what I like to start with is the EKG. So again, we're going to have them expose the right clavicle. You can just have them move their shirt collar over, moving out of sight. The best recommendation for this, and again, these are the non-conducting sites, is we use an alcohol pad to first clean the site. It seems like you probably took a shower as well, so that's great. So maybe not completely necessary, but you're going to do your right clavicle. And so then what we're going to do is we're just going to clean that site and then let that dry a little bit. You can use a gauze pad to get the alcohol off if you need to go right away. You can also let it air dry. Don't blow on your participants. They don't typically like that. So just gonna wait a second. And then we can go ahead and apply the first ECG sensor. As far as laterally what on the clavicle, it's not really that important, just that we're on that site. And again, same procedure once we get it on there, kind of using 3 fingers, rotating that lead cable around to make sure that we're getting good adherence to stick in every site. So perfect. Next thing we can do that is we can use the paper tape to do the same thing as on his wrist and create this sort of little service loop here. I have no idea where it is. Here it is. And then do the same procedure. So especially the kids are moving around, having that site on these different things as they move around and they tug on the lead, it doesn't actually tug on the electrode site, which is nice. Of course, we have to tape up the kids a little bit more, so there's a sort of tough decision you have to make between the two, but that would be a nice example of that. And then we do the positive ECG, so it's going to be on the lower left rib. Again, what I'd like to do in a lot of cases is have the participant tell me where that is to begin with. So I'm not having to poke around necessarily if it's not obvious. The location is going to be right on the shirt seam or right where they put their hand down.
The last one?
On the lower left rib.
The last one?
Yeah. Laterally on the where that valve should come forward. Yeah, perfect. Good. Yeah, one of the very last rib is going to come forward a little bit, but just the last one on the shirt seam is right here. You don't have to tape every single one. Just that's good for that example. We're gonna hopefully trust that when we tell him to sit still, he will. Or you don't get your prize. So next thing we can do is one at the front. Wait, you have white? Oh, the ground. Sorry, I forgot the ground. Completely. Yeah, go ahead. So with this one, it's going to be opposite to create that triangle there. As far as where it would go and the height, it's really not important that it's completely on the right bone structure on the side there. So anything in this area would work, but you can usually just follow the process she did and place on that site. So if we were just plugging ECG and scan conductance, we're done. But we're going to apply 4 more sensors for impedance. So the top white one is the next one I would start with. Again, jugular not being perfect, offsetting to the participant's left is nice if they're having a speaking test. If we offset to the right, and especially in Cato, we're going to run out of real estate between the ECG and the impedance, so that's why I normally offset the other one to the left.
Is there like a threshold, that they start considering it,
No,
or just like
No.
as far away as
Yeah.
possible?
yeah, they're completely different frequencies set on these. So it's not that the impedance frequency would go into the ECG sensor or anything like that, yeah. Okay, so other front electrode site is going to be the Zygote process. So if we're going from the sternum, essentially it's the 2 sides of it. So up for the jugular, offside of the bone, or it's that first little pocket there after the sternum stops. Again, if we have some sort of issue with the participant's physiology, if they're pregnant, a little bit over higher BMI, or if we have something like a bra that has that bottom, like let's say a wire bra or something right in that area, we can lower that just enough to go under that location. That's fine. And what we're going to do is we're going to get the interior measurement with that measuring tape there. That'll tell us that difference. So it's okay if we deviate from that just a little bit.
Do you want me to put it inside the shirt or just?
Yeah, sure. It's nice if you're moving around here, it doesn't quite grab on stuff, but that's normally what we would like to do with participants, so that when they are moving around, they're not grabbing the leads that are on the outside of their clothing. And especially if we're gonna have like a little pouch for kids, or they're gonna be putting it on their side of their belt or their pocket, it's nice that the lead cables kind of just go right into that. Okay, and then the back ones we're gonna do. So what we're gonna do is we're going to oh, everything the measurement as well. So if you actually want to focus a little bit more towards the audience. Oh, 180.
Okay, quick question.
Yes.
When you're measuring that lead distance, are you measuring it as if when you have it offset to the left, are you measuring from the jugular notch down, or are you measuring from the base over the side to be just a slightly longer?
Yeah, it's not straight line distance, it's just straight down. So what we're gonna do is if this is offset over here to the left clavicle, let's just imagine it's there though. We're going to have the base down to this one.
Okay.
So you're just gonna take it out and measure with a centimeter.
They need to be aligned.
No. So imagine this one's over here. You just come down to where this one was last.
You project.
Yeah.
So you're doing the
You're right.
It's the vertical distance.
Yeah.
vertical distance, not the back.
Yeah. Okay.
And then again, as far as the shirt, you can have them point to where those are on top of their shirt. We don't have to measure under it. And then we can quickly reference those points, and we're going to get the bottom of the top one to the top of the bottom one, that's sort of shorter distance interior.
It's kind of like eyeballing.
So you do it from the front here.
I measure from
the front. Yeah, the front two are our reference points. That's why we're going to take the measurement there. The back ones are going to be the constant current. That's why it's constant current source. And then the S and S being the sensing sensors. So the back two are actually putting that electrical signal that goes through the chest. It's actually,
No, you're not doing the back.
yeah, it's just measuring out front.
Yeah, it's just like this. Here, but if you go straight.
Yeah, we're gonna do it in centimeters, so I'm just flipping around a little bit. So 2 to here. So 2 to 9. So we got about like 17 centimeters. You started at 2 at the top there. Yeah. So about 17 centimeters, and we'll just notate that later on. And that's it for that. And so now we can actually, I'll take that from you, and then you can actually start to apply the back sensors.
Yeah, for the back, it says, that's inches, right?
Yeah.
1.5. So do I measure it from the front or?
This is more of an eyeball. It's not that specific. The most important thing to know about with this is that the back ones are above and below the front ones. So it's essentially outside of the range of the interior ones. That's the most important aspect of it. So if you actually look, there's a dotted line of where that back one would be placed, and same on the back. has a dotted line of where those other ones should be placed. So 1.5 above or below, it's just slightly just more than the diameter of the sensor. It's usually as far as the back of the spine is on the fourth vertebrae there. That's sort of when it sticks out in a lot of people. Then on one in the back, what you can do is as far as the one of the xiphoid process, you can have them point. You don't have to measure, but you can if you want.
I don't know.
What?
I know the.
Oh, to do the other one, so 17 centimeters, then put it up. Yeah, you could do that.
It's right now. It could be a little bit.
So what you can have him do if he turns sideways here, so you can have him point to where that one is outside their clothes, and they can use their finger to guide where you would want to put that one on their lower back. Awesome. So good job, thank you. And so now what we can do is we can plug these different leads into the mobile device here. Again, everything is color coded, and they have these sort of bipolar plus and minus on them. Of note here, the skin conductance, you can't see it here. It does have a plus and minus, but these are just bipolar electrodes. One is just referencing the other, so it doesn't matter which ones you plug in. We did a plus and minus because we thought it'd be confusing if we didn't. But those actually don't matter so much, so we can just plug those in as needed into either of the plus or minus green GSC ports, such as that. And then from here, I'm actually going to have you fold this. Oh. Yeah. And so if you can step back a little bit, actually. So one thing that is nice is the rest of these, the positive and negative does matter. If you mess it up, we can fix it later in the software, but just try not to, of course. And so one thing that can be helpful to identify them is just using the sort of anatomy of the body where we place the electrodes to how long the leads would be coming out of his shirt. So for example, there's 2 brown leads, and sometimes it's a little ambiguous after their clothing, like which one is going right or left. But the one on the right clavicle should be much shorter coming out of the bottom of his clothes. It's higher up the body. So then we can identify that, and then we can plug that into the negative CG there, and then the lower brown one that we have can be plugged into the positive. Awesome. The black ground on your right side, there's just one black ground port. And then same deal with the impedance as well, but now with the polarity is a little bit reversed. So the positive white one would be the shorter one coming out of your clothes. And then the longer one would be the negative. And then the red ones. So these are a little bit harder to guess sometimes. And so before you can turn around again. And so this is a little bit easier in this case because they put down his clothes, but this one right here being the negative, and I'll send this. In the torso of lines, I think. There you go. Okay, awesome. And now it's from you. Just usually like this. Cool, awesome. So there we go. He's all set up and ready to go. So if you could just stand for a second there, we can look at your waveforms, make sure we did it correctly. And then after that, you can sit down and we can start to collect some more data. Actually, if you want to stand a little bit off to the side, you can see that. Okay, so I would imagine we have all the sensors out, ready to go. A participant comes in some forms, gets the sensors on them first, hook them up with this different array. We've loaded our configuration file, setting up configuration, verify that the gain setting is to 1. And then next thing we can do is the preview, the blue buttons on the right side of the screen. I would like to start with the ECG to begin with. Okay, and you're live. Congratulations. And we can see visually here that we do have those PQRST components of the QRS complex that we like. We can have them just distill for 10 seconds while the ECG populates the screen. We can then hit pause and tell them they can move naturally. Then what we're looking for here, again, is going to be just as a PQRST that I talked about before. So if we're focusing here, we have the little P wave that comes before the large ECG spike. So it's, again, the atrial depolarization. We have a nice trough. The R peak being the most important thing that we're concerned with. If I had nothing else down there, but I had the R peak, then I would be pretty happy because that's all the analysis based off of that timing. It's from that fiducial marker that we're going to say from one R peak to the next, what is the time between them. So that is the most important component. But then having these other components on here can help us identify that we have placed the electrodes in the right location. So this would start to look different if we use different configurations on that triangle. Or if we put the electrodes sort of in the wrong sort of laterally on the body, you'll see that these P and T waves start to change in form a little bit. But mostly, yeah, seeing that we have PQRS and then finally this T wave, the particular repolarization, and then we have a pretty good go on that. We don't have to verify the range or the amplitude of the ECG. But as far as the differences between them, so on the Y here, we have the raw data in volts. Scaling, if we had applied any of our scaling methods to the data, which we don't have to with the mobile, it's volts to volts. So these are two identical because that's off. And then the green filtering here is if we had a filtering applied. Again, I did put the ECG on before, but typically I would have that off unless there's a reason to have the filter on. So then now yellow, red, and blue are all the same. And then finally the waveform math, if we had to make any adjustments to that, which we can't do in a second, but that is on none, so then they're all identically the same. So you can verify that everything is looking correct at each level because they're additive. So if we had the raw data plus scaling, that is the red. If we had raw data scaling plus filtering, that would be the green included, and then all three of these together, if we had waveform math, would be the blue. So I would normally recommend that we look at the raw data here to visualize that. If it's easier that you might potentially have some sort of filter on, but we know we're never going to have to scale it because we have the MindWare device, then the green is maybe an easier row for everyone to focus on. So anyways, you look good here as far as the ECG. Well, both, but so everything's set on that one. Next thing we can do at the top right is we can drop down to the next waveform to visualize that, make sure that everything looks good. So I got to Z0. So again, if you can kind of stand still and breathe normally, see if you can actually do that. And then I can hit the pause button. And if you can, actually that's perfect. Okay, cool. So yeah, same deal here before. If everything's off, then they're kind of all the same, but we can focus on the green one. And this is exactly what I want to see. So what something we're looking for are these triangle waves. And before, if you remember yesterday, I talked about how the Z0 signal actually includes both the blood volume that's being pumped out of the heart each beat. So if we actually were to detrend this, remove these of this other wave that we're riding, so down and up and down, these are actually the respirations. So as he's breathing in, breathing out, breathing in, breathing out, we can actually see that in the Z0. But if we were to detrend this, rectify everything perfect and flatten that out, we actually take the area under the curve of here to the DZDT max down to its baseline, and that's where we can actually get stroke volume, so how much blood is pumped out of the heart each beat. Cardiac output being those data essentially multiplied on the heart rate times for each minute of blood pumped out. But anyways, this is how we can actually drive respiration from the impedance signal. So if the constant current is going through the chest, it's extremely fast frequency. It's 100 kilohertz, so 100,000 times per second. It's sending through that electrical current. And then two frontline ones are receiving that signal. Again, if there's blood in this area, the highest concentration is going to be the aorta of the heart. So that electrical signal from the back is essentially going to hone in on that point. And then from that point forward, the two frontline ones receive it. So if there's blood in the heart, we're going to have very little impedance or very little resistance in the signal, because blood is a very good conductor of electricity. If blood is ejected out of the heart, peripheries, and we have more resistance because that electrical signal has to go through bone and tissue, which are not as good of conductors as is blood. So that is actually what's changing the modulation of the signals in the triangle wave function. The other thing that is happening with that constant current source is it's traveling through our chest, is that it's going through the lungs. And so as we breathe in, our lungs expand. As we breathe out, they contract. So the actual distance and time that it takes for that signal to go through changes depending on the breathing patterns. So we can actually use that trending, remove the actual trend from the Z0 signal and apply that to a slope change factor. So that is, again, the y equals mx plus b for that slope change. So we can actually say, like, this is a respiration here, here's another one, and we can create that on transformation and create a respiration signal. So that first derivative, the first mathematical derivative, dct, is the next thing we want to look at. Before we do so, though, there are two waveforms that we want to visualize to make sure that we're in the correct range. The first is Z0. We want to make sure that we are between 5 and 35 ohms. You're a little bit low, don't worry about it, it's okay. So this right here, I mean, he's right on the borderline here. What I would probably do in this case is just wait a couple minutes to see if essentially that gel, the electrolyte on the ECGs, can saturate that tissue a little bit more and bring it up to an order of range. If that doesn't happen, 4.95 is, I mean, and honestly, I would probably just run that protocol. I think it's close enough. And in a lot of cases, he's running up to 5 here on normal. So I would probably leave this one alone. But if you needed to, if you're far below 5 or below 5 in that fashion, really, taking your sensor out and, you know, applying them, you'll have to take the old ones off, a sort of wet wipe to get that gel off, dry that off, alcohol pad, new sensor, tape it back up. So something no one wants to do from everything I just said, of course. So it's pretty rare that it does happen, but certainly can be the case. And yeah, so normally what we see here with the ECG or Z0 being low is the sensors are dried out. I mean, that's not always something else to do with it, but it can be indicative of a lower electrolyte balance. So if we're not getting certain electrolytes, you know, usually potassium is not the issue, but if we have, I'm sorry, usually sodium is not the issue, but sometimes with potassium, sort of the intracellular electrolyte can be a little bit low sometimes in some people. So that can create one of those things, but it's still rare. The thing that's more likely is that we have a higher ohms rating, which is essentially less resistance, and that is due to dehydration, essentially, in a lot of cases. So most likely the sensors or the dehydration could be other things, but that is another reason why ensuring that, at least notifying them, letting them know it's important that they drink plenty of water and don't drink alcohol in excess 24 hours before they come in is very important. But anyways, this looks great. You have your little triangle waves there. This is going to look different for every person. So I wouldn't use these, screenshot them, print them out, put them in manual and say it has to look like this. It is nice to the general framework. Those participants are going to have that same triangle wave structure. If we put the sensors on correctly, they're not dried out, etc. But in some cases, again, it's just not this purple triangle wave, but you have that. So congratulations.
What was the frequency for impedance again?
It's 100 kilohertz. It's 100,000 times per second. Okay, and then here is that derivative of Z0. So we've done those things I talked about. We have detrended it, so we're not seeing those up and down waves due to his breathing. And we've also interpolated to make sure everything's positive. So in that way, if we had put the either of the positive, negative on the sensing or constant current, because we rectify it, then our system will automatically flip it for you. That's not a problem. ECG is not the case. So if we had put those in the wrong one, you actually see the ECG upside down. I'll jump back to that actually when I'm done so you can see what it looks like. But in most cases, it's pretty obvious. In some participants, it's not. Like we actually have the R peak as that pronounced sort of marker there, and that trough afterwards. That sort of the S location of after the peak occurs is sometimes equidistant from the middle of the ECG as the R. So it looks the same in a lot of cases. And I will show you how to identify that a little bit better. In some cases, it's better to just collect the data. And then when we're doing the analysis, you can visualize to see if the P and T waves are both positive. Because there's just a button that flips it. It's not a big deal. So if you have that sort of ambiguity, I wouldn't necessarily go into worrying too much about flipping that on and just notate that error a little bit. The question of its polarity. But anyways, this is perfect again. Did a great job picking him up. This is exactly what I want to see here. And I think he actually does express a B notch. If I had to guess here, I can actually see a little bit of a change here occurring right where that B notch location should be. So hopefully this is something we can add later. And again, we don't need to sort of look at the range on the Y here because we did that with the primary Z0 signal. So if that's in the correct range, its derivative will be as well. And then lastly, the skin conductance here. So as far as this goes, this is a much slower synthetic marker. What we just see in a lot of cases is these nice crisp rolling hill kind of smooth architecture contours that we see here. If there's a lot of jaggedness to the signal, again, that's usually due to, older sensors or their participant is dehydrated. In the cases where someone's slightly dehydrated, this is usually the best place to look at it for the skin conductance because we're going to have less of that sweat available. Especially for the sympathetic reactions, we're going to focus physiologically on thermoregulation being a little bit more important to keep us cool in some sort of fight or flight scenario. But yes.
Does the temperature of their hands affect this? So, some people just have really poor circulation, really cold hands. Is that can affect your hydration?
Not as much, no. I mean, like, if there's like extreme temperature changes, then you can certainly see that, but if they're habituated to that environment, then it's not quite as bad. Yeah. I mean, you can, if you wanted to, you can abrade their hands a little bit. I mean, that's typically like not a great idea. It can be painful if you're using like a pumice stone or something like that. So, usually not a huge problem.
Okay.
Yeah.
I have a question, but it's like a kind of like my own experience because I have ADHD and I take stimulant medication, and this makes my hands like feels pretty cold.
Mm-hmm.
But you said it doesn't affect if it's like a natural like the temperature change, but if it's like a body reaction, does it change? Does it affect the reading?
Absolutely. I mean, so classifying and doing a self-report on their drug use, both medicinal and recreational, is extremely important. So we can look for any sort of areas afterwards. It's usually not the case that it's going to be exclusion criteria because again, if we're looking at a normal population and we're excluding everybody that's on some sort of amphetamine for ADHD or something similar, like you're going to get rid of a lot of your population. In some cases, we definitely want to do that. Other things like SSRIs, MAOIs, any sort of like barbiturate receptors, things that they're taking, we're going to have to essentially assume in a lot of populations people are taking it. We're going to get rid of like 70% of our population if we do that, but still notated. So ask the questions: are they what kind of medications are they taking? And then later on in analysis, we can look at a group that doesn't have any sort of reported drug use, those that do, and then we can look for sort of a statistical difference between the two. If there is, then we'll exclude potentially the participants that are taking a drug that is having a reaction. If not, then we're just going to include it back to the normal group. Okay.
Okay, what about external environmental conditions? Like if you're testing in more which less human conditions?
Yeah, I mean, that definitely have an effect on it. Not just the sensors, but the actual person. So going back to a little bit what I talked about before, if the person is living in that environment and they're just adapted to it, that's normally a little bit more stable. But you should expect either just globally and even between races, you're going to have a little bit of difference in fluctuation. So there's definitely some notable. What I would normally recommend in that situation, like if you can have them drink water, that's great. But in a lot of cases where they're not used to drinking that much water, we might actually see a little bit of a different change from the normal state. But sort of stating outright that when we tested certain amount of individuals preliminary, we saw an average skin conductance level of this, and so we can now sort of change our range that we're expecting based off of that sort of geographical location. So for instance, skin conductance is normally our participants are going to fall between 2 and 20 microsiemens, so that's a pretty good range. As far as the reportable range, it's about 0.5 up to 35. So if we're looking at an area that is very dry or something, we're expecting or even testing that participants are a lower hydration levels, that would be a reason to sort of validate the reason as to why we went down and looked at skin conductance down to about 0.5 microsiemens.
So if you were doing like field collections, then you would just maybe know like if this was collected in summer versus this collected in the winter.
Absolutely, and yeah,
And not just because of the physical temperature, but like you're saying humidity.
So the first time I collected EPA was in a study of adolescents in Washington, D.C. and there's incredible seasonal variation
Uh-huh.
in the humidity level. So we actually had a Humidex here in Philadelphia, and we reported the daily humidity levels.
And these just
Yeah.
that as a quarter, yeah. And
Absolutely, yeah, and then, you know, like just in addition to the, you know, basic, you know, sort of measurements about their height and weight, which we saw an impedance application could be helpful if we want to use that different stroke volume calculation. But in addition to those, I would just get general other health information from them. So height, weight, you know, BMI, and then and activity states as well. So how active are they? Are they engaged in a lot of activity sports? Just something that, you know, potentially gather that information for some sort of, you know, covariate or change in their physiology later on.
Do you recommend during this like signal check, making sure electrodes are set up correctly, that waveforms are interpretable, having participants move, having them talk, trying to get a sense of like what's gonna cause a problem before you actually collect data?
Like, so for instance, like having them sit here looking
Yeah,
at
you
it.
say
And then,
it's super still, it's like great, amazing, the data is perfect, but in reality, in the lab setting, you're probably doing things. And when I've like trained people on how to collect data, I've always had whoever my volunteers, I'm like, be a bad participant just so they can see what bad quality data looks like. But I've always wondered, I'm like, should I try to preemptively figure out which electrode's gonna fail?
Yeah,
in the
that's-
movement
yeah, that's a
before I
very
collect
great
data?
idea.
Or is that kind of like, no, you set it up really well, don't intentionally mess with it before?
I would definitely do my advice if you're, you know, expecting a lot of movement there, especially with the kids. You know, there comes a time though where you have a certain amount of time
Yeah,
participants in here versus like checking every possible condition, so you have to balance that a
Yeah,
little bit.
yeah.
But I think, you know, having them, especially like talking isn't usually a problem.
Usually, like,
You can't
easy
usually
work.
visually see a difference in a lot of the waveforms from just talking. I mean, it's going to be just slight, like, you know, interval changes that
Yeah,
are hard to
I've
see.
done
But
it
like,
more with like impedance, trying to see like, did we offset enough?
yeah, absolutely. So that's not a bad thing if we have the time. Yeah. Thank you. Wait, so something that happened because he's kind of relaxed here a little bit, so it's why I start talking, of course. Is that we actually see the lines become a little bit jagged there, but that's just because the waveform, the actual software, is just zooming in on it more because the range to sort of change up and down is less. That's not a problem if we see something like that. And actually, don't do anything, don't think. Okay. If you know, obviously looking between here, we want to be between 2 and 20 microsiemens, well within there. You know, most people fall in kind of, I mean, I don't even want to say that, but most people are around 8, sort of. But between 2 and 20 is great. And yeah, so if we do see this jaggedness, and most importantly, we see this sort of straight line going from quadrant 4 to 2, this is fine in most cases, especially if they're in that range. What this is indicative of is just sort of sympathetic withdrawal, this sort of activation, at least at that organ. And what we'll want to do in these cases, even though we are on the correct level, is we're going to want to induce a skin contouch response. So again, if you remember, we can have the sort of psychologically driven ones and sort of the same. We can have a respiration that actually creates an SCR just due to that sort of connection between our respiratory and sympathetic nervous system, which I'm very happy about, because if I see a tiger, not only can I run away, but I can also breathe and not pass out. So because of that, though, we do have that connection there between the two. So if I saw something like this and everyone's just kind of chill as cucumber, then I would just have them take a deep breath or a deep sniff. And then about 1 to 3 seconds later, we see that rise right there. Everything becomes clean. And then we can know that we have a good connection with the sensors. Yes.
We've had, so in our study, like sometimes the EDA sensors would be like falling off, and then I think I just put more tape on it. Would you recommend actually just like swapping a new one, or like
The new sensors?
Yeah.
Yeah, I mean, if it becomes a problem where, like, you know, you push down, like, the gel's squirting out and you're not sure about that kind of thing, I would definitely take it off. One thing to do when you're, I actually don't have any on me, I don't think, unfortunately. Yeah, sorry. There's, you know, just wet wipes, the sort of ones that don't have any alcohol in them, and they're like sort of gentle for, you know, skin and stuff like that. There's little pouches, I don't have them, unfortunately. But having those available is nice because we don't have to have them go wash their hands again with everything, especially taking the mobile into the bathroom and stuff like that. So if you don't have a sink available, especially, I would have those wet wipes there. So take those off. You know, you have to get the gel off the wet wipe, flip it over, make sure you're cleaning their hand, dry that off. new sensors, take them back up. But
It's like they're pretty sturdy, that we could like.
Yeah.
Maneuver and kind of keep that.
yeah. So I would just tape them down now to begin with.
Okay.
Just try to prevent that as much as possible. But yeah, definitely taking the back off and making sure that we have good ones. You know, of course, if you do that, you have another 5-minute waiting period after that. So trying to get it done upright would help a lot, obviously.
My question was just gonna be about that waiting period too. I know that, yesterday you were talking about kind of waiting a little bit before like collecting a baseline, for example, or continuing with your next task to allow the electrodes to like, kind of like in the pace to start kind of setting in. So you said, so if we would do that in our protocol, would 5 minutes suffice, or is there a specific amount of time that you know, recommend?
For Synchronization, it's 5 minutes. Yeah, the other ECG, I mean, stuff like that. I mean, like that's just a couple seconds or something like that, 30 seconds is fine. But with the Synchronization ones, I mean, if you're, maybe your question is a little bit like, if we already put Synchronization sensors on that gel saturated, why can't I just put new ones on and record it right away? Theoretically, you could. It's just to make sure you're exactly in that range, that same spot where you put this previous sensor on. So I would say that clock probably resets in a lot of cases when you put new ones on. Yeah.
I mean, it was, I think I just was concerned about the fact that like, we would want to switch them if, because the appearance of them is just like 4 at that point. So we're sacrificing data quality if we keep the same electrodes. Hence, I think why like Joanna was asking that question about, is it better just to replace them? But at the same time, thinking about kind of protocol, if we do start to implement that switching of the electrode, wanting to see, give the appropriate amount of time to wait so that we're still kind of like, because you would accept if you wash your hands or if you wipe away, like you're also wiping away sweat, right? So it could cause like the skin to dry. And so I wonder if that could be like confound, especially if it's like before or after like a stressor, like if it's after a stressor, are we really getting a measure of like their skin conductance level like going down if we just wipe their hand or,
Timing is a big one on that. Like how long from identification of like, or the sensor falls off and we see it to how long we put the next one on, that matters, right? If it's like 10 minutes or something, then, unfortunately I would recommend another baseline potentially in the middle of protocol or, during a recovery stage or something like that. But yeah, I mean, as far as the drying their hands out, I mean, the sweat, as long as we're not putting any sort of glycol alcohol in there, I mean, there's plenty in there available.
Yeah.
So we can pump the other stuff out within, a couple seconds, of course. But when using the soap specifically, there is something we want to use again, is something like very low in alcohols and stuff like that. So not the Gojo soap that they typically have in there. That's going to be just 90% alcohol or something. Having a low alcohol soap, there's on our web store here, if you go to our site, there's this soap we recommend. It's actually very cheap. It's just soft soap, and it's just the Aquarium series, and so it's like $1 at Dollar General if you want to get it there. But that's a nice one to start with, so you're not using some, stuff that's gonna dry them out.
Okay, sorry if I like answer or if I ask kind of follow-up questions because I want to see, because this could potentially really help us. So so let's say because what we've noticed a lot is that it's generally like during and after the stressor where we really get that like the electrodes coming off, just because it's like the kids are really nervous, and so even though they're not like necessarily like using their hands for that task, maybe through like nervous trying to self-soothing behaviors, they might just be pressing or scrunching their hands in a way to sort of self-soothe. And we tape their hands a lot. But even if they're not like, if they're trying, we always tell them like, please try not to squeeze your hands. So they're also aware of it, right? But their hands get really sweaty. So would you say that it's recommendable to switch to like, I guess we're just concerned in terms of kind of like post stressor, would we wipe down the hand with like an alcohol free like wipe, stick the new electrodes, wait maybe 5 minutes and then count that, because that would essentially kind of interfere with kind of our post-stressor period, right? So I guess that's kind of where our concern is. Is that something that then we would have to make a decision about what we're weighing or what?
Yeah, I mean, that's a tough to give like a blanket answer on. Of course, if it's in that recovery stage that we're going to use as a potential change score or return to baseline kind of reason from a post stressor, I mean, like that's a really tough one if that falls off. looking at everything we're collecting now, like what's the most important thing that we're concerned with, right? Is it ECG and impedance or skin conductance? Like,
Right.
because if we have to stop things for skin conductance, you're stopping everything, right? So I would take that into consideration quite a bit. But if it is something necessary, then yeah, I mean, stopping it, doing a recovery, you have to do another baseline, but you're going to lose that window of recovery from that stressor. So
Okay.
yeah, it's a tough decision to do there. So take as much as possible. Another thing with the kids, it's just like, is it's actually due to the sensor is a little larger than a lot of their hands is. So when they move it, because the sensor is larger, they're more likely to come off. So in a lot of cases, what we can do is we can trim. We can just take some measures and trim around that rectangle, just ensuring that we're not. I'm just going to show it on the circle, but just ensuring that we're not getting into that little gel pocket. So right outside of that, about centimeter outside of it, and then when we put it on their hands, tape over, and that can help quite a bit.
Okay, that's really helpful actually. Especially with the younger kids.
Yeah.
Their hands are slightly small.
Yeah.
They're not too small, but some 11-year-olds are really tiny.
Yeah, and also like considering for a new study that's beginning a different site, like is it the wrist, which is a little bit more common, is it the shoulder, things that we can look at a little bit later. Yeah. Yes.
I know you mentioned dehydration can impact the quality of the signal. Does like overhydration have an impact? Because kids are also doing blood and saliva samples, so we have them like drinking water in specific windows throughout the session, and if that's like not normal for them, does like being overly hydrated impact? Is that something we should like put down, or because it's everyone? It doesn't-
Yeah. So when I was looking at the sorry if I talk really fast. The impedance signal here. So as far as skin tests we just saw there, it's pretty rare, and as far as like North America and developed countries that just due to our diets, even if they're bad, we still get a lot of electrolytes in them, especially sodium. So we don't normally see that if they're like overly hydrated, that like skin conductance goes above 35 microsiemens, and like that's usually more indicative of just somebody that has like hyperhidrosis or something. But as far as impedance, yes, it can happen. It's quite it's pretty hard to do. But I have a little sort of anecdotal story personally about this. So I had a friend in college, and I was into this at the time. Of course, I was born sort of interested in this. But he was a track star at Ohio State, and he decided one day to start drinking distilled water on its own, and was always drinking distilled water and not getting enough electrolytes in, and yeah, almost took it to the end there. So finally found out what it was going on with them. I was like, don't drink only distilled water or something like that. But in most cases, yeah, if you're doing like a lot of hydration intake, it's still pretty rare that you would put them out of a range just because of the fact that we get a lot of it in our diet. But if it did happen again with the Z0 signal, sort of a reduction in the ohms here is usually going to be something to where they are overly hydrated there, because yeah, there's sort of like more distance and everything between those electrolytes. Like water is a good conductor, electrolytes of course, but it's a little bit less if it's spread out, right? And so when we see something though where it's much higher, that's more indicative of the dehydration. So if it does fall below that 5, that's possible, but it's very rare, yeah. Okay, so skin tests, I think last thing on here. So there's a Z0 signal going to be between 5 and 35 ohms. And then with the skin conductance, we want them between 2 and 20 microsiemens. Again, using some other contexts that I talked about before, we could expand that up to the lower being 0.5, 1/2 of a microsiemen, up to 35. But that's about 6.5, great. And so we're good to go. Any questions on these signals, verifying the ranges, anything like that? Yes.
So this is more of a general question, also for everyone as the data. So do you like kind of do some kind of normalization across participants, because some participants could just have it 1% 2 to 4, some from 10 or something. So
Absolutely, yeah. Statistically later on, you're going to want to normalize those data in some way. Especially the sympathetic markers. There's a lot of variance between participants with that. So yeah, you'll definitely want to do some sort of Z-score or something to normalize this. Anything else? Great, awesome. So, yeah, I guess now you can take a seat so you're not having to stand the whole time. There's 2 leads behind you, so if you want to just move those a little bit to your side as you take a seat, so sit on them. Perfect. Okay, great. So now what we do is we can, as a group, maybe stress them out horribly. We can do them a speech or something. What do you guys think? Something? TSST right now? Oh wait, Paul, you have an ice bucket, don't you? You have it ready? Yeah. Experience. That should work. Actually, right now. Okay, so at that point here, what I can do after I verify the signals is I can hit there to move to our next screen. And as everyone saw before here, what comes up after that is our software asking where do you want to save this file. And I'm going to save this onto acquisition 2. And then I left my transient screen on just so we can see what that looks like with actual data. Great. And then again, at this stage here, we can start manually if we're under one of those conditions I spoke about earlier, or we can sit here waiting for the UDP network packets to trigger us to say start. Or if we were on a more proper trigger mode, this would be grayed out, so we can't hit start. And then once we receive that TTL, that sort of electrical digital pulse, then it would start for us automatically. But just pretend that we don't have any of that stuff. We're just doing some sort of dyadic discussion or something protocol. Then we just start at this point here. So common question that comes up is, you might have a little bit of 60 hertz there. Oh, it went away. What were we doing? Laptop? Yeah, something. Is you touching your laptop now? And off. All right, could be that.
Oh, the chair has like metal on it. I don't know.
Okay. Yeah, it seems like it was on your touch or something. Anyways, one thing that can be done here is, you know, certainly if we see something's wrong, and hopefully we caught it in the preview stage, but if not, we can hit stop, go and check it out. But another thing people will do is if they hit start, that is maybe sometime at the beginning of the baseline, when they hit start, I would recommend that you hit start, give it a couple seconds, because, you know, you hooked them up, you sat them down, they're doing their thing, but, you know, before we actually do the protocol, I would have it, you know, just a little bit of data, and then hit a function key to actually start the baseline. That gives you a little bit of time. Okay, you hooked them up, the system started, everything's running. If there's another program on the PC, you can make sure it didn't crash everything. And then we're going to hit the event marker once we are settled, not just them.
Okay.
Yes.
Just what you were saying there about the buzzings. Do you actually put your hands on your laptop? See if it does. Yeah. So there's a little.
I think it might actually be a move and dart effect from him moving his hands over because we didn't tape those that other lead down. Yeah.
So one of the things that often in studies where many people do laptop or tablet based interactive tasks. Is that likely to make it more likely that we're going to have to apply the 60 hertz filter if they're actually interacting with electronic devices?
It's not as likely because laptops or even PCs, they have a like a converter. It's a transformer essentially from the alternating current to direct current. So that's this guy right here. That's what he's doing. And so because of that direct current, it's not going to create that acoustical harmonics that we see typically. But in a sort of slightly less likely scenario, though, if you had a very hard metallic, sometimes an Apple laptop that case, that is now an antenna receiving more any sort of interference. And so by touching that, it's possible you can get a little bit, but it's pretty unlikely unless you're in some sort of environment where there's a power transformer right next to you or something very powerful like that. So not usually a concern as much. If you are having them do something, that is a nice application for like a response pad from ePrime or from Cedrus, because those are going to be completely non-metallic interface. But one thing we can try here, which might work, is we can just show everyone what that might look like. It doesn't happen in a lot of scenarios, but if you want to come over here for a second, I'm going to go ahead and plug the mobile device in, and we'll reflect the data, and we can see if it'll do some of that current here. But usually the transformer is doing a good job, so it doesn't hopefully. So don't really any there, but if they are touching something that's plugged into the wall, like a power cable, let's say they're sitting at a desk, they're doing computer-based tasks, and there's power cables dangling under there, their foot touches it, like you can definitely see in that case, especially if it's transformer, that they might be touching something. So definitely be cognizant of that. Fortunately or unfortunately, we can't, make the 60 hertz happen right now, but there is a support article. If you actually go to the training guide that I showed you before, one of those articles is 60 hertz noise, and you can see that and plan and filter what it does for the data. So never mind, you can sit back down with this. Yes.
So how much of an impact is sitting in the chair and then pushing it on to the chakras?
Not that much. So you'll see that the impedance signal does degrade quite a bit, like right here, when that occurs. But if with the ECG, it's really pretty standard, especially if we use the tape, and it's also in the front, so it's not so much a problem with the chair. With impedance, it does degrade the signal, but how we actually analyze the data controls for that in a lot of cases, because we're not using every single beat, essentially with the blood flow, to look at those individually. You can. Some people, you can actually do pre-ejection period on a single beat. But in most cases, we're looking at an ensemble average. So over like 30 or 60 seconds, we're looking at every single one of those. So in a lot of times that washes out the effect of any sort of movement artifact. If it is a problem when we do an analysis, and we're like, hey, these 5 seconds, they were rocking back, forth, like, or something like this, but it was happening for a very long time, we would go in and just delete those RPs and remove those messy signals. And if that happens enough, of course, within a segment, then we're going to have to discard that one. But yeah, the fact that the current is being induced from the back ones and received on the front makes it a little bit less susceptible to motion artifact as well. Okay, so and then I guess just sort of showing this graph a little bit. If you do some pace breathing, 3 seconds in, 5 seconds out. And then the respiration being in red here. So we can actually see that correlation there between heart rate increasing, he's breathing in. So a little bit of a latency there, of course, as there would be. But anyways, yeah, this is something we can use again for some rudimentary biofeedback. Another application for this trending screen is even if we weren't planning on doing any biofeedback, we can have this open, and most commonly just the heart rate one, which is in white here. And we can have this on the screen, and we can just keep an eye on their heart rate. If we're doing some sort of like really railing them on stress and stuff like that, it might be a nice idea just to make sure that we don't exceed any sort of healthy heart rate range for that participant. It's in a 5-second bin. So every 5 seconds, it's taking that average and then populating this cell right here. So normally that's not necessary, but if we get something in excess of like 120 beats per minute, then that's usually the idea to dump the entire ice bucket over them and then stop the protocol. Okay, so from here, the data are flowing across the screen. We have our, at the top here, next to the real-time event log, we have all the different settings that we had done on the previous screen, just to sort of show us the last time what our settings are done. And we have a real-time clock over here, our sort of absolute time. This is based off of your Windows clock. So yeah, make sure that, especially if you're traveling with a laptop across time zones, that this has been set correctly, because if not, then your clock right here will be off. The thing underneath it, the duration, is just a relative count of how many seconds we are into the acquisition. When we're looking at signal quality, or potentially we're in an environment where there is a lot of EMI, there is a higher probability that there is a disconnect from the mobile device and the router. So one way that we can kind of look for the signs of that is to look at the duration clock, this relative clock here, and essentially every second it updates. Even though it's sampling 500 times per second, we see a change in the clock every second. And if that is drifting sort of from what you can see in the clock in the seconds here, you can also sort of, we have an idea as humans what a second is. If we see that sort of being very slow compared to normal time, or let's say that it got stuck at 500 seconds and it's like 3 or 4 seconds later, and then all of a sudden our data flows in and catches up within the analysis window or the actual acquisition windows here, then that's usually saying that it had the mobile and the router were actually not connected for those seconds. Once they reconnected, the mobile device, which can cache the data for 2 minutes, fed that back into the router. If it's disconnected for more than 2 minutes, it's going to completely disconnect. You're getting a window pop up saying the mobile disconnected, and at that point you'll go back to the main screen. I think it's I forget. I think it's configuration, and then you'll have to redetect devices, and then go back into your protocol. So just kind of being aware of that. That if you see that sort of situation and it's being slow, and all of a sudden you're at a point between stages of actually acquiring data, something like the recovery's done. Okay, now they're doing something for 20 minutes, and then we're starting to look at physiology again. That's a good time to potentially unplug the router and plug it back in. When you power cycle the router, it'll automatically scan your area and it'll check, it'll put it on the channel that is least busiest at that time.
I have a quick question.
Yes.
What does it mean? I think you explained yesterday. What does it mean when you say sample 500 times in a second? Is it detecting data 500 times a second by electrodes?
Yes. Yes. And that's good that you brought that up as well. So in the devices, I talked about this in the beginning of the first day, but everyone wasn't here. When in selecting the device, even if it's not one of ours, we do want to make sure that it is sampling, especially ECG, at a minimum of 250 hertz, 250 times per second. That is per the HRV guidelines. And other waveforms can be sampled at a different rate. I would definitely make sure that's well for impedance as well. Skin conductance can be sampled at a much slower rate, but I would recommend you find a device that can sample all of the waveforms at the same sampling rate, because if we're trying to look at something like that convergence or divergence between, let's say, sympathetic markers, and one sampling at a different rate, you're going to have phase shifts between the two. There's not going to be this perfect millisecond correlation between them. So having something that's 250, the mobile does 500 on everything.
So I had a follow-up question about kind of like recommendations for situations in which the mobile disconnects. It's very rare that happens, but it's happened to us before. And I'm assuming it's like having to do with maybe like network connectivity. And so, let's say we're in the middle of like, we just finished up baseline and things like that. Would you recommend, you mentioned unplugging the router and then plugging it back in, right? How would that be just within having the same file like open and recording? Or would that be like, would you recommend trying to like stop it and then just start a new recording and just kind of calling it like part 2? Just because I think we've had that issue of where they're like the clock time on like the on BioLab is like slightly delayed, and so our concern is like, okay, how is that gonna like impact our event markers? How does that impact like what we're actually seeing like on the display? Is that like what's currently happening, or is that just like data that has been recorded, right? So I think I'm still a little bit confused about how that works, and maybe some recommendations for like if that happens in the moment, kind of like how to troubleshoot that.
Yeah, sure. So I mean, no, not just keeping the same acquisition open. So as soon as we unplug the router, the box is going to come up like right within this window. It's going to kick you back to the main screen, and it's going to say lost connection because that network is no longer connected to the computer.
Yeah.
So you would definitely want to, you're going to exit the acquisition, and you're going to configure your devices again. When you plug that back in, it's actually a computer Windows thing to where it gets assigned an IP address from the router, and that has to happen again. And so I'll go ahead. I have enough data. So let me answer that in just a second to let you show you what to do in that situation. But to answer your first component of it, yeah, like you would not be able to do the same string. So you're going to have the part 1, part 2. Well, I guess you're going to have part 2, and then you can relabel part 1 maybe later. But anyways, the last thing I want to show in here is a couple of these other buttons over here on the keyboard strike. So So the keyboard events here, like I said before, we can actually, oops, I had to hit function key here. So I had to hit, like, for instance, laptop, I had to hit function and then the F key. So that might be a reason as to why I just want to get over here on the right. It makes it a little bit easier for me. But anyways, when I press these things here, we can see that they show up here in the real-time event log. So just confirming that they're working for us. And then here's the F11 key. So this is that live sort of defined event thing that occurs here. So, something that has occurred if we're doing it as such as like a behavioral marker. If it's not one of those first 10 things that commonly happens in your lab space and it's something different, we can type that in real time. And like I said before, if we drop this down before we do anything, here's my example because I always unfortunately bring up my issue of people falling asleep during my protocols. But this will save the last 25 things that you've typed in. So we could, on purpose, before acquisition, come in, collect white noise, put in our 25 things that we want in addition to the 10 on the previous screen. And then when we come to this, we can kind of select those as we go along. But it's usually better for when those are actually points of the sort of behavior aspect, not necessarily the markers, because it's going to take us time to drop that down, hit F11, or hit F11, drop that down, and then select OK. But when we do type something in, such as the cough here, and hit OK, it's actually time synced to when the button was pressed, not to when you hit OK. So you have as much time as you need to fill that in and enter it. So I guess there's my event that occurred at 11:22, but it's already 11:23 when I actually hit that OK button. Okay, last thing on here is the journal. This just opens a text file that is saved in the same habitat, if you will, as the other files. And yeah, you can, any sort of freeform text that you want to put in here, and it's not only tied to that file, but it has the time and date when you open it up. So if there's something that we needed to put in here, such behavioral notes or something, we could actually hit F12 every time that we have a unique note. And then each of those text files has the time at which you entered that information. So it's also the case that Windows is going to save when the file was created, but just if it makes it easier for you, that's helpful. So demographic information came in here. It's not necessarily what I would choose because then you have a text file, you have to transfer it over to whatever you're probably using for that information intake. But it is helpful to have at least the electrode distance on here. So we're collecting from him, so we can say ICG distance is 17 centimeters. And then we hit OK, and then now we have a record of that front electrode distance. When we go to the analysis, it'll be right in that text file waiting for us.
If I could just show you multiple times, so it's just gonna open the same dog or is it gonna?
No, it's a new one, a new unique one. So that's why we can know that the timestamp is when we pressed it. In theory, you can go in and change the file creation time within Windows. Not that someone would like have a Machiavellian plan to do it necessarily, but like can be done accidentally, whereas this has that timestamp actually embedded within the text file. But if you wanted it to be one stream of information, you could just open it near the beginning of acquisition, keep it down here or something, and then just bring it up as necessary. Are we good? Yeah.
I have another question, looking back to the question Charlotte had about like disconnecting the network and stuff. The MindWare mobile is like very, very mobile compared to like kind of a hardwired version, or like alternatives like BioPack, which has an Ethernet cord, like and the power port connected to it. So in the case if the mobile were to get like disconnected or like the RIA forgot to charge it or whatever, is there a way to hardwire it at all?
There is an SD card sort of cord board that can be plugged into the top, and sort of a normal SD card just looks like an SD, but it's just cord board plugs in. It has a cable that comes out and can be put into USB. It's sort of custom that we would make that though, so it's not like super cheap.
Okay.
But that can be done if necessary. What I would normally say is that if you're having problems, there's a local mode, so you can record the SD card. So if you're having those kind of issues, if you go into local mode to begin with, you turn it on, and then there's Wi-Fi local mode down too. So if you go into local mode, you say that these are the channels I want to select, you hit pre-acquire, then it lets you view all of those waveforms, just like our preview did up here. But it's, the actual screen is not like of like the sort of LED quality, so it's a little bit harder to see those things. So if you're having a problem with that, what I would say is connect it to the Wi-Fi, do the preview, make sure that we connected the thing correctly, and then switch over to local mode and record there.
And then if, like, for example, the other, like, version of MindWare disconnects network,
Mhm.
there's no, like, Ethernet hardwired version, it's just like, you would have to reconnect.
Yeah, again, I mean, we can make that thing if you
Uh-huh.
needed to, but it's sort of, yeah, it's a little bit different every time for every sort of operating system and how you need it done. But if that's something that you absolutely need, we can, yeah. I mean, one step before that though, if you're having these very frequent disconnects, I would reach out to our support team. A lot of cases, it can be fixed and or dramatically reduced. So these are dual band routers. The mobile also has dual band radios on it. So in most cases, especially around like sort of academic buildings and hospital settings, the 2.4 gigahertz range, there's multiple channels within there, but the entire sort of frequency range is usually saturated with like 1,000 different networks if you looked at it. Now there's the other major channel array, which is the 5 gigahertz range. And in that, there is a little bit more distribution of like ranges, but it's also the case that university hospitals don't really use that frequency so much because as it is a higher frequency, it can transmit more data, which isn't normally helpful for us because we buffer in the device, but that's why we have it. That's why we have that other band. And anyways, we can transmit data faster between two devices. But what it doesn't do very well, because as we sort of change the frequency, so we have a sort of normal, let's just say 2.4 gigahertz taking up this range, 5 is going to be much smaller than that. It's going to be a smaller waveform in the middle. So thus, if we have the mobile in this room and the router on the other, it's not going to go through walls extremely well, because if it hits something, it doesn't have the range to send some of the packet information from, it'll just be completely destroyed. Whereas if it's 2.4, it has a larger ability to go through walls and stuff like that. So it's a little bit of a trade-off, but if imagine we're in the same room or right next to it, then that doesn't really matter. We can actually disable the 2.4 gigahertz network and then make sure that you're always on 5, which is usually quite cleaner. Awesome. Okay, so that's it then. I'm going to go ahead and stop, and then we'll go ahead and show the network disconnection protocol we asked about. So if we imagine that the router was disconnected, actually, let me go ahead and jump back in so we have a different file here. Okay, so now what I'm going to do is I'm going to go ahead and just disconnect the router here, and then kind of see what appears on the screen here. So it's going to give it a little bit of while or a little bit of time here to see if we're going to be able to plug it back in and create the connection again. But at some point here, it should drop out and give us that error. Again, this could be a minute or two here, but if we can just be patient here, we can get these two what that looks like. Okay, so here it is. And so what we would do in this case is hit OK. Hardware, I couldn't think of what it was. We'll hit hardware, redetect devices. This will take us back to this initial screen. So when we first open BioLab, this is actually what it looks like. I glossed over this because we all said we knew what it looked like. But so when it does that, and especially for plugging the thing back in, we want to ensure that we're on this .88 subnet. So those right there, under the second decimal. That is going to be the MindWare network subnet. You're not going to see that with anything else, likely on your local network. And that's what we want to make sure that's on, because it is possible that we're connected to multiple networks at the same time. So especially with the laptop, we have a wireless radio, and then a lot of them still we have an Ethernet port, or you might have a USB to Ethernet adapter. So, but regardless, you have two networks that the computer is connected to. So you could have, for instance, when we do this, we want to say, let's say that this is not the .88 and we're this is wrong. Settings, change IP address like I just did. And then it's going to restart BioLab after I do this. And then if I drop this down though, we can see there are two networks. There's the .88 I'm connected to, but then there's this IP address because I'm connected to the internet from the university. That router has assigned me a different IP address, so we have two. So it's certainly possible that, let's say we're connected, .88, we lose connection, the experimenter doesn't quite plug it back in, or something occurs where the PC is not receiving that IP address from the router, and then we only have this other one available. They just select it because they're like, oh, there it is, and then all of a sudden we're not going to get that data as we want it. So making sure we have the .88 or investigating through hardwired connection or through Windows network connections would be the next step after this. But okay, so we've selected our .88, and then it's going to tell us we need to restart BioLab. Of note, though, so the .88 is going to be standard and likely the 192.168, but with a lot of IP addresses. But after this third decimal here, those get completely dynamic in a lot of cases. It's just DHCP, so that means the router can assign in any IP address within that range essentially. It's usually going to be something that is higher or much higher than other devices on that network. But yeah, anyways, I wouldn't copy the exact, complete thing. It's more just about focusing on that .88 when we're explaining this to somebody. So I have to restart BioLab, as I said before. And then it should have that .88 connected, and then we should be able to the mobile device and go back into our protocol and hit acquire. So we're gonna go ahead and select that here. So I'm connected. So there we go. Almost did it. Okay, so this is, again, had we done all this restarting or we just began our session, this is the person that pops up after we open BioLab. So then we confirm we're on the .88, and then what we're going to do on the device itself, can you, do you have that on the side? So then what probably happened is it kicked it back to the screen where it says connected. It has an IP address on the screen. Is that where you're at?
I was saying rather.
Oh, okay. So in this mode, just because we just picked the network sort of inadvertently, it can get stuck on this mode, which is, I guess, a good example. So when we're actually acquiring data, it'll say it's acquiring, and it has the name of everything. It says that if we need to unlock, we need to press the left and right direction arrows at the same time. So we just need to do that, and then it'll say it's unlocked. We can then hit the A button to end that session on the mobile device. And again, this happened because what it's going to do is it's going to ensure that any data we're collecting is still stored in this cache, so that when we can access the file, it's whole. It's not like we have some sort of corrupted ending of the file or something. It was manually ended when we hit that button. So anyways, after that, it'll take us back to the connection screen. Then it's searching, talking to the router. Router assigns an IP address. We see that on the screen, and then we can hit the A button to start the acquisition. Here you go. So sometime, usually 30 seconds or less before or after we hit the connect button on the mobile device, it should pop up on our network device screen here. If it takes more than 2 minutes, let us know, because that's annoying at the very least. So that's another thing that we can do as far as changing some router settings. We can also do this remotely, even in a lot of cases in less than an hour. If you call our main line and talk to support, we always have someone answer that. And then if it's an urgent need, we can divert that to somebody that can help you out right away. Like I have participants right now and it's not working kind of situation. If it is not of that level of urgency, we would like it if you would prefer it if you go to our support site and create a support case. It's right on the front of that. But again, if it is urgent, we can certainly give us a call. Okay, but we have our device turned back up. I'm going to hit connect. This is going to save the configuration that I've done before. But Bio1, that's the brown ports on the mobile, and then Z0, DZT, and then JSC is going to connect us. We hit connect, And then now the perfect sort of operations again would be to open the configuration. I would recommend that just to, especially if they have multiple experimenters, because it's just a nice sort of habit for them to do that kind of thing. However, you can, if you have to go a little bit faster than that, the state of BioLab will be exactly that of when we closed it out the last session. Now, I would not just do that and then we're like, oh, yesterday it was this, and then we're kind of trusting it. But in rapid succession, if it's just you, like you could theoretically bypass opening a configuration and then just hit the acquire to go on with your protocol. And you know, when doing this, if this is in the middle of the protocol, I would practice this and be as fast as possible, because we don't want 10 or 15 minutes again in between, like something like a baseline of the condition. If it's in a very crucial point, that's especially in the middle of the protocol, that becomes even more important. If it's in the beginning of it, I would just redo the baseline and start over with a new session. So, and don't delete the file until much later, you know, even after analysis, the analysis stage, just wait and keep it for later just in case there might be something in there that you're like, oh, we really needed that other baseline. So just kind of stay in that framework. Don't try to hide stuff. Paul, Cam, they'll catch you. So just leave it there. Right here on the file mode, so that's an auto name. So if we were to go into acquire and let's say that for every one of these sessions, I'm gonna have to make another one of these. So in some protocols, people are hitting start, they run through something like baseline or a certain part of the task, and then they're gonna hit stop, and then they're, you know, doing whatever they need to do in your paradigm, and then when they're ready for the next section, they're gonna hit start again. It is perfectly fine to do. It's essentially like creating our own manual epoch mode, if you will. But just be aware it's doing the same thing. You're gonna have different MWI, MWX files for every time we hit start stop and start again. So yeah, that's certainly one thing that can be done there. When we look at the file mode here though, if we actually look at the files, I'll show you kind of what that looks like afterwards. So, so here we have the first session, the start stop, and had we not done it twice, it's actually not going to have this _0. It retroactively puts that in there. And the first iteration of that is 0 because it was done by engineers, of course. But this is now the first session. It has a post, sort of post hop going back and going to put that 0 in there because we hit that stop and start again. And then this is going to be that second session that we did there. So again, different file types, and that's kind of what you would expect, that 0, 1, 2, 3. That's why that's there. And the other modes that are available. So we had a question, I don't know if it was you, splining things together. I essentially said don't do it. But if you needed to with 2 of the start stops, you can actually hit this append mode and it will take those 2 start stop sessions and it'll combine it into 1. Don't do it, please. But there's some people that were like, oh, we're doing it. And but the other more common thing that's usually I would advise against vehemently would be the write over method. So when we hit start, where data's flowing, and we hit stop, then we hit start for the next session, right? That first one is erased. It's writing over that first session, which is that okay to do? It's a horrible thing. You took off your glasses, you're like, all right, listen.
Why is that still an option?
So yeah, don't live in the wilds of psychophysiology. Just go stay in the auto name, and then yeah, we can always make a decision way later on that we don't want that first session. Okay, so that's it. for the data acquisition component of it. We got about 19 minutes here, so let's just take a break and then hopefully lunch is within the next few minutes here. Cool. Does anybody have any other questions for that?
Do you want to do anything about other alternative electrode placements or different ways?
Yeah, so we don't have enough time here before lunch. Let me check on the food and I'll see when that's going to be here.
Because it's- yeah.
But that's something that we could do right after lunch. I have some buffer time in there. So. All right, so I'm going to take a break here and then we'll have the food soon. Oh, here. Give me a second. Okay, let's talk. So what we're going to do to first get started is, this is essentially the analysis section of the training for today. And I think what we can do to first get started is I think it might still be smart to go through the analysis if we can, and then potentially look at the alternate EVA locations, if that's okay. We should have plenty of time. I don't fly out until tomorrow, so if anybody needs to, and we actually run to 4 o'clock, we can do it at that point, if that's okay with everybody else as well. But yeah, I just want to make sure we have the actual content here as far as the standard stuff. So what I'm going to do is I'm going to first start with the heart rate variability analysis. I'm going to run to impedance cardiography, and then we're going to finish up this conductance analysis. So the focus of this is going to be mostly on the settings, making sure that we're having the calibration settings done correctly, and then the actual analysis, so things that would actually affect the data and how we analyze it. I'm not going to spend as much time with sorting through the events and things like that. There's a lot of different modes and options. If you have a question, certainly ask me about it. If it's a little bit too complicated and it's going to take a little bit of time, I might take that question live and then have you hold on to it for after we're done with everything. Yeah, and other than that, if there is anything that I'm glossing over a little bit more or a little too fast, like I said yesterday, you can just tell me to slow down or cover that a little bit deeper. And again, kind of deal with that as time goes along. But with these 3 hours, we're going to be probably pretty close to getting through all 3 of these measures and editing these data. Some questions there. So again, if there's anything more complicated or different electrode configurations, things like that, we'll obviously save those to the end. Cool. Any questions or anything before we get started? Okay. Okay, so also I wanted to just show everyone here the sort of folder that with the data files that we're going to be sending out following the seminar. So everyone will get a copy of all these songs, maybe Michelle's files there. Those are just in there, so I have been organized.
Appreciate it.
But yeah, the PowerPoint presentations will include both the one that I presented yesterday, and I also have 2 more presentations that will essentially be from previous webinars to include as well. So those will be in there. And then we have our electrode placement files, our standard, alternate locations, and references, publications, and all the different guides are going to be in there. And then the data analysis files is what we're going to look at right now. Have some prepared examples of normal and sort of ectopic data, messy data as well. And then the data acquisition live, that is, sorry, Kurt, what's his name? Raphael. Keep your there. That is actually going to be his data. I think there's a second or third session when we actually got his data. The other 2 are different examples, which are labels. So, anyways, everybody copy that along with the recording following the session. It might take maybe like Monday or something just to stitch everything together. But everyone has to get a copy of that. But okay, so I'll go ahead and start looking for my third examples. This one you see at top, it has ECG data, impedance, conductance, and I also have accelerometry, which is at ECC. This file set doesn't really clean ever on any previous measures, and so it's a nice kind of frame of what a nice data acquisition quality, data quality should look like. But again, I wouldn't recommend just printing this out, posting it, and saying data has to look like this, or we need to put sensors on or something like that. There's going to be individual genetic differences between people, so there's some changes within that, which we'll see, but it's a good starting point. It's a good framework if you need to start with a nice file. So I'm gonna load that one first, just to sort of explain the applications with a nice data set, and then go into actually looking at the topic MSD sequence. Okay, so again, I'm going to go over some of the very basic setting changes a little bit more quickly. It normally takes about 3 hours just to do HRV training and comprehensively with all the settings and stuff like that. And of course, we need to make that a little bit shorter for today. So I will go ahead and, like I said, do some things. If there's something missing or in your use experience, there's something in between that you don't know about, again, just let me know. But the first thing we do here is I'm just mapping across. We actually will ask you to point the channel to what waveform you see on the y-axis here. This is because for a couple of reasons. One is that there can be multiple participants within your file. So if we have that, when I drop this down, you'll actually see like if we labeled it correctly, maybe mom ECG, mom C0, all these different things, and then we'll have the child versions underneath that. So how we analyze data is one person at a time. So we come in and let's say claim mom's data, we export those results to that XLSX, that Excel file, output file, and then we come back to the screen. So once we do that output, it'll return you to this screen here. Sorry, I just jumped forward real quickly. So I'm just going to map these two. 3. So I'm just going ECG, Z0, ZT. I'll talk about respiration in a second. But anyways, if we did an export for mom, come back to the screen. We don't need to open it again. We can just say, oh, go ahead and map channels, and then we'll switch these over to the other person and conduct analysis. We don't have an edit file yet, so we're just going to say new here. And going back to the respiration and why we're mapping impedance here. So if you remember, we're actually going to be deriving the respiration from the Z0 signal in a lot of cases from the impedance raw wave. And so in theory, we don't have to map the PCT. We could just have ECG and Z0, but it's just good practice to just fill it in if possible. Now, if we don't have a respiration valve, which hopefully we don't have to have, we have impedance, then we're actually going to leave that respiration blank. That really is just for if we have a belt. When we go, I'm going to jump forward to the calibration settings here. If we actually look at the respiration signal we use, when we map Z0, that is the only form of respiration, it'll automatically pick up on that and put it in there for us. Now, if we have a respiration valve and impedance for some reason, you can certainly toggle between the two, and it will pick the first thing it's going to pick is that respiration channel if we map that one. So, anyways, this is how you can kind of change between the two. You can see here if I do also map ECT, I can choose that as a respiration source. That doesn't really make sense in a lot of cases. Some people would like to look at the sort of any sort of effects of respiration on the ECT after it's been detrended and interpolated, but there's usually very little effect and reason to do that. So again, just the sort of oscillation between Z0 and respiration valve if you have that or not. So, but anyways, in this case, because I do have impedance, because I do want to drive respiration from this is the correct configuration. Okay, so as far as the events and modes go, was anybody not here yesterday? Okay. No. Okay. All right. So I'm gonna move through this a little bit faster just because of that reason. But of course, for everyone remotely, we'll cover what I think is a sufficient amount.
I'm sorry,
Yes.
I may have missed this, but are we in BioLab again?
We're in the HRV analysis.
And this is a separate piece of software?
Yes.
Okay.
Yep.
Okay.
Yeah, BioLab is mostly for acquiring data,
Okay.
and then we have separate modular analysis programs for producing the data.
Okay.
Okay, so anyways, you can see here we have a couple different modes available to us, such as time, event, multi-event, and continuous. And then we have a couple different event source windows. We're going to spend most of our time in HRV, and these sort of events and modes are the same, or mostly the same in every analysis application. So focusing a little bit more time on here when we open up the other ones are better faster, of course. But anyways, we have two major things. If we go ahead and start with time here, what we can see here is that we have just a sort of time scale beginning at the sort of relative time 0, and then ending at what happens in this file, 436 odd seconds. And so in this case, if we have this check, it's saying start at the beginning, end at the end. If we wanted to do something a little bit differently, let's say that the intent was really that we wanted to have, let's say 120 seconds. So we could actually type that in, and then this is a little bit going back to what I said before, is if we have a little bit of drift, a little bit of data that is, really something that is not necessary and then we don't want to include because we're trying to standardize the same amount of samples for every participant, and this is something you could do. Of course, you're going to want to think about this a little deeply as to like, is that really what we want to do, or should we have that last 16 seconds and combine that with the other 60 seconds prior to that. So some of this is to be made there, but this is one strategy. Another thing that we can do here is splitting this up into different segments for in there. So we'll want to do this always at some level, just to reduce the possibility of any sort of non-stationary data. Our recommendation is that we do 60-second segments in most cases. If we're in a sort of block design experiment and we're sort of making the assumption that the participant is going to be in the same or similar psychological state during the entire condition, then normally 60 seconds is sort of a safe way to go, because there is a couple rules for HRV, and they're spelled out clearly in the additional PowerPoints I'll attach here. But one of those rules is that we have 30 seconds continuous data for any sort of frequency-based statistic of heart rate variability. So respiratory sinus arrhythmia being that one, most popular frequency-based, and in such that the different committee reports are essentially saying that we need at least that amount of time. Now, the one that was just released, I think it was late last year, does have some definition there on sort of children, adolescents, and those very high heart rates, as to where I think we can get down to about 20 seconds of data they've actually looked at. So we did get a little bit of extra time there if you were looking at quiet data from children. Again, because their heart rate and their breathing and respiration rates are much higher, we actually do get what they feel is enough samples to accurately depict the respiratory sinus arrhythmia. But anyways, outside of that, I would be pretty cautious about using anything less than 30 seconds. It's certainly getting a lot of sort of eyebrows on that, but certainly referencing the new committee report would be sufficient. But anyways, what you'll see a lot of times in the literature is that there's either 30 or 60-second segments. And we recommend 60, again, in the sort of block design where we're just going to average across for every segment within the condition. Because if we just need 30 seconds continuous data, I'll actually jump forward to explain this a little bit better. So there's 60 seconds total here. If there were some issues where there was a lot of motion artifact or something, let's say in the first 10 seconds, and then maybe in addition to that or on its own, there's also some messy data at the end, well, we can actually just delete the data on the sort of bookends here, and just as long as we have 30 seconds of continuous data in the middle. So 30 seconds is, again, that minimum, and if we have just a 30-second window and there's data on the wings that we can't really interpolate at all, we can't do any sort of fixing to it because we don't have a proper bookend, then we really are sort of out of luck on that segment. We're going to have to discard anything. So 60 seconds is a little bit more flexibility with that. The sort of advantage of using 30-second windows is if we have discrete epochs within a segment where there's something that we're very interested in, like a keyword that was, or a topic that was discussed, or some sort of stimulus presentation where there's visual or acoustical or some sort of haptic feedback of some sort, and it occurs at a specific time within a segment, we really want to be able to hone the sort of emotional response around that specific thing. And so if you can imagine, we have a 10-minute trial of a sort of stress induction, and we want to know that the second that they put their hand in the ice bucket, what is the sort of reaction around that, not just sort of the reaction of the next 5 minutes or however long it can last. Then 30 seconds allows us to put a window right around when that essentially the hand was the ice bucket, instead of washing away the effects of that by aggregating the entire 10 minutes, if you will, and averaging across. So there is sort of distinct reasons on when we might want to do different timing scales, but it's also the case to do both, right? If we clean the data and we look at it in the 60-second segments, and then we're going to reanalyze it to look at something like within subject, and we're also doing between subject. When we make the edits, in most cases, it's fine to just load the edit file into the new analysis timeframe or the new mode, and then we don't have to edit that again. We can just load the edit file, change the timing, do a quick verification to make sure that the edits that we make don't like sort of occur right in the middle of the segment when it's 30 or something, and then we can just write them all out at once using this function right here. So it's usually, unless there's again some sort of weird edit that occurs, such as like a mid-beat that is right here during the 30 seconds or something. Other than that, it's usually pretty quick to just jump in there and reanalyze it. On that note, I'm going to skip over to one more mode, which is a continuous mode over here. And so once we've actually edited the data, another thing that we can do is we can load that file, or we can come back to the screen. We're going to want to make sure the edit file is loaded, which we don't have one yet, but it would appear at the top here. And then once we have those two things, we can actually go into continuous mode, and we can reanalyze the data in a different way. So what continuous mode is going to do is, depending on the buffer size we have here, which is 30 currently, it's going to start the first sample and create a 30-second window. And then it's going to move through your data set with that 30-second window in this case. And it's going to use that bin to create an average of the different physiological values at that time. So the most common use case of this is, let's say we're doing some sort of growth curve analysis, and we want to see what is the second-by-second changes in RSA. So something that we would normally need at least a 30-second, maybe a 20-second bin or more, we can now actually see that with that bin, but we can actually see it moving through the data set, not in necessarily these larger aggregate averages throughout the condition. So I'll show you an example of that real quickly here. So in this case, actually, we're going to say the data. When this occurs at this stage, or even if we're in normal analysis and we're writing out, it's going to create the output data folder underneath the wherever your files are that you're loading, and then it's asking you to essentially stick there. So through reanalyzing this, it's going to actually take every example of changes in RSA. It's going to replot that along with heart rate and all these different metrics that we're looking at. This is going to take some time, depending on the computational power of your PC here. So it's something that you can certainly set, and then maybe answer an email or do something else on it while you're kind of waiting on it. But
Jay, is that then the output file is going to be writing out second-by-second values?
yes,
When did that get added?
I was just gonna ask that.
since 6 years ago, I think.
Oh,
People should look to see if our version of HRV has been updated.
Okay.
You need to show me again how you activated that, because that's pretty well seen.
Yeah, for sure. So anyways, it's done for this one. It's just actually a smaller acquisition, but yeah. So then we can hit exit. I'm going to go into our main folder here and go into my examples. And then is our output data, today's date. I'm going to open that up. And then we see this plain text file here. So all of the settings, times, everything, did we use configuration or not? Did we use the edit file? These are all things that we can check on at a sort of macro level later on. So if we were to load these into, make up essentially a CSV file or something, and we want to load it into Excel, we can have a macro that very easily says, let me know whenever Excel says yes, or says no, or anything like that. Just to ensure that we have the correct settings for all these different participants. I also said earlier that we're just this month releasing a new analysis, well, it's not analysis, but a new application necessarily called Study Compiler. We had it before, but it was kind of broken, and so we have a new version, and it'll actually pull all the different text files, all the different output files, aggregate them all together, and let you do some rudimentary filtering the data before you actually export it to your statistical compiler program. So for instance, we can actually load, let's say you have 5,000 Excel file outputs. We can load through there, ensure that all the settings that we want for that study are set correctly. If not, we can actually see those outliers and visually where they are if we want to make a correction on them. We can also apply some sort of demographic information to that, or anything, a lot of different settings and filters that we might want to create a file that is directly ready for SPSS, R, SAS, all those kinds of things. Anyways, so we have the settings here, and we can see here from the samples. So the time 0 sample, this is going to be the first, in this case, 30-second bin. So it's going to be from time 0 to the first 30 seconds. And this is going to be your value, and across this row here is going to be the average of those values for the first 30 seconds. When we see this second time 1, this is going to be the 30 seconds from 1 to 31. The time 2 second there is going to be 2 to 32, so on and so forth. So it's that 30-second bin moving through the data. But then again, yeah, there's all your statistics that you may be interested in, frequency and time domain available for you.
One more question on that. So, in the applications I've seen for doing the rolling 30-second and extracting the second by second process, it's the ones I've seen don't account for the autocorrelation that's being incorporated into the calculations of the second by second bit, where each second shares 29 out of 30, so 97% of its variance.
Right.
For the JSON point. Does this algorithm factor that out to try and isolate?
No. Yeah.
Okay,
So
so it's the same algorithm that the others I've seen applied in other software, not just
Yeah, exactly. There's different ways to kind of split that up with very small buffers, but I mean you're gonna have that regardless. So yeah. Okay. Well, there's a good reason why you were using it. So.
Well, that's we've been having this argument for quite a long time. And I've been very reticent to apply this method.
There is a different method which you can, if you're looking for strictly second by second heart rate changes. I will show you that real quickly. If you go to the calibration settings here, so we have an initial window that can be defined here by the events or just by our timing. In addition to that, though, we can break those settings down into intervals here, so we can actually do it. So the interval, we can change that interval to a period of 1. I'm going to jump forward to the analysis real quick to show that a little bit more. Stop by Zoom. Wrong mode here. So. Okay, so this second by second change, these intervals that I created.
The recording has stopped.
Here. With that. All right. We'll kind of see them around. So with the second by second changes here, what we can see here is over on the HRV stats, we have now a table that is, when we have this on, it's going to create a new book under that Excel output file. And then we'll actually get these second by second changes in heart rate, the energy interval, and the number of I peaks, or I'm sorry, R peaks that occurred within each bit, which is normal one. And anyways, this is something we can use to see those changes on whatever interval we specify. One thing you'll notice that is in some cases we don't have some data that has an interval attached to it. This is just because if we were looking at second by second changes, we actually can't do this on this first beat here because there isn't a landmark on the other side to look at. And if you wanted some more information about this and why that's being applied there, it's called the Graham weighted method of our periods. If we can see today if it works, it's sort of control H function here, but it's probably not going to. No, okay. I don't know why that's happening, but I have reported that we'll see with that. But normally if we hover over almost anything in the analysis software, the title or the cell, we hit control H. That'll actually load the manual for your version of the software. It'll jump to the manual that covers what your mouse is hovered over. So yeah, like I said before yesterday, I've never seen that 404 error in my life, but pretty cool that happened to y'all. So but I'm sure that'll be fixed soon. Anyways, yeah, that's kind of why you see those areas in which we don't have that. There's also, if you go to our support site in the search bar, you can type in seconds or second by second, and then you'll be able to see that some supplemental information in that publication. Okay, so now that we've covered time and continuous, I guess there's one more thing with time, which is this one right here to show events. So let's say that we did want to go through our data set, we don't have any events necessarily that we're interested in. and we have 60-second segments. However, we do have events in our files. This is not maybe the best example, but if we had events in our files that were more behavioral in nature and not necessarily the segmentation for conditions, then it can be helpful in a lot of cases to still see when those things occur during the data set, but not necessarily make a lot of interpretations based upon it. So for example, we have so we have an event here that occurs at essentially 30 seconds, and we actually hover over, see what that event is. But you could imagine that if this were something like a cough or something, we could see if there was any sort of respiratory sinus or a respiratory change at around 30 seconds. We can see what that respiration looks like. We can also see if there's any major deviation in the interval timing here. So I will.
This meeting is being recorded.
But yeah, that's kind of the deal as to why we might want to show this in time mode. Okay, so moving into event mode here. Again, we're looking for, we have a lot of discrete events within our condition. We can actually potentially do analysis twice. So one might be that we're going to do the multi-event, and we're going to say, like in this case, as an example, we're going to change event. I'm going to get rid of all these. And then we're going to come across and we're going to click, drag, and release as to when all these things occur. So let's say that we were going to do this, and then we're going to conduct our analysis on it. So that might be a good way to frame that. Then we can do the analysis for that. We can come back to the screen. We'll make sure our data file is loaded at the top. Again, it just appears up here. It's not quite here yet. And then we could come back to event mode, and we could use other events that would be in here, such as like sneezes, coughs, different things. They touch their face. Maybe this is when mom looked away from baby. All those kinds of different things that we coded in. And then we can look for essentially we can look for anticipatory effects if we're interested in that by setting a negative window before the event occurs, so 30 seconds before, let's say. And then we can also look at some sort of effect because of the event. So let's say that that is 30 seconds afterwards. This can also be used not necessarily just for anticipatory versus reaction, but it can be used, I think, a little bit more commonly as, let's say that black event is just representing all of the events in the table below, but let's say that this was some sort of stimuli that we're interested in, then we could look at the 30 seconds before as the baseline, and then the 30 seconds afterwards as that effect. Now done like this, it's going to include all of that information, which can be helpful to us if we want to see the entire window around it. Actually, okay, well the first one's not a good example because there's no time for it, but let's see here. So yeah, here it is. So this right here is our marker. So we're actually seeing the 30 seconds before and after that occurs and including it together. Of course, like, in this case, we're including all the information before and after, so it's something we want to think through. But if we did want to have a sort of a smaller window that owned around that event, we could do something like the plus and minus 15 seconds, right? That gives us a very smaller window around when that event occurred, and is separate from the initial analysis we did of like the entire condition all at once. So again, this could look a little bit different in that case. If we want to split them into different segments, such that I'm going to share that these are in 6 segments. So I shall leave that off now. So if we want to do this, then what we'll do is we'll get 2 different segments for each, pre and post the event. Of course, this one happened at 0, so there's nothing before that. But so in this case here, we can see that there's this baseline start, and so if we look before that, we actually see that the baseline start is here. So this is 30 seconds for the baseline, and then this is the 30 seconds after the occurs. Then we would have 2 separate columns and rows in our output file that we could actually compare for like change scores essentially between the 2. Okay, so that's it with the sort of pre-post. I'm going to go over to multi-event. This is, I think, maybe the most commonly used event in here, mode when we have events. I saw before, I was just sort of click, drag, and releasing as we move through the protocol. Before I show the sources a little bit more, one nice thing about this is that these events are going to be common or should be common for every participant in your study. Then what you can do is you have it kind of auto sort for you for every participant. There is an error check that comes up letting us know if one is missing or there's a new one in this file that was not present in the other one or not present in our template. So once we have this all set, we have our calibration settings, how we want everything is set up for as like the template or configuration for the study. Or at least let's say this is for mom, and then we have a different calibration settings for previewing this up for child. Then we would come to settings and save that configuration. So then the routine would be, we're going to open up the analysis application, open up the configuration for that study or for that demographic, and then it will automatically sort. It'll try to find the same events and sort them into this table for us. Again, throwing up an error if there's an issue with that. So just something that can be very helpful for you, and instead of having to sort them manually every time. But yeah, from there, I just want to kind of explain this, why there's two different tables here. So this one up here is event sources. So there's a lot of different ways that we can receive events. There's a keyboard presses. We can do norm E prime. It could be, MindWare sending out an event. All of these cases that can be accruing essentially inheriting this different event source. So here I have the MindWare mobile. I have demo events that we could say came in from a stimulus presentation program, and then we have the mobile itself, which is always going to have that first acquisition. And you can imagine if we had another stimulus presentation sending events in, there'd be seen here as another major title here. So we have our main from mobile impedance, and then there would be another one at this level for, let's say, like events from SuperLab or something. So why this is helpful, and then we have another one down here, which is the same as breaking up all of these events that are found within all these parents and children, taking them all out and putting them in this table. So this is nice, it's a visual moving through in a sort of time standpoint method that when all these things occur. And so now what we can do is, you can see in all the different modes, essentially, we have the ability to do event or event source. So that is event being this table over here, event source being this one right here. And so if we were to pull events, this is how before when I have that on, I can actually click diagonally from this area, event source, clear amount, say okay. Then we would be pulling from this one up here. So they're not going to be in the order of time in a lot of cases. It's going to be based off of the title of them. But it's not exactly fun in some cases to go down and find them because it's not in the right time mode. We do have this here to reference to tell us which ones those are in relation to time. But once we do this once, again, we can set a template, and then we shouldn't have to do this a second time. But if we do something like the same method here of the baseline, the start, and then the recovery, which again is going to be a little out of order, but certainly could be handled by a numerical sort of data at the beginning of the title or whatever have you. But let's say we put it through here. The advantage to looking at the event sources, let's say that we save this as a template or we're just loading the next file. It's going to, the analysis application is going to look at the title only of the event and not time. If we pull from the event table here and we're in event mode, those both criteria need to be matched. It's the time of the event and the name need to be identical. So this is not going to occur in a lot of cases where exact millisecond every event is put in there, unless we're in something like Epoch mode. So in a lot of cases, you probably want to be on event source so that these things, when they occur, are allowed to float around a little bit, of course. Once we have those instances, our marcation points of the beginning and end of the condition, for example, there is another thing you can do down here, which is splitting them into multiple segments. So let's say that this baseline here, we can actually see on the table on the left, that's about 2 minutes. And so we actually put, very likely, from what I said before, want to break that up to either 60 or 30-second segments instead of looking at all of the data at once. Okay, I think that's everything I wanted to talk about in sort of a nutshell quickly. Does anybody have any questions on how sorting works? If you want any sort of very pointed, personalized advice on what might be the best for you, we can certainly talk offline or something or now, but any general questions? Okay. Also, if you go over this normally, in Control H, there's a very nice section within the manual that has screenshots and some sort of like key areas, like if I choose this mode, what does it do to the data, things like that. So certainly you can check out if there's any questions you might have. Okay, so focusing on the operational settings, and then we're going to go ahead and start analyzing the data. We already know the calculation mode. We know I can break that down. Respiration cell to use, BNC 0 because we have impedance. Inverted ECG, I'm actually going to cover in a different example, but essentially if we had flipped, let's say, the ECG leads on a mobile device with Raphael, then hopefully we would have caught that and fixed it for the acquisition, but if not, we just click that button, it rectifies everything, makes it positive, and then we're fine. There's no sort of phase shift, there's no data loss, it's okay. It just opens us up for potentially a little bit of error in the analysis if that rater forgets or doesn't notice that it's inverted. So I will show you how to look at that. It is not always easy to detect in some participants, especially when our electrode placement is not perfect, but it can be done certainly. Windowing function. So there's quite a few options here on windowing function. So what this is doing, this is the spectral analysis setting component. So I'm going to jump forward to this routine here, explain a little bit better, and then we'll come back to that. So at this window here, this first series here is just the analog collection of the different QRS complexes, the different heartbeats, and through a couple different algorithms that I have in play here, such as the timing characteristics of them, and the energy envelope. So it's a Shannon energy envelope where it's saying this is what an ECG energy point should look like. We have all these different things at play as to where once this detected those peaks, it's putting these blue circles at the top saying that there's a normal beats and a normal distribution between them. If there is a potential for an artifact, such as movement or a topic beat, very likely that the R peak or the area within it, if it's messy, will be yellow circles. A yellow circle doesn't always mean that we have to make an edit, but it can in some cases. Once we have the time between beats identified with the clue markers, then we have the IBI series chart. So what this is going to do is to actually take in those times and letting us see it at sort of the scale of, on the Y here, we have time between the intervals and the number of intervals there. So if there was an event that took more time than the previous one, such as this here, if we look actually straight up, we can actually see that there is more time involved with this interval right here than the previous ones. And so it's going up because there's more time between them. If there's a shift downwards, such as one interval is less than the other, that's interpreted as a down mark there. So we don't normally need to look at the IBI screen to make any sort of interpretations based on it. But there are some cases if we get a little bit tired and we've been editing data for a few hours, and some people have been doing that here. Let's say that one interval, let's say that the software made a mistake or there's some motion artifact or what have you, and there's an artifact at right at the beginning of the segment, you just kind of miss it because, you're about to bleed from doing all the analysis. Then this IBI series chart can sometimes help you identify that sort of mistake that you failed to identify, which can also be really helpful if it's just one little extra beat that could be within the segment. So I'm going to go ahead and just add an extra one at a sort of random point here. And then once again, we can kind of see that everything's auto scaled, but then we have some sort of deviation there that we want to look a bit closer. Okay, so once we have that data, and we have our RBI series chart here, then we can see here that these data are interpolated, detrended, and resampled at a much higher rate, so that we have the actual time between those cardiac cycles. And the reason why this is done and why we don't submit just the IBI series chart to the Fourier transform is because you're going to see a lot of jagged sort of points in here between the time where we really don't want. The Fourier transform is going to take a time to a signal. It's going to pass it through and break it up into its spectral components. So another easy way to kind of interpret this is a white light going through a prism, and then kind of see the color spectrum that makes up that light. And so anyways, when we're doing such a thing, one of the postulates of the Fourier transform is that it must be a continuous signal. So any time in between that signal is going to be seen as noise that's ejected into the file at some random frequency. So to do this, something that's kind of helpful to think about, it's not exactly how it works, but we're going to take the first point here, and we're going to take the last one, and we're actually going to, if it was a string, we're going to like kind of connect them to each other so that we have a continuous signal. And we're going to taper that off so that it has a minimal effect to actual data. And so the actual tapering window that we're going to be used is sort of that previous calibration string. So as far as the windowing function that we want to use, typically in almost all cases for human ECG collection, when we're doing high frequency heart variability, is to use the Hamming filter. The sort of very, very close alternative is the Hamming filter. As far as looking at a normal distribution here, so the Hamming is going to be have a little bit more breadth and information at the very ends, sort of bookends of that filtering. Essentially letting more high frequency information in, which is what we want for RSA analysis, for example. The Hamming is going to be very similar, but it's going to have a sharper attenuation at the end there. So it's going to be a little bit higher in the low frequency spectrum, but a little bit more steeper, closer on that high frequency, which is what we don't want. So there are some other algorithms here that can come into play that are helpful, other ones in the literature which you can choose, but if you don't have a really good reason to change it, I would make sure you're on Hamming with an M. Okay, so just to finish up the sort of data processing, how this is going to do the application. So we have the time series data, we have time pass the X here, and then we pass it through a Fourier transform, just pretend this line here, and then we have broken these time series data into their spectral components. So the different power and frequencies that we see as the area under this curve are made up by different oscillation changes in the heart rhythm, if you will. So very, very fast changes that might occur, such as this one, are going to be seen as in the higher frequency range. Very slow changes that we see, such as this architecture here, would be represented in this lower frequency range. That makes sense. So anyways, once you do that, the reason why we're doing this is because physiologically, as I talked about yesterday, the sort of activation rate for the parasympathetic and sympathetic are different. So on the heart, at least, the vagus nerve will essentially be collected from the acetylcholine in the brain, and they'll actually dump acetylcholine onto the synovial node, changing its pace or its rhythm. This is a very fast myelinated connection, so it happens on the order of just a couple hundred milliseconds. And as far as sympathetically, we do start with acetylcholine by the sympathetic chain ganglia. Then we do have to make a chemical transition over to epinephrine and norepinephrine. So that takes time, literally, and to get it done. And that's why we know that the sympathetic nervous system can't operate at a higher frequency. It must be any sort of activation or power there must be due to the vagal activation. So that's kind of why we're doing it here, because we can isolate the power in that higher frequency spectrum, and we can say that the area under this is, again, just due to parasympathetic activation or activity. The lower frequencies here, so essentially the very low frequency between these blue lines represent these statistics here. There's a white line under, subseated essentially under this blue, but from this line to this one here is the lower frequency spectrum, and then the higher frequency spectrum, again, yellow being underneath us, from here to here. So, yeah, as far as use application of these different ones, the high frequency spectrum, that's going to be the log transform in milliseconds squared, or the RSA is here. And the lower frequencies, the very low and lower frequency spectrums are not commonly used. They're not usually of that much use because the power into that is slower, and we can actually see that the sympathetic nervous system does have the ability to change heart rate at those lower frequencies. So, and we don't know how much of each. It's kind of, as we think right now, impossible to tear them apart or differentiate them, I mean. And so, yeah, they're usually not super commonly reported or used in any way. There are two reasons why you might want to use some of them, though. So the low frequency band here, there is a sort of idea here and such that there is some bioreceptor activation that can be present by sort of changes in lower frequency spectrum. It's called the Mayer wave, M-A-Y-E-R. So if you wanted to look into that, you can report as essentially in that lower frequency spectrum as potential correlates to bioreceptor activation. Normally, I would only recommend this when we have a continuous blood pressure monitor, which can actually see the BRS series and those changes at a very small, like millimeters of mercury over like 5 millisecond kind of range. But regardless, this is something that can be done at spectrum. The very low frequency spectrum is very rarely researched. It doesn't have a lot out there, but there are some correlates to temperature regulation within that spectrum. So, but by and large, what we're very interested in is the high frequency RSI band. So the high frequency heart rate variability, again, is the tool that we use to observe the phenomenon, which is RSA. They are not the same thing. So right now, how we have this set is from 0.12 to 0.4. This is the settings that we would recommend for resident adults. If we are going to be looking at child data, then we need to very likely change these settings to account for the fact that they have a higher heart rate and a faster respiration rate. So we have the general recommendations. There's a guide within the, there's an article within the HRV training guide in our main support site called Modifying the High Frequency Band Settings, written by yours truly. And in there, essentially, we're suggesting a 0.24 as the lower band here, up to a 1.04 as the higher. And you can see here as well when we change that over to, let's say that we were looking at the child data. What it does is also change the respiration min and max that we would be expecting for that population. So it's based on a 60-second 1 minute cycle here. So if you actually multiply 0.24 by 60, you get the 14.4 and the 1.04 to the 62. So that's the range at which we would expect the child or sort of allowed to be within. Sort of difference between the two, and then it's 7.22. And also forget what it is for the normal. 24 if we have those normal settings. When we do change it, if we wanted to, again, for something like the child data, we do want to make sure that we don't have any gap in between the different band settings. So if this is 0.24, then we want to come back and make sure that this one right here also says 0.24, so we're not missing anything in between. Okay, so I'm going to change it back to health settings here. That's how that works. I'm going to actually touch 2 more things here, and then we're going to jump to data editing. So as far as the artifact settings, most of the screen you can just leave it as is on those things, unless you have good reason to change them. But a couple of algorithms that you are allowed to actually modify here are the IVI min-max check and the MAD-med. So the IVI min-max check is literally looking at this table over here and saying if we ever have a participant where their heart rate falls below 40 or exceeds 200, then we're going to want to throw up a flag. Hopefully, if it's anywhere above like 140 of your participants and they're an adult, we will probably very visibly notice that we should stop the protocol. But yeah, anyways, you can set this range as you'd like right there. But this is sort of a normal standard. And then the MAD-med is a medium artifact deviation, maximum expected deviation. So this is an algorithm that actually looks within the IVI and then for surrounding intervals as well. So it's looking for things such as if there was an artifact, we have identified an RP, there's an artifact that precedes or follows it. Is it even physiologically possible for another RP to have occurred there? If not, then we can automatically say that that's not an RP and not mark it as an artifact essentially, or erroneously as an RP. And anyways, you can certainly read more about it on normal days by hitting Control H over that. But something that we would recommend just kind of leaving it out at all times. The baseline of noise filter is going to remove any sort of electrical contraction from muscle noise, activation, and also baseline muscle movement. What it's doing is essentially applying a band pass filter from 0.25 to 40 hertz. This is that frequency range at which we expect human ECG to be offsetting in the frequency domain. So it is allowing data through a filter and attenuating, but not deleting or anything, the data outside that range. Normally you can leave this on unless, of course, you're looking at potentially a different species or something. So the notch filter, this is if we had that 60 hertz noise in our data, we have a very thick band of interference, then we can essentially just apply this filter and remove it. 60 hertz being data collected in North America, and then the rest of the world is going to be at 50 hertz. Okay, so going into the actual analysis now. So we've kind of walked through the ECG data all the way to the power spectrum. Another thing on here is the respiration time series. So how we would interpret this in most cases, and this is looking at quite a bit of data here. This is 2 minutes, but it's fine. So we don't really need to make any interpretations on the respiration unless there's like some sort of drop off, like a gap or something. Of course, if we see something like that, then we'll want to inspect that quite a bit closer and even think about breaking those segments up because, yeah, that could be something like an impedance lecture that came off or something, right? And then you're not going to have respiration data. We don't want to include that as some sort of random noise in your frequency splatter. So you want to keep an eye on it at that level. Also, this is the reason why breaking it up is a little bit easier on us in some cases here, because we don't have so much respiration data to look through. But the other thing we might be looking at is focusing on the respiration rate up here. So how we actually detect the respiration rate is we're going to pass the time series data through the Fourier transform. We're going to look for the peak frequency or the highest, tallest frequency within this entire range. And we're going to use that as identification for the average rate of respiration. In doing quite a bit of different research and digging into how to extract the respiration rate, it turns out that something like counting these or having an algorithm that does it is pretty inaccurate because there are a lot of sort of subjective decisions that need to be made on respirations that are not complete. They're, something like I'm talking or something, I'm taking a full inspiration exhalation. So what do we actually do with this? Is this 1? Is it 2? So a better way to look at this is actually the power underneath that entire time, which we can see here. I mean, here's the majority of their breathing pattern, with this being the most powerful. So we're going to take that peak frequency and actually create the respiration rate sort of backwards from that area. So the other reason why I'm looking at this, besides the dropout, would be, does this number, let's say 14, make sense with this plus or minus 10? Like, is it in that range? I can say immediately yes, like it seems like it's in that range. I can count if I wanted to, but let's just not, because it's a waste of our time. But if it were something like, if it says 60 and we see this, then that's a better reason to look at that a little bit closer. But other than that, mostly what we're going to be doing is we're going to be focusing on the respiration power spectrum here. And this is the very first thing I do as soon as I open a file in a segment, and for every segment, is focus on the respiration. Because if we're looking to report on RSA, that's what we need to do. Because we need to validate the RSA measure from the respiration. We need to actually say that they were breathing within the normative range, while we're actually looking at that same range above for the area in the curve for that parasite activity. There is a way in which if we don't breathe or breathe very slow or hyperventilate, essentially, we can invalidate the RSA measure. So we need to be breathing within that range. So if this tallest peak here that we see is either to the left of that sort of lower component here, which has to be 0.12 in this case, or if it's above that, then very likely we want to discard that segment because they were breathing that normally. One thing that can occur is that if we set the wrong frequency settings completely, is that we can see something like a respiration frequency information that's off to the right, it's not on the screen for us. So what we can do is, if you're ever in question of that, such as like you see there's 60 respiratory time series respirations, but we're only in this 0.2 frequency, which really would be more indicative of like a respiration rate of 13, then what you can do is you can take this hand tool here, and you can actually click and drag, and you can go something to like up to 1 is perfectly fine. And you can see here there's like almost no activation after right here at about 0.5 hertz. So just if you're ever in question about it, if something doesn't look right with the respiratory time series to the rate, this is something you can do pretty quickly, but normally not necessary. So we've opened the file and we've ensured that the peak frequency is between those two marcation points here, and then we can go ahead and look at it a little bit closer. So in the series that we see at the top here, everything has a blue circle on it. When we're first getting started with editing data, I would recommend that you always hit the edit R's and look at this a little bit closer. So we have the tools at the bottom here. This first one that's always selected natively. It allows us to actually move the X and the Y cursors around, and you'll see that change up here in the cursor section of the X or Y cursors. The high and low is just whichever one is to the left, right, up or down relative to the other. So for example, you see this one is changing the high amplitude, and this one is changing the low. But if I move this low above it, then this one becomes the high cursor. And same to the left and right. So this is now the higher X cursor, changing that high value. This is below, but of course when I went to the right, it was high. So just so you don't get confused about that, we'll go over why you would use these tools in a second, but that's what that function down there does. Within the zooming windows, there's a couple of different options that we have available to us. As far as like your normal day-to-day, what you're probably going to use is this middle one here. So if we're looking at the entire second window, which you are right now, we can click on that one. We can click, drag, and release around a specific area that we're interested in. They'll zoom in and we can look at that a little bit closer. Yeah, the other thing that you're probably going to use besides that one is this one right here. Click on that, it'll jump us all the way back out. There are some applications for these other zooming windows, but we'll do a bit later. But the other options here are also be able to click in every time I do that, and then we can also zoom out every time there's a button click as well. With these two, I don't usually use that too much because, especially with ECG data, you always want to see the entire amplitude range. If you zoom in too much, let's say we use this top left window to do something like this, well, we get peaks, but now we're missing the bottom. We have to like scroll up and down. It's kind of messy. So that's why this top middle window is a little bit better because we can, no matter how much we zoom in, we can always see the amplitude range. Okay. So anyways, and last tool down here is the ability to click, drag, and move through the data. So this is an option once you zoom in. In the new analysis, we actually have, I think, a better way to move through the data sets. So once we use that first zoom tool, we can actually use the left and right arrows in the keypad to move through the data in 1 second intervals. This keeps our actual y-axis constant as we move through the data set. So that's usually a better method to get that done. Okay, so then as far as these features in here, that I'll highlight. So once we're in the window, we can actually save or save as within that window. So if there's maybe we're in question or multiple ways we want to add the data, see how they change, we could use the save as function. Saving this window is not necessary exactly. We can, when we click exit, it's going to ask us to save that file, or once we hit done or exit at the actual end of our analysis section, it's going to say, hey, there were edits made, do you want to save that file? So if you say, yes, I want to save at that point, then you don't have to go through and hit file save within every segment, but if you want to, you can. Also with the editor, we can undo and redo all. You can see the hotkey functions there, which is helpful. If you leave this window, let's say we do some sort of edit and we leave this window, you can't then go back into it and hit undo or redo. So if you really didn't want to use that information, we'll want to probably hit done, save the edits or not, probably not in that case, come back in and then do the edit correctly. So if that's happening to you very frequently, then that might be a reason as to why you might want to save the individual segments as soon as you made an edit, for example. Viewing data, so there's point distribution and data edits. So data edits, I don't really have too much of a proper use for in this application, but if we wanted to, we can actually come in here and say that we're going to remove some of the data because it's like, let's say, message, for instance. And so we can actually come in here and actually say that we're going to remove that data. Now, while this is okay as far as the algorithms are considered, when it's doing analysis, it's only using point to point. So what it's looking at is from this point right here, about 39 seconds, all the way to 90. That's where the analysis is being done from. And we've removed that first section, which maybe that's what we're going to do. The problem is that if we were ever wanting to look at this data again and show like, why did we make that edit? Why did we remove it? It's impossible to say from our edit file. So, unless we're trying to hide something really badly because we can always go back to raw data, this would be not a great decision, especially if we're like a sort of, inexperienced data coder. We have experience, a sort of research coordinator, if you will, looking over edits, making spot checks, or potentially even editing the same data set, or, a sort of interclass correlation coefficient, make sure everyone's editing the same way. This becomes very difficult for that person to look at afterwards. So, in most cases, what I would recommend is that you just stay away from the data editing column here, at least in this application. If we wanted to actually remove some data, let's say from one of the ends or making some other decisions, I would recommend staying in the point editing realm here. But before we go there, the reason why I kind of jumped to that is the data edits that you can see here for the reverse window. When I actually remove them, we'll do the data edits. So you can see here, this will actually say how much percentage and how many seconds I've removed. So that can be helpful again if we're removing data, but I would again normally recommend doing that. It can be helpful to make sure we still have 30 seconds, I guess, but there's I think still a better way. So I'm gonna go to the next segment, and we can look at that. So within the actual point editing realm here, we have the ability to insert, delete for just some single points, and then we have the ability to do the same things between the cursors, the X and Y. So let's say that we wanted to remove the first few seconds of data because they were messy, for example. We can move our X cursors around that range, and we can say delete everything in there. We can also do something in this where we set the one cursor there, and create a file over here. If I do Control plus Shift, because I have both, it's a little more efficient way to get rid of the data on both sides. So once we do something like this, whether it's on one side or both, I would recommend you come in here, set the X cursor about wherever that R peak is. Don't try and get perfect with it. And then once we have that, the delta times that we see up here are the absolute time between the two. So we have 48 seconds. We know we're over 30, and keep the 7. As far as the why we might use that one, the Y cursor, insert and delete. So I'm going to actually create some noise here. And so there's some artifacts down there, and we know we don't want that because we can see all our artifacts at the top, but there's just some low level noise that's being picked up by the algorithms. And so what we can do is we can actually create our Y cursors. We can actually move our Y cursors around that range. Oh, my answer's still on. Okay, there we go. So we can move our Y cursors around that range, looking all the way down to make sure they're all kind of encapsulated there, and then we can kind of delete them all at once. So that makes it a little bit faster than coming here with a delete and this window and having to manually go through and with these points. Also inserting, like if we ever came to analysis window and for some very weird reason, the analysis algorithms have failed to just put peaks on some of those ones that we've identified as good beats, we can use the insert function with the snap to peak on. It gives us this little window in which we can say that we need to find the tallest point within that circle and place the peak there. If we were to do this manually by turning snap to peak off, I can get pretty close to this point here, and it will make it look good visually, but if we actually zoom in, you're almost never going to be able to get it at the exact point. You just keep doing this forever, and you're going to be a little bit off. So normally we recommend that snap to peak.
You can vary the size of the circle to be more precise.
Exactly, yeah. So once I turn that on, there's a sensitivity setting here. It's also my trackpad, which isn't as friendly, of course, on a laptop, but the mouse cursor wheel will also adjust this. So but once I do that insert, we can see have a more specific kind of window here. If we're sure there's nothing else around it, we could, make our window a little bit bigger, make it easier on us, but it'll find the tallest point and it's right there for us. In some protocols, if there's ever a beat missing or it seems ambiguous in any way, what some labs will do is actually have an estimation of where that occurred because we're not completely confident in it. It will place it at that point, which we believe is the correct location for that R peak. But what it'll also do is it'll change our other data viewing components. So this is where I would think you're normally going to live, is in the point distribution settings. So if we change that, at the bottom right now, we can actually see we have a couple different bins here. The blue being the normal beats that have been detected, yellow being potential artifacts. So we have 5 throughout the set here. and then the orange being the estimated beats, or they're sort of extrapolated bid beats, if you will. And so, yeah, as far as those potential artifacts or estimated beats, if we estimate them there, then on the next screen here, we'll change this over to distribution. We have that one estimated beat now, and that's being seen here. So we have a couple different roles available, and I'll cover them all in just a second, but this being one of them that we're going to focus on just a second. The last thing to look at is just mid-beating, so we'll go over that, and then we're kind of ready to move on to the data, edit that, and then move on to the next application. But for now, let's say that I want to zoom into a specific area, and for some reason, let's say that there's a couple of samples missing. Hopefully it's not that they are having some sort of cart blockage or anything like that. But we can go ahead and just kind of take this for now and just remove these data. So let's just say that this occurs, and more likely, hopefully, it's just like messy, jagged lines from them creating motion artifact. But regardless, what we can do is you can put cursors into two surrounding intervals that we know are good beats. So we're going to do that by qualifying the two before it. So PQRST, PQRST looks good, and then doing the same with these over here. Once we have that there, we can now move these cursors into the surrounding intervals. So anywhere in here, anywhere in here, it'll detect based off the distribution of the interbeat intervals for this participant within the segment that how many beats are missing within that range. So this detected that 3 are missing, and we can now hit the mid-beat function. That's going to place these mid-beats at the 0 amplitude because we don't know what the amplitude is, and it really doesn't matter. All we're concerned about is the time between them. And it's going to put it into evenly distributed intervals, again, based off of average 2 is based off of their normal IBI timing. And so this is the sort of proper procedure so that we can have that continuous stream of data, again, at least 30 seconds or more. Now, as far as doing this, and the additional kind of layer of that role is we want to make sure that we do not estimate more than 3 beats in a row. And that comes into play just because the respiration changed as well. So we're reducing the amount of data points, right? Because this is sort of artificially placed beats on where we believe they're going to occur. And it's probably very close, but in addition to that sort of actual data loss that we're doing with that is when we remove that beat, the 3 or more, what we can do is we can start to remove an entire respiratory cycle. So if what we're doing is validating an RSA by respiration, and let's say that they were very close, something like the respiration, let's just say, was down to 8 breaths per cycle, and for resistant adults, we need to be 7.2 to 24. So if we remove the effects on the ECG, on the heart rate due to the respiration by doing too many mid beats, then all of a sudden we really have one less respiration there. So now we're at 7 instead of 8. We're below the range that we should be at. And we don't have enough changes again in heart rate due to breathing. So, for example, if I wanted to get rid of these 3 here, it's nicer to see with the respiration overlaid. We can actually I'll do one more, of course, 3 to 4. So then what we can do is we can put these cursors along here, and it's estimated that 4 are missing, which is correct. But if you look at the respiration compared to that, I've really removed the entire phase of respiration by doing so many estimated beats. So it's no longer paying attention to these timing, it is these ones down here. And they're very, very close, of course, because it's using the normal distribution for the area around this event, but it's not perfect, and milliseconds matter. So again, try to do 3 or less if possible. So going over the rules and sort of 1, 2, 3. So we need at least 30 seconds of continuous data within a segment. We want to try to estimate or interpolate the amount of beats, so just how many of these occur at less than 10%. So we're already at 15.4 here because it estimated a lot. This can be somewhat flexible. There's really not a way in which I would ever report how many beats I've estimated necessarily. But just internally, you do want to have a lot of scientific rigor, if you will, and so 10% is normally a good amount or less to be able to extrapolate and still have a good assessment on a person's RSA. if we are dealing with very messy data, like people on treadmill, children, free playing and stuff like that, we're gonna probably have to expand that window a little bit to use any of the data. So in those cases, something up to about 20% is sometimes acceptable, but it's a little bit of a sort of risky landscape there because we are essentially putting in the extrapolated information. So take that with a grain of salt there. Hopefully you can stay under 10% ideally, especially with like resting state adults that are moving around a ton, you should be able to stay below like 3 or something. So anyways, the 30-second continuous data, estimating less than 10%, and then do not do more than frame around. Last thing is just, it kind of follows with this measure, but then also our others. And within a segment, if we needed to remove data, so we're actually going to remove the beats that we didn't want by actually hovering over them and saying that we're going to just delete the R peaks. So again, this leaves the actual ECG there if we need to validate it later or verify it later, but it only starts the analysis on the peak, if you remember before. So if we needed to do something like that, then what we're going to try to do is keep at least 60% of the data within that segment. And that's very aggressive to remove it up to 40% of your segment, but in some cases you might have to do that. But I would strongly suggest you don't go beyond that bound of 60%. So this would follow within a segment and then for a condition, mathematically, which would include both. So if we're doing this, and let's say that due to respiration, this one's close because we do have some activity here with the highest frequencies here, so we're okay. When I do see something like this and it's actually bleeding off into the higher frequency, I would certainly look a little bit closer to make sure up to about 1 hertz that nothing is there. But it's fine. It's still the highest frequency is within that band. But let's just say that the highest frequency is outside of it, either low or higher, or there's just so many issues within the actual data that we need to remove more than 40% of the data. That's when I'd actually drop the segment. And so if we imagine that there's like a 5-minute segment such as this, we could get rid of 2 of those, up to 2 of those, and still have 60% of our data remaining. Again, that would be the highest I would want, but hopefully you can follow with that. Okay, any questions with this so far? That's kind of meat and potatoes of everything. So now we can kind of move into some messier data and ectopic files, which are a little bit more meaningful, I guess.
I wanted to know, so I think one thing you were talking about earlier, and this has more to do with like respiration. So I know we want to have the respiration, like peak of the respiration power, and that within that high frequency range, right?
Yeah, right.
But then we were starting to talk about respiration rate. And I think that's that part I got a little bit confused about when you're looking at it and sort of how we can use that as well as respiration time series to sort of keep an eye out for anything that might be like an artifact or something like that. Would you be able to explain that a little bit?
Sure. I might repeat myself a little bit, so just to let you know if you need a different explanation for me to say louder. But let's go to a normal sector. So when we're looking at something like this, so any sort of like slow kind of changes in respirations, these here that you see, those are going to put power into a lower frequency area here. Any sort of fast little changes that we see here are going to be in the higher frequency range. So when we're looking at the time series here, the only 2 decisions I'm making based upon that are if I see a dropout. So it actually goes from something like this area and down to a different range. So not like it's sloping down, it's a straight line down. Like it says just like an electrode came off if we're driving from impedance, or the belt came off altogether. You're going to see that complete drop off straight down. And in those cases, then I'm going to start to ask questions about the respiration. So if it's impedance, let's crack open the impedance application, see what that data looks like around there. But in those cases where there's a complete loss of it, we probably want to think about just removing a segment because you don't know what happened there. So there's that one thing. It's pretty rare. Hopefully your sensors are just coming off. The other thing is when we're looking at, so we open the file or the segment, we focus on this first to make sure they're breathing correctly. We see the highest peak is within there. That's that peak that's being used up here. So 0.3 0.3492. This is right here. And so once we've detected that peak on a 1 minute cycle, we can multiply 60 and we can actually get that respiration rate from there. And so that rate there is the rate that is cumulative of this, and it's very accurate. You can go ahead and test that. You can count if you want to. It's sometimes, again, difficult to count, but this one's probably doable. I don't know what that is, but and you'll get very, very close to that point. And this has been found to like much more accurate than having some algorithm actually counting there, because if I'm talking, you're going to see things like this, where it's not this very defined like breath I'm taking, right? It's just like partial breaths, and I'm talking so fast that it's probably just like this straight line or something for me. But that's the kind of thing that I'm looking at within the time series. After we kind of look at that, which if you get experience should just take you like 2 seconds. All right, you're checking that, looking at the rate. Does this rate make sense with what we see here, plus or minus 10, which is really pretty fast? Like, does this look like 30 to 10 respirations? I would say yes, it's within that range. Then I don't have to necessarily move this frequency over and see if there's some information that I'm missing. So, I hate you, Zoom. I know there's a way to get rid of it, but then we'll need it back, I know. So what we can do when that doesn't make sense, when this rate doesn't make sense, what we see over here, we can take this hand tool, move over here and up to about 1 hertz, see if there's any activity there. Because it's certainly possible that if we're seeing that like this is saying 20, but we see like at least like 60 different oscillations over here, that's could be what's happening. And so just go in there to make sure that there's not like a much higher powerful peak and a higher frequency. But again, only doing that in the instance in which this rate does not match this, and sort of plus or minus 10, if you will. Yeah, and then I guess just to continue that a little bit more, reset this to range. So if there's the tallest peak and it falls to the right or higher than 0.4 for assisted adults, or it falls below this, lower than 0.12, then that's usually a good reason why we want to drop this segment, because they're just hypo or hyperventilating, which could again invalidate our segment.
Oh,
is that helpful?
That's very clear.
Okay, good. Okay, all right, so now I guess we'll move into a messy file here, and we'll take a little break before we get started on the other two. The other waveforms, as far as the sympathetic markers, impedance and conductance, there is a lot less regulation on how you edit the data, so that can either be relieving or very stressful, because now we don't have a lot of guidance on this. We do have some general framework recommendations on it, but because of the lack of rules and regulation, it's quite easier to edit in a lot of cases, so it doesn't take quite as long. But anyways, I'm going to go ahead and open up some of the other data files I have prepared here. And of course, you will get these to look at yourself. Okay, so the first thing, I have 2 subjects in this file. So this is again why we have this channel mapping screen, why we have it is because we're going to edit 1 person at a time. You can see there are 2 people within here, and for some reason there's another random subject with conductance, of course, but hopefully you don't have too many of those. And in this case, we have respiration. Now, if you're having respiration belts and impedance, like let's do a better job with the labels in BioLab, but this can also be obvious to us, I guess. So in this case, we do not have impedance, so ECG and then respiration, such as it's a respiration belt. This is that warning that I talked about before. So I had loaded that file before that had the baseline start, baseline end, recoveries, all those things. They're not here, they're missing. And so this is letting us know that they're missing, or that there are extra ones in here that weren't previous. So this is that error check for you to let you know. And again, if we had sessions for a protocol in which all the participants are receiving the same events, maybe they flow time a little bit, but the name should be the same, then having that event source is a little bit better, because you won't get this error every single time. As long as there is an event that says baseline start and everybody, it'll find that and it'll sort it for you in that multi-event table automatically. Okay, but let's just go ahead and stay in time domain mode now, and we will go ahead and try to edit some of these data. So first things first, you see we have an artifact potentially. Let's not just jump there, but we can also see that there's different inflection change in the IVI. So this little sort of tension grabbing as well. If we fail to see that, you have little circles up there. So before we do anything, again, let's focus on respiration because especially if we're looking to report on RSA, if respiration is wonky out of bounds, then why even waste your time trying to edit the data set? So respiration looks good. It's within that bounds. So we could go in and we could try to fix that right now, but I think a better approach would be that, okay, so we see something abnormal. We can zoom in really quick to look at this. But, there's a different structure, which should be hopefully, somewhat clear to everybody, especially as you start doing this a little bit more. But if we understand the sort of PQRST and just the morphology of the normal QRS, this should look quite a bit different to us. So there doesn't really seem to be a P wave there. So this could be something such as premature atrial contraction. There also is quite a difference here with the architecture, such as like this, the amplitude. Now, I said before, we don't really care about the amplitude, but it's notable here, right? Like, as far as this normal range here, it's quite a bit lower, so it's another identifier for us. The breadth or the width of the actual Q to S points here is quite a bit wider than we would expect for the other beats. And then also this T wave, if that's what that is, it looks completely different than the other ones that we're seeing, the surrounding beats. So there's a lot going on here. It could be a combination of different sort of premature or junctional contraction issues. But regardless, we don't need to get a template. We don't need to get the clinical ECG book and verify this. It's not a 12-bead clinical, ECG question, so we didn't even verify anything at this level. But we can't see those things. It's just that we don't really want to get caught up or down the rabbit hole of like seeing which one it is. And you telling somebody that because we took a lead 2 configuration that they should go see their cardiologist because they have an arrhythmia. Like, let's not even go that route. There is a kind of intersection between ethics and your IRB, and so I'll kind of leave that up to you on what you're going to do with that information, but that's my official stance. But anyways, so we have identified what is probably a normal beat. We have the circles, we have our different information I just identified to you, and we want to get rid of that likely. But the thing would be, if this occurred once, we might want to think that it occurred more than once. So before we go into this first segment, start making edits, let's see if this keeps happening. Like, how bad does it get for the rest of the segment? Because if it happens too many times, and we have to, do these mid beats and these estimations, we start violating our 10%, then we just have to throw out the entire participant regardless. So in a sort of efficiency stage, let's just take that first step back and see how messy this gets. And really, that's a good approach regardless. Even if we pack it open, the first segment looks good, let's just kind of make sure through even some random or quite random checks throughout the segments that most of it looks decent to us. In this case, there's only 5, or sorry, there's way more than this, but regardless, this is not a ton, 38 to look through. We can stay on the screen, just like when we're in the edit Rs, we can actually hit the arrow button to move through these, which we can do pretty quickly. Another thing that we can do is we can do the search, find the next artifact, and that's like control right, as you saw as a hotkey. So if I do that, I can, every time that there is an artifact detected, I can jump to those segments to see how many of those are occurring. There's also the find previous. So let's say that we're completely done with the analysis for this participant at 38 here, and we're about to complete our session. One last check you could do would be to find any previous artifacts and just make sure we didn't miss anything. Another approach here, which I did show yesterday, is before we do anything with a participant, especially if it's just, for the study, we're like, okay, they're all messy, like it's these kids doing free play, like we're just expecting a lot of artifacts, but we want to upfront say, how messy are these data and how long is this going to take me to even inspect? So a question like that. So when we first crack it open, something we could do is we could go to file and we could just say, write all the segments out. So it's not going to make any edits or interpretations. It's just really going to write them all out. So we're going to have to sit here just for a second while I go through this, but I'm going to selfishly use that stream button. I think I got slower at the end, right? teasing us. Okay, so we can open up our folder that had these examples in there. And I was on the first one. It created the output file when I hit write all. And one thing of note that actually brought up to me earlier. So when we have a file open, in addition to the MWX raw data and the MWI index file, while it's open, we'll see that there's some other files. It's SHM and WAL. These are temporary files. They're really the ability for the index file to communicate with the MWX and extract that information from it. As soon as we load a different file or close editing analysis, those will disappear. So they're really not something we need to pay attention to. If your computer crashes, Windows crashes, power is out, or something while we have a file loaded, again, what could happen is the MWI file, the one that got actively loaded, could become corrupt. It's also the case that you might have the SHM and WAL always there. They weren't removed. And in that case, you can certainly delete the WAL and SHM. There's no problem with it. And you could even go the first step of like, I'm just going to delete the MWI as well, recreate it from WX and start over. So just so everyone's aware there, but we still have it open. So, but I'm going to look at the output data, and I'm going to crack open this Excel file to show you that method I'm talking about. So in here, we have our HRV stats. The very, well, second to last book here is our editing stats. So if we actually focus here on the artifacts and the percent of artifacts here, we can essentially look at this in a sort of a heat map fashion if we wanted to, with some conditional formatting. But essentially here, you can see that we start to get a lot of artifacts in this range. So if this is something like 80–90% artifacts throughout an entire condition, I mean, just automatically I know we can't use it, right? So in this sense, though, we can see like, okay, like you'll get a gauge, like how fast am I cleaning data? And then when there's 10% artifacts or something within a segment, how long does that take me? And you can just kind of get a feeling for it, if you will, on how long it may take you to look at those sections. As far as honing in on them to see what that looks like, I think the previous example of being in the analysis application and just using the find next and previous artifact is probably a little bit more efficient. But does that make sense to everyone? Like kind of what we're doing there? Okay. But we'll all have perfect data that doesn't have any messy noise, so just no problem with it. But okay, so jumping back to this section here, now that we know about some other tools, we are going to hit the editors. We're going to zoom in to that area to look for any abnormalities. And I'm sorry, we would also, and we kind of talked about this, but I would do some checking throughout the entire data set to see if that issue continues to occur. And it looks like it does. It looks like this is kind of repetitive for them, which is going to be very common. If you have PDC, you're probably having them somewhat seemingly spontaneously occur all the time. And we can see that sort of this just continues to happen for them. So not sort of exclusion criteria at this point. I mean, we can let the estimated beats, if that stays below 10, we can let that guide us on how many is acceptable. However, there is, again, an event that occurs right now, like we send a startle probe, and then right in the middle of that, we're having all this PVC, like that's probably a problem, right? So it's not just across the board that we can put a mid-beat in. If that's the area that we really need to know about, then that's probably the sort of reason why we have to drop that participant. So use it as a kind of a guide, but there are certain different contexts in which that would be appropriate. But okay, so we've done all that stuff. We come back to the first section. We see that we have a potential artifact. Let's go into it. One thing is, let's not jump right to the issue. So because we know this person has some sort of premature or junctional contraction issues, this might be repetitive. It also might be the case that the analysis made a mistake. It put a peak on what isn't an actual R peak. And so when I see something like this, or I'm just dealing with someone that has these issues, I know about it, start from the beginning, create something, I like a 10-second window, move through the data, and get eyes on every single beat, make sure it's there. This is also a procedure I would recommend to anybody that's first getting started. Like if you're not used to seeing these things, an artifact that's turned blue, it's probably not going to be obvious to you in any way. So going through, even when everything looks blue, and using this window here to click, drag, and release, something like, again, just my personal preference is about 10 seconds, and then moving through, training our eyes on the peaks, making sure that those blue marks are there, but then also taking a quick glance down to the PQRST components to make sure those are all present as well. Now, sometimes there's going to be some ambiguous, like sort of motion artifacts or potential different conductance changes. that you might see in here. So it's not always like you're going to get these perfect signals, but you know, if something is like completely missing or something in that instance, then it should be a little bit more obvious to you. So anyways, sort of training my eyes again on the sort of blue spots there, and then as I'm going along, kind of also looking at the bottom components to make sure they're present. So when you get really good, you can usually use this at a much faster speed here. And so just going through, it takes us a couple of different seconds, I'm sorry, a couple more seconds, and then we can arrive at our original issue. So I'm actually going to turn off respiration for now because it's sort of in the way. So I'm going to click up here on it and hide it. If we're trying to make edits to the ECG signal and you can't, it's just not working. It could be the case that you are on view only, so then I can't do any sort of changes. So just kind of make sure that it's always just on edit. And I'm really saving you and us from that support kind of issue, so probably that. Okay, so anyways, so we've arrived at the issue, and so what I would do here, you know, if this isn't sort of obvious as what to do, we can sort of say like, okay, like if this is more ambiguous, like it looks close, but it's early or something, then we can set the timing window for, again, 2 intervals before that occurs, and we can get an idea of the interval around that area. Of course, we could change this up in a couple hundred milliseconds, so it's not this perfect science, but it can help us with a general investigation as to where that RP should have occurred without the event. So you can see here, there's still very minimal change between those intervals. And then if we keep walking this over, we can see that if this had this heartbeat had been affected correctly, that we would probably expect that RP to be somewhere around that time. In addition to this, what I would say as another security blanket is going from the left to the right to the left, and sort of getting some sort of agreement that making sure there wasn't some sort of dramatic change, some sort of reset in the rhythm that occurred at that time, and then we can kind of know that there's difference. Now, in this example, it seems, at least to me, pretty clear that there's a sort of copy beat. I don't have to do this timing window stuff, but again, as you're getting started, or if there's more ambiguous, something can be helpful. Other than that, what we would normally do is we're just going to move our X cursors into these good intervals, starting it, again, good being 2 QRST before it, PQRST, PQRST, and then on the right side of it as well, PQRST, PQRST. If I have that for those 4 beats, then I'm going to move the X cursors and intervals right next to it. I'm going to use the delete function to get rid of any sort of spurious points that I put in there. And then I'm going to rely on the bit beat function here in the middle to let me insert how many beats should be missing for that participant. Again, based out of normal IPI distribution. So it's going to put that point for just 1 in the middle, and then we're kind of all set. From there, don't forget that you need to look at the rest of the data in this segment. Don't just like I did it, done, and then go to the next segment. Because again, there could be some sort of issue with this person where even if it could be motion artifact, normally they look a bit different, but you could move in such a way at the perfect time with the right envelope. The software thinks it's a beat, it placed the blue circle there, and if you didn't look closer, you wouldn't see it. So definitely continue to look for the rest of the segment, make sure there's nothing wonky going on there. But okay, we've done that. We're going to go on to a couple more examples here, and we'll take a break at 3 o'clock. So again, as a more experienced data cleaner here, so first thing, bone respiration looks good. And if we were looking to report on something like chest heart rate or arm SSD, we don't have to do that with the respiration. It's not that we have to validate those things for respiration, but very specifically with RSA, we do need to do this. It doesn't go into the calculation. Like I can actually turn off respiration in this case. I'm going to save these just for the video and everything, but yeah, so I can actually, I have my edit file on. It's grayed out some of the changes, not letting me sort of double dip, if you will. So I can actually turn off my respiration, and I can still populate the RSA values. It doesn't, so it's not like the respiration goes into it, but we're just as the data cleaners ensuring just sort of validating that that RSA value is correct because they were breathing in that normative range. But I guess I'll just go ahead and start with this data set anyway. So anyways, we did it with that one before, and then at this point here, it could be acceptable that you don't have to necessarily go in and look at every single RP. I'll let the PIs kind of decide on that. I have a sense of what all is in here, but In a lot of cases, it's just really good practice to get at ours, jump in, look at those 10-second windows, get eyes on every beat, and then we can kind of move forward. This can be very quick after you get used to it. So something like this can take you like 15 seconds to look through and just make sure that everything looks correctly. But again, it's sort of up to you or whoever is in control of you, or maybe that's not the right word, is it? To sort of dictate how you're kind of doing that. I thought I was like, wait, are they? No. So anyways, once we go through the look at everything, we can kind of make sure it's done correctly. I'm disappointed. I've looked at this file 5,000 times. Everything is good in there. So here at the end, though, we have something like potentially some additional artifacts we need to look at. So let's jump into that one. And again, don't just go right to it. Let's start from the beginning of the segment. And same deal. We're just going to keep an eyes on the R peaks and then looking for any sort of egregious abnormalities with the T waves as well. Okay, so we've arrived here. Now what we have is some different structures that is occurring with this person. So again, because we have something that maybe let's say that one is a premature atrial contraction before, we have premature atrial contraction of PACs, premature ventricular contraction of TVCs, and then premature junctional contractions, essentially electrical conductance issues that are commonly found in the data. Again, we don't really need to look those up and match these on those who want to just kind of nerd out. But when one of those things occur, other of those potential cardiac arrhythmia or ectopic beats are more likely to occur for that participant. So we can see here that in this beat, it looks, different. I mean, the sort of T wave structure from the one before actually looks similar, but the beat is now missing or inverted, or I don't know what that is. If there is a T wave, maybe that's it. It's very questionable. But this could be something like a premature ventricular contraction. I had to take a stab in the dark here because we do have a T wave here. Looks like the atria did depolarize in the correct way. But I'm really just very much guessing because I only have one deflection here. So, but regardless, this is an abnormal beat. We don't want to include it. Before making edits, though, we do see another beat after that looks similar to the one before, where we are potentially missing a T wave in this one. And then we do see what is a very long pause, and then this is a T wave before that occurs, and it's also heightened more than the ones that we were seeing previously. So again, there's a delay, a little bit longer on that, but then it's also just notably a different height and amplitude. So a couple different things here. So hopefully this is more clear, or maybe the word obvious. I don't want to use that too much, but hopefully it's more clear to everybody here that this is a somewhat or abnormal beat. And so in these cases, the sort of treatment here would be to delete this peak, and then we can put in 2 mid-beats here. I think it's pretty questionable if we should leave this one in the middle of these 2 artifacts. It is in technicality fine, a good beat, but I'm going to leave it for now. But I think on a personal level, I would not trust anything around this area because of it. But the technical proper procedure would just be to enter these beats. Now, this is actually in a lot of cases a better treatment and when we have multiple raters, because this is a game time call if we're going to leave one in the middle. I mean, what is the criteria? Like, hey, if there's 2 arrhythmias, if there's one in the middle, we still delete it. Like, these rules start to become very complex. So in a lot of cases, if we see anything, we're going to need to move on. It's sometimes, even though maybe there's one interval that's off, instead of doing that between our 5 raters, there's going to be a lot more consistency, which is really what we're after. So you can develop a protocol in which you want, but I think even though this might not be the ideal situation, because this beat could be offset because of the sort of ectopic beat, right? The timing could be set off that. For the sinusoidal node is able to reset itself, and those 1,000 different cells are able to start firing a synchrony again. This could certainly be the timing characteristics could be thrown off because of it. So certainly possible, take it with a grain of salt, but I think this is usually the most preferred procedure again when you have multiple raters. So okay, so we've entered the 2 mid-beats there. We go to the next segment, and then like, oh gosh, it starts again with the same issue. We're gonna jump into it. And again, it's in the window from the very beginning. Now we can see there's this event here, this sort of we'll just call them what we think they might be, like sort of PVC, and it's PVC occurring. This right here, in a lot of cases, where we see a very long interval afterwards, those T, It's also called compensatory pause. So essentially this is occurring, allowing the sinoatrial node to reset its rhythm at this beat. We'll see this later on. But anyways, this is sort of what's occurring here. So this is, it also could be a reset that's just not sort of taking, if you will. Yeah, we saw the same structure that we saw just a couple seconds ago. And here again, it's just sort of going over here. And then it starts to normalize without those ectopic beats. So again, we could call that same structure before as deleting these any sort of spurious beats within these other ones. And it just so happens that we have a good beat every other one. And so then we could go through and we could actually do this mid-beat procedure for every single one of the intervals. And yeah, sort of create these oscillating good beats and bad beats. The reason why I wouldn't do this in this case, just because it is one good, one bad, one good, one bad, just because it's flowing, is so what we've done here is we've put an estimated beat between the 2 points. So this is an extrapolated sort of artificial point at which we think that beat should have occurred without this abnormality. But this interval now, this timing between the good beat and this bad one, that's not like a real timing, right? And so we have an extrapolated interval here and here and here and here and here and here. So really what we've done is we have interjected a lot of sort of information here that has nothing to do with any sort of arrhythmia due to breathing for this participant. So in these cases where we have those kind of oscillating back and forth things, I would just delete everything, especially from the beginning of the segment if possible. If it happens in the middle segment, you could take this procedure, but then then you're using two rules. You're like, hey, it's ideal if we do it on the ends, but if it's the middle, then we can just mid-beat. So coming up with a sort of more rigid rule is better for that. Sort of a grand sort of interclass correlation coefficient is higher when we have one kind of rule about it. So if it's mid-beating, then that makes it better for you because we have like 17 people having the data, then you could certainly follow this procedure. If I had to do that though, I would still make sure that we have at least 30 seconds of continuous data, excluding those ones that we had to create if it happened to happen in the middle of a segment, of course. Hopefully, if this does happen and it's not on the ends, like even if it were happening all the way in the middle to like this point here, we could theoretically do something as far as deleting all the information there, and we still do have something like more than 30 seconds available. So it would have to happen right in the middle, at which we would have two ends that are automatically less than 30 seconds. So hopefully that only happens once in a while for you, for that person, but there's a lot of flexibility we have in which we can do this. So yeah, anyways, just something to kind of keep a note is it's not only wasting our time, it's just adding some data which is going to very likely underestimate the RSA in that case, right? Because if we have these intervals that are very standardized for this person, all of these are going to bring down any other change, so any sort of natural change for these beats that are occurring over here. So just kind of keep that in mind. Okay, so that's kind of this just keeps happening for this person, but they are I think there's one segment that we have to throw out, so it's pretty good still. And I'm gonna save all these edits here, but for the recording officially, so we're gonna hear me. So let's not look back and be like, oh, Jay edited this way, and the file's fine. It's like, I'm leaving it just like this, so when you're looking at the files yourself, you can kind of have the same stopping point. But okay, so and real quickly here, I added files. I said yes, I want to edit this file. I came back to the screen. Now we have our MWI file loaded. Again, this would say like your subject identifier, but we have our .MWI, and now we have a .EDH2. So it's edited data, heart rate variability, and then 2 is just our new structure. So we have that loaded. So if we wanted to then do another analysis pass over, we could go ahead and do that now. And we could do a different event if we wanted to do 30-second windows, for instance, or we want to go to this event to look at specific ones pre and post, but we have our data already edited, or the continuous mode, of course, as well. So we have our edit file. Now let's output those second changes. But okay, cool. So I'm going to I'm going to do one more. Okay, so sorry, I forgot about something. Okay, so I'm going to jump back in one more thing that is done. So a couple different ways we can edit the data. One would be that, we have this large amount of segments here. This is probably not too bad. We can get this done within a session, but in the real world, let's say that we have 2 hours to edit data and we have to go do something else. one thing one approach we can take is we can edit each segment. We can say like, okay, segment one's good. Once we're done with it, we're gonna write it out. So when we write it out to that Excel page, we can see here at the top right that it's been written out. And if we have done this previously, this will turn into yellow written saying that, hey, this was written out in the previous session. But regardless, when we do write that out, we can see now that we have our file, we have our edited file loaded from the previous edits, and now we have the output file actively loaded, that text.sx. And this is really just a Excel file format. I mean, you can turn that into a CSV and run to any other thing you want, but regardless, so we have all those things available, and as we're going along, we can write out the segments as we have corrected them or as we verify that nothing needs to be done with them. And yeah, so that's one thing we can do. And then when we're done, let's say we have to, we're at the end of our 2-hour mark, and we need to be done for the day. We can notate, we could write down like, hey, I finished at 3, need to start at 4 tomorrow. That does open us up to a little bit of user error, I think. So, you know, that's something that we could look at. I mean, there's also, when we load the file back again, you'll see that that written has been done for some. So in this way, I think this is maybe the best way to do this. We could then say that we have that written out to the Excel file. We're gonna hit done. We're gonna say yes if there's any edits that we made in that session. Then let's say we're coming back the next day and we're going to try to finish this file. So we open it. We're gonna make sure that we have that edit file loaded. It'll automatically load it for us as long as it's in the same subfolder. If you left it there, then we can just okay. So now we have the MWI and EDH loaded, but we don't have that Excel file loaded. So what we need to do is we need to jump back into our analysis, and then we're going to say open the output from the previous session. And then I'm going to open that up here. And now that it is correctly loaded, we do see that segments are written out in the previous session are yellow. And then what we can do is we can say that search for the next unwritten segment. And then that will check for us automatically and let us know where we need to start doing the analysis again. Another method here, which is, I think a little bit riskier, but I mean, can be more efficient if you know you can get it done in time, would be that we go through and we edit every segment without writing it out, right? We're just going to go through, correct every issue, and then when we're done, we can just hit the write all segments. The problem with this would be if you have a segment where we're going to discard it, then you're going to write out the one that you didn't want. So only in certain circumstances would I do that, but there is that write all function. I think the write all function is better used in the first example where we can actually see how many artifacts are in that file very quickly. But, okay, there we go. So now we're going to load a different file here and look at some other normal data. So in this case where I was looking at a different person within that same area, I need to say I'm not using that edit file. I'm going to create a different one for each person. So we're going to now map subject 2. Just so happens we had 2 people in a session that both had some abnormalities, so whatever. But let's go ahead and first, so we have a respiration peak frequency. Now this one right here, as you can tell, is it's right on the border here of which one is actually taller than the other. I would say just as a general distribution, most of the power is within this high frequency spectrum. If you zoom into it and actually look closely and put your cursor there, this one is slightly taller. But when we're looking at creating this rate, it is only looking within that window, and it's also looking at 5% outside of it for any sort of peak. After that, we're assuming that, you know, if this is truly the peak respiration, it's your job to identify that and then not write it out to Excel. But anyways, this one's really close, so it'd be a little unfun to do, but you can see here, the actual quality of the respiration data is not very good. So but this person's respiration belt's probably moving around, we didn't put it on tight enough. But anyways, we do see that the waveform up here in red at the top, it looks different than before, right? Like we don't have just that pronounced R peak going up. We now see that we have an R peak maybe going up, and then we also have something going down. So before I was talking about, you know, sometimes it's very obvious if the ECG is inverted or not. In other cases, it's not. So this can be due to just the, you know, genetic individual differences of that person. A lot more likely it's because of the electrode placement was a little bit off, maybe towards the stomach, towards the back for that lower one. or maybe off of the bone a little bit on that right clavicle, it's creating noise, what have you. But yeah, so we do certainly want to look at this a little bit closer. And this is another example where, you know, because of this, unfortunately, even if we inverted this, it's going to have the same sort of problem, right? You're going to have to get eyes on every peak just because of that sort of ambiguity as to which is an actual peak in there. And that in this case would be a very good idea, it turns out. So if we zoom in here, you can see the very first thing we have is probably not an R peak. This occurred, of course, before relative time 0, but it is just a motion artifact that, in relation to these other ones, again, the only one that the Mad Mag check is this one right here. So the algorithms are a little bit limited, but that motion artifact, or if that's a T wave, wherever that is, just happens to be the right timing with the right energy envelope to where it's sort of, you know, full of the algorithm there. So those are things we definitely want to catch by, you know, when the file's a little messy, or when we can't tell, obviously, start from the beginning and look at every QRS. So in this, if the question is it inverted or not, we can zoom into just a couple beats, and we can look at this a little bit closer. When we do that, it sort of looks a little bit different, right? That the P and T aren't quite as pronounced. So then that's a good reason to use this other zooming window here. And we can set the range just right above and below what we see there, and then the waveform's a little bit more obvious. And these are kind of hard for you to see, isn't it? It's a little bit better, no? Yellow? Is that better for guys? Can you see that? Yeah. Better. Cool. All right. So
We only recently realized you could do that. It was like, oh, fun.
yeah, that's pretty much right. You just pick your favorite color. Yeah.
I had that same moment. I was like, well, how long have I known you guys? I can make it pink.
This is the only feature we didn't operate, so we got people to buy it. No, but so cool. So we've changed over the color to see, which is nice. I usually do purple, but it's not very good here. But okay, so if we're looking at these components here, we have the P and T wave. So we have this P wave here. T wave is a little bit hard to see in this sense, but we could move that window in even a little bit closer. If we're not sure to pronounce that a little bit more. It's going to distort it a little bit, but yeah. So what we're going to look at here is a couple different things. So P wave is, again, P and T wave should both be up. But again, sometimes it's a little unclear because after we have the upward inflection of T wave, we have a dip. So then if we invert it, you're going to have the same thing. You're going to have what looks like a T wave going up. In this case, it's not really that much of a structure, but I'll invert it to show you what I'm talking about. So the P wave is usually the better way. You know, if this is up in that sort of time criteria, and the P wave is up, that's usually the green light that everything's fine. However, as you can see with the P as well, so if I were to invert this is now going to be negative, and this is going to look like a P wave. So I'll go ahead and show you what I'm talking about. I think you're rubbing off on me, Paul. I think I said boot there, but close. Okay, so I'm going to invert this one. And like I said, it's almost like not really clear if it was from that first example. But we'll go ahead and zoom in on these. Okay, so I think the level's fine. So we can see again something similar. Like, oh, here's a hump here. Like we weren't very experienced in doing that, and honestly, in some other data sets, it has a perfect reciprocal on the other side. So the timing criteria is really the one we look at. T wave is a little less reliable. That kind of drift a little bit more. P to this R relationship is very strong, and so what we can see here is that we do have something that looks like a P wave here, but it immediately drops down at that point. That should not happen. There should be a time of at least like 30 milliseconds between peak of the R here and then when it goes down to that Q point. So if we do see this, that's why this is incorrect, because it drops straight down. It's a very usual indicator that it's incorrect. So it was not inverted before, it is now. Okay, and an additional thing that we have on this one, this is a spool of good examples. Yeah, right there. I think that's. Alright, so we have this artifact that we can see here. Maybe yellow wasn't the best color, I don't know, whatever. I can deal with it. So we have an artifact right there, but everything looks normal. So if we look at the surrounding intervals of PQRST, everything looks fine. It doesn't even look noticeably early or anything. We can get our cursors because we just can't believe it. I'm gonna set it for the one just before, but okay, normally I'm here. Let me just do the correct thing. So we're gonna do that. We're gonna move it over. The timing is about the same. Again, there's some drift here. Anything less than 50 milliseconds is not significant. That's pretty normal. But there is some drift, but relatively we're in the same cardiac timing. But if we move it here, we're starting to see there's a decent amount of drift. If I move this over this second one here, we can actually see the time difference between the other interval, and it is well over 50 milliseconds, 4 times the amount. So it is significant to us, but it doesn't mean that it has to be removed still. It's really not significant enough to where we can visibly see a change in that. And if we turn on the respiration, now this is where it helps us quite a bit. So in this case here, this person is taking very long exhales when they're breathing. So maybe this is part of a case screen task. They're doing a really bad job of it later, but whatever the reason is, they're taking sort of shallow inspirations and then very long and then deep expirations there. So when that occurs, we can actually create what looks like an arrhythmia by doing that. Like if we exhale for 10 or 15 seconds, you'll see your interbeat interval change and probably start to highlight a lot of red flags on there. And that is inducing that change there. So that's why we really don't want to use those people that are breathing too fast or too slow, right? Because that'll show you right there that that's something we don't want to use. It'll give you an RSA value, and it'll be a pretty huge RSA value, which we would like in some cases, but it's incorrect. So visualizing when we see an artifact like this, everything looks fine. It's not super early, and then maybe a little bit. It's over that 50 milliseconds, but just because it's over 50 doesn't mean it's wrong. Like that's certainly allowed to be drift. It's just usually that's significant. So nothing's really matching our criteria what to do with it. But we did notice that they're taking very long respirations before the next beat. And when they do take them, they're not very high in amplitude. So in this case here, what we can do is we can look at what's occurring here. So they're taking a breath in. So we would assume that with a small amount of latency, the beats that occur after that are starting to shorten, right? They're breathing in, heart rate's increasing, the interval between those is shortening. When we breathe out, then now I would expect the intervals at this point are starting to expand. So this actually makes sense here. We can actually see as they breathe out and they keep breathing out that the intervals are expanding in time. So that's actually what we would expect from RSA, right? And so this is a beat I would actually leave alone. Now, this can be confusing, and this can cause confounds when you have multiple raters because we don't know that they'll make the same decision. It's a little bit subjective in such that they took a very long expiration there. And so to make that decision and say that that's a good beat, we're going to leave it alone, can sometimes cause more issues than if the rule was just get rid of everything yellow and make it a mid beat if not. So that's one of those sort of, research specific decisions that you all can make. But personally, I would say, or officially, whatever I am, I would leave that one alone. That is just an example of arrhythmia due to breathing in this case. After we ensure essentially that highest peak is there. But you can see that's why we have so much activity here. It's because they're taking those very long exhales. So that's what's making this lower frequency area larger. So something to be cautious of. And then I think this actually has a couple more things for us. Running a little bit over, but okay. We'll get into these figures later. Different file. This is the example that I wanted to show you here, where it's maybe the RP. It honestly I don't think it's a any sort of ectopic beat. I think it's just potentially a motion artifact that's moving around at the same amount of time. Especially because this person doesn't exhibit any of those other abnormal beats anywhere. But anyways, this is picking up on probably what is the peak actually up there impressively, but there's two. They're close enough to be the same thing. They could certainly be the peaks. honestly, like this one down here, it also probably fall within that window that's allowed, and so did that one. So what visually we see what we think. I mean, like here is the P wave there, or I'm sorry, I mean this is the P wave, Q, the R, the S, and then maybe there's T missing. We don't know, but it's pretty ambiguous at this point, honestly. But it just so happens that that occurred at an acceptable amount of time for the IBI and the ADVEC check, and it also is occurring within the same amount of time there. So the same energy envelope, everything is matching. So this is a problem. This is why when the signal does not look perfectly clean, we really want to get on there closely and keep eyes on every R peak to make sure that we don't misidentify this one. An additional sort of step that we don't want to make is any sort of confirmation error. So if we were to go through and do something such as a mid-view procedure here because we're not sure about it, this is what I would recommend you do. Then we're going to go ahead and place a mid-beat there. What we don't want to do afterwards is say like, oh, that's where the mid-beat was located. That's really close because that's the normal IBI timing. Let me run a cursor over there. And, oh, it looks like that mid-beat is actually exactly where I placed that R peak. And now I'm going to go back and change it. Don't ever do that. If your decision was up front that I'm not sure about on the mid-beat, you need to stick with that afterwards. And then don't sort of use any sort of confirmation bias to go back and change your answers. I guess just from here, if there's any additional questions on sort of messy data, there's quite a bit in here that we can look at, but a lot of times you're going to have to make some judgment calls on whether B looks good or not.
That last example, could you have just, or would it have been acceptable to just leave it with the peak that was designated as your R peak? Because like you did your timing, you're like, it looks like it is it, and just leave it. It's like, I'm not touching it.
Right.
My decision is, because that's what I would have done.
Right.
I wouldn't have mid-beated it and cursor checked it, so I was just.
But if, like Dr. Guerrero wanted to open it and prove to him that that's a QRS, how would you do that?
I would tell him basically I did it based on my time, and that's as close to proving it as I can get to.
Right. But it doesn't look like QRS at all. So
Right.
It's that kind of confirmation point. If we had to look through the data, if we're having that, because what we would normally recommend is that just for like an ICC check, if you have your sort of normal, inexperienced data cleaners, they're doing most of the work, right? The sort of experienced person should edit the same amount of data, or at least not the same, but some subset of it. Now, normal recognition is something like 40%. A lot of times that's not possible. But in so doing that, it would be a lot more difficult to kind of verify if everyone's making the right decisions. Right. If some people are leaving it and others are not doing that. So
it really just be about the consistency of making that decision across the participants or across the data.
Right, yeah. And you could change it there, but I mean, again, like it doesn't look like a beat at all, and milliseconds matter.
Right.
You're doing something RSA. It's probably not significant. I'd say it doesn't do anything to it, probably until like it's 100th of decimal. Right. But it's just you by yourself adding data. Yeah, you could go ahead and do that if you wanted. But if you had multiple people making different decisions,
because across the board it would be more even to do that.
Just do the mid-beat. Yeah. But anyways, any sort of messier data we're running into, such as this one here, it does become a little bit more difficult because we don't have what is a clear P wave there, probably very much due to the motion artifact. But if you look at other components of it, just sort of the general architecture here compared to the other ones around it, the width, the breadth of this, I do believe that is the R peak. I don't think this would be hard to show everyone on a consistent basis. Like when we see this, everything's fine, the time criteria match, we can move our X cursors, everything's fine. We can leave that one alone. If we go through and we're like every single one that isn't perfect, we're gonna mid-beat, you're gonna end up having to throw out most of your data. So things like this become a little bit tricky, but hopefully in using some of those tools, even when we're in a very messy section, help you, identify that. Like for instance here, this one again is looking quite a bit different than it, but we do at least have that R spike from the Q to the R, and as that looks like the same architecture compared to the first one. And so what we can do is we can come in here and we can actually use our sort of timing walking method to go through here and just do another confirmation that beat is occurring just exactly where we'd expect it to. So there is a level of ambiguity there and sort of, art form, if you will.
That's why it's so important to get that training SOP like consistent across people. I had a subject that kept sniffling and coughing a couple weeks ago, and then it was like I couldn't decide whether I want to put mid-beats in on that messy section or am I just cutting those little chunks out as long as I have enough time around it, right? And
Yeah, and there's a principle, I'm not gonna say completely, but it's either F, yes, or
yeah,
right?
right.
And so if you're not completely sure about it, then do that for
Okay.
special multiple raters is gonna be a
Yeah.
lot more
Yeah,
specific.
so there's like multiple segments where you have little coughing fits, you know, and it was
Exactly.
just small chunks of time, but it happened multiple segments in the rest and in the post-rest.
Exactly, yeah, so that's kind of why we wanna use that in between there, but yeah, does everyone feel kind of comfortable with this?
Yeah, okay, that's good.
Right. All right, so if we wanna take, like a quick 5-minute break, so we'll go to the bathroom and then we'll kind of finish up with the other two analyses there. We're running a little bit over, but if anybody's still interested in hearing what I have to say, we can continue on for maybe 30 minutes after that, so. Cool. All right, so let's take a quick break if you need to. And next thing here, we can look at into impedance. So, one quick note here, just, I'm gonna actually, show something real quick. I think I don't know if we made edits on the, example file, so I'm gonna go ahead and do that. I just wanna show the step of, the fact that we do want to, edit once essentially between the HRV and the impedance application. So we don't have to make this decision twice. So I'm gonna make an edit here that is proper, but I just need to make an edit on this file. So we're done. I'm going to save those changes into that demo file. And now what we're going to do is we're going to load that same file into impedance. So we edit the data in HRV, move it into impedance. And so in that case, we're going to load the same file. And we're actually in this case, we don't have an impedance edit file, but we want to bring the edits in from HRV. So we're going to say we have an existing one that we need. There is the EDH, so that's heart rate variability edit data. If there were an edit data from impedance, it would say EDI. So we actually do want to load that EDH file. It grays out ECG because it's not let me change that. I'm going to change it to an HRV. And then I just need to map mine to 0 and 16. So I'm going to go over the calibration settings a little bit quicker because we'll have to leave here in a little bit. Yeah, I think I talked about this, I think quite a bit yesterday, so I don't know if I have to spend a lot of time on it here, but I guess, does anybody have any questions about the settings that were over yesterday, or anything like that? Okay, one thing I do want to show then, in just that case, is the Ensemble link here that we see. So for adults, this is a good setting that within the cardiac cycle, about 750 milliseconds are that sort of mechanical property of it all. And so when we actually look at the analysis section of this, we can see here that we have that 750-second window. Now, certainly it is the case that we could have a much higher heart rate, right, within small, shorten that window quite a bit. And so if we ever did come to this screen, especially if we were looking at that child data, if we're looking at that 0 to 3 range, I mean, their heart rates could be, 100, 140 or something beats per minute. And so in this case, you can see 2 of these DCT things within the window. If that ever occurs, we need to shorten that ensemble length on the previous screen. So what we're going to look for, what is the window that we're going to use is pretty easy. And we're going to do it on a segment by segment basis for these participants. So if we're coming in here, we see our QDT or Z max, the X is that point of closing. We can just pick a point right after that. So we can say something like in this case, 500, 575 is a little bit more drift so that we don't have to change it every segment necessarily. But so let's go ahead and hit 575 before the next event occurs. And we're just going to put that into that window right here. So we'll change that on a second to second basis. Again, if I don't want to have to change that and go back and forth every single time, I should probably pick a window that's sufficient enough to go through the entire data set, making sure that X can be identified in every single one of these, and if it is, then we're good to go. So just one important distinction there, so everyone can catch it. Oh, and you had a question about the DCT and sort of being lower and offset from the ECG signal, but it's hard to like correlate to.
Yes,
Yeah.
but I checked yesterday, yeah, there's
You checked?
trendy
Okay.
too, yeah.
Okay, cool. All right, just wanted to highlight it. There it is.
Yeah.
Cool.
Sorry,
Yeah.
I did just have a question about ensemble link. So would you say that it would make sense to maybe standardize ensemble link just for a whole like population, or is this something that you would have to do like participant to participant change it, or?
It would probably depend on your age range that you're looking at. If it's a tighter group, you could probably do that. But if you're looking from to 18 or something, then you're gonna have problems with that.
Yeah.
It wouldn't be a problem though, as long as you can make sure that the X present on everyone, it doesn't matter if it's for every person.
Oh,
It's just that you're identified, here's the closing of that electrodic valve, because we don't care about anything like that.
yeah.
It doesn't matter until we start with the new, Q point in the ECG reflex cycle.
Okay, I wanted to know, because I was wondering if changing that name was gonna do anything in terms of like value.
Just as long as you have X. If you can't find the X, what's gonna happen, I mean, you should be able to see it, but sometimes there's always a problem, right? Now, how when should we look on a signal that is changing over time? One thing you can do here, so if it can't find X, if it can't find that trough, then your left ventral ejection time is gonna be highlighted red.
Yeah.
And so when you see that, that's what's going on, is it can't find that closing X point. So, but yeah,
But if you see the onset of another wave within the 750, it should shorten.
absolutely. I mean, if this right here, there's an example on the sports site, I don't wanna sound like broken record, but there's an example on there as to where this is the same thing as this. So in those cases, you want it right outside the X point, to make sure that you're not running into that other EKG signal. So you should see both though, right? It's not like you're gonna see just the DCDT if you see the multiple peaks within there, so.
And I think we could set what the ensemble length is for, to use as a standard.
Yeah.
And then if there's an individual for whom we need to change that to get rid of this, because they, for whatever reason, have a much more rapid rate,
Outside of that.
then that's okay.
Yeah.
You don't have to adjust everybody else.
Right, I can definitely do that. Okay, so anyways, this file right here doesn't have the endosemantic. This is what an ideal CT would look like, sort of triangle wave structure. We have a max singular pointed max blood flow Z, also sometimes seen in the literature. And then we have a X point closing. And this might not look very simple here. If we jump into the Ensemble editor, and we actually use these zooming windows to, sorry, the second one here, to focus in on this, it is actually quite defined when we zoom in. So, if you're ever in question on that, you can use that second zoom in there. But, yeah, anyways, cool. So, anyways, this is an ideal kind of situation here. I'm going to essentially jump out of this application, assuming that that's fine, whatever, understand what that would look like. And we'll go into some impedance examples. So this certainly can cause some questions because as with a lot of sympathetic markers, there's a lot of variance in results here. But one thing to note here is, you can see that the ZZT is quite different than that first template that we saw, but it probably still is usable. It's not that bad. Like we can see that there's a single peak up there, and if we use that zooming function with the Ensemble editor, we can see that that is actually a singular peak. The X is finding that trough location within the 3 and 600 millisecond offset from the VNOx opening. We're expecting the closing within 300 to 600 milliseconds afterwards. It's finding that point. And also, based on this person's heart rate, the range we're expecting that to occur is being identified correctly with B. So even though it does look different, I think this is probably still salvageable. What we would likely want to do when it looks like something like this is actually hit the edit R's, look in here and make sure that if there are any messy segments, we're deleting those corresponding peaks. So what we would do here as far as editing the actual data, all these tools are exactly the same, which is nice. If we zoom in here, we're going to do our 10-second window. I'm going to show you something that I know would never happen for any of Paul or Cam's or anybody's students would do, but in this case here, what we can see is we have what looks like an inverted ECG signal. If we actually invert it, it really is. But the other signals are, as far as the DZT are upward, totally possible. As we move through this a couple seconds later, we see a lot of noise here, like they're jumping around, they're MMA fighting, they're plugging electrodes in and out. And it turns out they did the latter. So what this experimenter does, they were like, oh, crap, it's inverted. Let me do a quick swap here for, I don't know, within 500 times per second. And then afterwards, once I actually get it plugged in, like, oh, it's perfect right now, and nobody cares. So definitely do not ever do this. If you notice that that is inverted, just leave it alone. We have a button for the inverted ECG. The DZDT should always be rectified in positive if you're using files from a different acquisition system that does not rectify it. It's possible, but again, we have a button within the calibration settings to invert it. So don't ever do this for sure. What this ends up doing is for this segment, because there's some motion artifact later on, and here this area, we can't actually beat through there. And so now what would have been 30 seconds that we can actually use, or 36 seconds, is now not usable at all because of this problem. So they definitely ruined an entire segment, which would have probably been the baseline. So yeah, seems obvious, but please don't do this. But anyways, as we edit in these ensembles or in these sections here, I'm going to go to a somewhat cleaner segment for this. The deal here, what we're looking to do is definitely zoom in on this one. Second window, this is almost impossible to look at from the first initial screen. What we're looking for is that those sort of singular peaks there for the DZT. And we want that single point there. For this person, they're just moving around a lot. There's not a lot of great cycles in which we see that. But we do have a few here. So we can actually get an idea of what that R to Z relationship should be on a couple different cycles. Of course, this could float around a lot, but it gives us a general framework for this person, so about 143 milliseconds, which can help us in other cases if we need to decide whether these surrounding needs at least are, whether it's the correct peak or not. Because what you're going to see in sometimes with the peak cardiography is we have a double hump structure. So I'm going to zoom in on that real quick. And so this right here, so we kind of see like this M structure here. And this is just like the gremlin of impedance cardiography because it's really hard to say why it's occurring. We do think that it could potentially be due to some sort of abnormality in the sort of valves within the heart, not necessarily anything that's issue with the participant, and that's going to be any sort of negative health factor or disease state that's being shown here. But it can also be shown to be done from posture. So I think with this specific example, I think it is due to posture. So if they're actually rocking back and forth, we're actually going to get some movement around of different organs and blood flow within that thorax, and so that can actually create this issue. The other thing it could be, and what is I think most likely is dried out sensors. So the actual ECG sensor, when they're dried out, you can actually see this conductance change when that blood is at its sort of most conductance point. If the sensors are dried, it kind of saturates the signal, if you will, or very temporarily, and creates this sort of thing. So really making sure that our sensors are fresh can usually alleviate this problem. But yeah, anyways, so what we want to do as we're moving through the data set is we want to come along, and when there's any sort of egregious change from what we saw from the Ensemble editor, not even necessarily those double humps, because we can let the initial waveform guide us. And honestly, if I saw this Ensemble that clearly, I wouldn't even go to the editor. Personally, I think that's clean enough to where we can be sure that any sort of edits we make aren't going to adjust the maximum of Z anything significantly. But certainly it's your own call if you would like to peek at them. And of course, if you have multiple raters, I would just tell them how to, of course. But going through and we're looking for any sort of egregious changes in that triangle wave following our peak. And guys, it has to happen in that order.
Go back
Yes.
to the first ones.
Here.
I'd be tempted to flag off this one.
Yeah, sure. It's pretty good. Yeah, there's like 3 of them up there plateauing. If you start to go down that road, though, you're going to spend a lot of time.
We do.
editing.
A lot of time editing.
Yeah. So you can. What we have found statistically, though, if we go into a signal again, if it looks like we have a singular hump up here, we actually can see the B-notch in this case, but there wouldn't be inclusion criteria ratings, and we see that closing there. So I can go in and I can do this for one segment. I can come in here and be very trying to use a word, it's not going to offend you because you do it. We be very precise about how we're doing this kind of thing. But we can come through and we can actually edit all of these that don't have more of a perfect triangle structure here, and we can leave those ones that do. And yeah, I mean, we can't get all of these perfectly, but we can kind of get the ones that you're talking about, I think, more or less here. So, here it goes. Yeah, well,
We call them cat paws in our manual. They look like little kitty paws.
Like this one.
yeah.
Water
So we
cat
got
over, they splash the water.
just from here, feedback,
Nice.
up through here, and start keep removing all of these ones that are very,
You know,
you know,
sometimes
sort of
it's
ambiguous. So we
Yeah,
remove,
yeah. You're doing like the spa.
this thing,
And sometimes
that
it
there, this one here, removing. And so one of two things are gonna happen. One is that we're going to remove more than 40% of the data set, and so then we're gonna have to probably throw it out. And then the other is going to be simply that it didn't matter what we did. So by removing this many, it probably will have some effect on the data set.
You've taken a bunch of it, so let's have a look at.
Right, okay, so before I make any change here, let's just focus on maybe pre-ejection period. We're at 120 milliseconds. I moved a lot of those things and we're at 120 milliseconds.
Okay.
So that's kind of my point.
I feel right.
Does impact LVET? I know that LVET's not really our main focus.
It can, yeah. It's usually not extremely significant in that case, but
Yeah.
it can, because if you look at those signals, when that closing occurs, again, it's not this like very powerful instantaneous reaction. So by removing the ones that are messier, we're removing a lot of that like sort of signal noise that's around that X point. So that is true,
That's
but
LVET seems to be where we're
Mhm.
primarily seeing big changes. Scarlett might have a better read on it than I do, depending on which data set we're looking at.
So with messy data, especially children, this is why I don't use LVET. Because
Yeah.
the X is not always obvious,
Right.
and you run into issues like
Yeah,
this.
and we don't move the X at all. It's just wherever the X is estimated, that's where the X is estimated. I know in Ghana, in the impedance data, we've had issues with the Q floating, where there's not like a clear,
With children.
yeah.
So you're gonna have to probably change that constant of 35 milliseconds.
Yeah, and I would have to pull up the manual to know what we settled on. There was a time when we were doing a very precise approach to moving it, and we've kind of scaled that back. We don't look for the B notch. I mean, you've noted if the B notch is present, but we're not moving the B notch at all, but we are over editing at the same time. I think with a study that has so many moving parts, it's a way to flag, do we have other issues going on? We could maybe scale it back. We've got some things, you know, in the manual and training as far as don't over edit, like really take out egregious DZGT where it looks like it will make a meaningful difference, not just everything that's plateaued.
Mhm.
But maybe if we don't care about how, at this point, I'm not sure of change.
Procedures, because we're reliable.
Yeah.
And they're referring to it.
Yeah.
But again, like, and I know it seems a little kind of risky, if you will, or not, but when I see the DZT structure that much, I usually don't even go into the editor because of what I just showed you. It just doesn't always matter. Now, if you don't like that, you still do your thing and go in there and delete the egregious ones. But you know, and doing this for a very long time, I found that usually wasteful.
No, I believe of me doing it for not nearly as long, but sometimes we do get meaningful changes and the cue becomes more visible.
It gets a little bit different.
Yeah, like
And you can think
for a
that's
while, there's little minor things that.
Yeah.
In a study of individual differences, maybe it's gonna matter.
Yeah.
It's time stuck, and it is a very more neurotic way of
Right.
doing editing.
I'm all about it. It's just, you have to make some resource decisions.
Yeah.
So, okay, anyways, that is this example from Impedance, and then I do have a couple more here real quick. Okay, so here's one that's worse. And so, yeah, we can certainly come in here and we can try to remove all of the ones that do not look ideal. It happens to be all of them. But yeah, the idea here would be that if, again, we have a messy DCT signal, and I'm actually going to hide 0, so it's on my way. What we would do is we would say if we don't see that nice, triangle peak that follows the R peak, so the yellow triangle that doesn't follow the red, then we would want to delete the R peak that precedes it. So in this case, this is all unusable. So I'm just going to go ahead and say that I mean, really from this point forward here, and the ones before it, I mean, it's just, you don't really see any sort of discernible peak here. And hit control, delete everything to the left of it, and we can kind of move through this more. But again, as I said before, it's just not a good signal. Like, it doesn't really matter how much we edit this one. I think I've gotten down to like 3 beats and it still looks the same. But you can see here, like, it did clean it up a good amount. So maybe we can look at that a little bit more, but the general structure of it all is pretty similar. So what, the reason why I'm caring a little bit less in this one is just because it just becomes unusable as we look through this further and further. So if this was the first peak here, one thing to keep an eye on is the heart rate, certainly. It's pretty high. So if this is an adult, then we would expect certainly that that B notch is closer, right? It's going to shorten a little bit there. But the problem is here is it's just between these two peaks, that is one. If I move this Z to the second spot, it actually appears to be something over this point here. And I can actually see a little deflection here in the signal. So it probably is the first one. You know, what we found that it's almost always the first hump when we are looking at that. If we just have to apply a roll across, it's very rare that it's the second one. And so that can help us guide that quite a bit. But this is a very short projection period. It's not outside of the plausible range. The actual dotted line is underneath the B in this case. So it's certainly plausible. It's just, it's very early, but this is also a very high heart rate for an adult. And this is adult data. So
Suggest we should be changing the ensemble window.
in this case here. So I don't think this is another cycle here necessarily, but it would be a good idea in this case, just because that, you know, that range of, like, let's say the average ABI is about a second for resistant adults. This could be that second cycle, and it's going to look different. Like, the software is only really focusing on the area from Q to X. After that, it's not applying the same sort of transformations to the signal. So that would be a potentially good idea here to put it maybe somewhere around 500 milliseconds, and then go from there, because really after this closes, and even on a cycle by cycle basis, we don't do anything with the data. We don't have any sort of interpretations that are from it. So if we were to actually zoom in here, again, this just looks like kind of hot garbage, but we can see signal, so it is in here. But yeah, if we have that sort of change, you can also see the squiggly lines here. On ECG, this is noise. This is 60 hertz noise. So we could go back and apply the filter, done it. You can also look at the P's data. There isn't any substantial interference on that one though, so it doesn't really matter so much. But we definitely would want to get rid of this though, so we have a nice defined P and T waves there. But again, just focusing on impedance for right now, that doesn't really matter so much to us. So yeah, it's just kind of one of those things where if we were to actually go in there and actually look at that ensemble window, which was what I was going to do. Sorry. So on a single beat here, and we kind of zoom in a different way to look at this. Yeah, as far as once that valve closes, which is like very close to, very difficult to say in this case, but I believe it's somewhere around here, then we can pick from that point, just automatically, the algorithm is ignoring everything from that X until the next Q point. So if you see a lot of noise, but it's after that X point, just don't worry about it. It's fine, leave it alone. It's only if it is before that X, or certainly in these cases before this X as well. So again, so if it looks very negative after that normal triangle wave is perfectly fine. But yeah, I think that's a really good idea here, Paul, to look at that a little bit closer to shorten that window. But we can look at that. It's still as difficult to say, but I think it's 550 anyways. And then we do get sort of the same structure there, but yeah. But anyways, this ends up being something that is very difficult to say, and I think later on it actually changes its plan here on the maximum blood flow here. When this occurs, it's almost difficult, if not impossible, to say which B it is. But I mean, if I had to take a shot at the dark here, I think it's just because it is normally the first one, it's probably this. And then also that would shift that window over, and this is probably that X point in here. But it's outside that window as it is right now. So if I wanted to see what would happen if I made that change, I can actually manually move this Z point to the set first tallest maxima here. So again, you could train your eyes on this value as you're moving along. I think that 255 is what we want to stick with. And then we can actually say, since we've moved Z now, let's recalculate B, put it into that range. And then we get closer to the X point there. But just because everything's so smashed in there, I would expect that X occurs a little bit sooner as well. So it's difficult. I mean, you can't really move it and then stay within that normal 300, 600 millisecond offset. But again, just, looking at this in my own experience, I would say that this is probably the X point after we drop down there. But anyway, this person is having a lot of issues here. The sort of max blood flow point is changing between the two. So it kind of gets to the point where I'd recommend we don't use this participant. Pretty pink data, unfortunately.
And that would be because it's hard to really make a definitive choice about which is the correct sequencing.
It is, and it's also just that if that is the first one, it's the heart rate is high, but it's not like obscenely high, right? Like you can have 100 beats per minute, especially under stress induction. It's just that even with that first hump, it's very, very early for an adult. So it's 70 millisecond PEP is like really going there at a pretty good rate. So that causes just timing characteristics problems with the entire sort of mechanical cardiac cycle. And so that's why we can sometimes see that it's the first hump that we're seeing more blood flow, and now it's the second one. And it's certainly the case that we could move it to the first one in that case, but there's a lot of like arguments as to like, well, what is that second one going on there? Is that impacting when the left aortic valve is closing? Can we use LVAD to suspect the next cycle? All these kind of compounds come into it. So in some cases it is usable, and there's just like one segment where it switches and we can just, discard that one segment. But in a lot of cases what you'll see is once it flips, it's flipping a lot as we go through the segment. So it just becomes really dicey to use those kinds of ones. So if you have one or two or just a few and you want to use that, or a lot of them, and you want to use our complementary training, I mean, certainly you could meet with one of the trainers and get their advice on a subject by subject file. So, but yeah, generally I would try to stay away from those when they get very, very ambiguous as to what we need to do. Okay, and then we do have another example here, sort of highlighting once again the double hump structure that we're seeing. And once again, I would, just because we're seeing with the books, if you notice that it's very sort of elongated here from a normal pre-ejection period that we would expect, but the heart rate is also super low, it's 64 beats per minute. So you would expect some change in range in there, but as we move out here, we can actually see that, and again, in most cases, it's the first hump. If you edit through here, that second one actually becomes more muted and it becomes more obvious. So this is an example in which going in there and editing can help us quite a bit. And it is not clean file at all, by any means, but if we go through here using the techniques that we showed before, we can reliably get that Z hump here. And in the situations where it's moving into the second one, such as this, we can move it back over. And again, the dashed sort of minimum expected line is actually right under that V notch. So this is something that I think we could edit just because of the general morphology. It's not as messy. And when we go in, it's the case that when we remove the very messy ones, that first hump becomes a lot more pronounced, and then the algorithm is always picking it. And so we don't have to worry about it as much. Cool. Okay, I'm going to jump into Synchronization real quick. I'm seeing how fast I can do this in this big session. And then, but if there's any questions and those that can stay around, want to stick around, we can go through it a little bit slower, of course. But calibration settings, I covered this quite a bit yesterday, so I'm not going to spend too much time on it. I am going to get rid of all these weird settings it shows there, but yeah. Anyways, I think maybe the biggest question that we had. Something from yesterday's questions about like, all these SCRs, all these compounding SCRs, our count of the number of those is off the charts. So normally the block size here, this is a rolling filter. So it operates in a very similar way as does like the continuous mode in HRV. What this is going to do is it's going to set a block size. So in samples of that rolling window. And what it's going to do is it's going to smooth the data out a little bit, which isn't always a term we love to hear, but is going to smooth that waveform a little bit by finding points that are like sort of physiologically possible between those samples. So if, for instance, this is a mold device, we can see how many samples are done by going to file and the file info. So we can see here that this can get sampled at 500 times per second. So normally that's our recommendation for every block size, that it just matches the sampling frequency. That ensures that we don't have any sort of like latency issues or phase shifts in the data to anything that would be significant. In some cases, it is fine to increase the block size to something that's double the sampling rate. Whatever we change this to, though, I would make sure that it is in a perfect sort of like square of what we were initially starting with. So if it was 500 samples per second, I would only want to sort of go to something that is 1,000 samples per second. So something in between. Because if you imagine that you have a sample at 0 and 1, and then we double that, at least when we do that, the intervals are, followed over. So we're not just creating some random amount of data. So in those cases where we need to, when we're experiencing an inordinate amount of SCRs, I think a block size of 1,000 is perfectly fine. And you can see in the articles that we have within the training guides for impedance, it'll suggest the same thing, that you can, in some cases, go up to 2 or 3 times the sampling rate. And there's also some hyperlink to the attached literature showing the validation of why we do that. But anyways, normally starting at the block size of the sampling rate is ideal. And then when we jump into this, we can see a couple issues that I have prepared for us. So just main things. So we have signal dropouts as this. We have to go straight down to that point. And we actually want to get rid of those. We're going to go into editor, which works the same way as before. And again, this is some change in between this. Conductance. So if impedance didn't have a lot of rules, Conductance doesn't have any almost. It is sort of the Wild West of psychophysiology in a certain sense, because it is just not clear in a lot of cases what to do. There's not like these nice, sort of standard repeating rhythmic points at which we can say like, oh, here's this cycle, whatever that is. It is just this continuous flow of sympathetic output, and we have this spontaneous SCRs and things like that. So there's just not these nice landmarks where we can say like, bring that off this time and those kinds of things. So again, there's a lot of sort of indistinct sort of things that we can't really tell exactly what to do. But in general, when we see a dropout like this, a recommendation would be that you set a window right before that dropout occurs. And if it does come back on right afterwards, then we can put those X cursors around that window and then spline those together. When we're doing something like this is where another layer of somewhat complexity comes into play, is if we have what we believe is an SDR. So there's 2 different things we could do. We could say that if we're splining data, we're going to remove any sort of SDR that is either there for or is created by splining the data. Now this SDR was there, and it also followed the point at which there's a little bit of a shelf to this SDR. Normally that's not what we see. If you look at one normally, it is a straight up and down sort of. So this is usually indicative of an SDR that's continuing, or at least a compound SDR, which is one that occurs sort of before the half recovery point occurs. So when we're actually looking at something like that, I think another approach we could make is that we are actually going to insert the troughs to make that a single synchronous response. This being the trough, that being the peak. But certainly there's a lot of downfalls to this approach as well, because we can make the different decisions on it. Like, if it should have been 2, shouldn't we enter 2 there? How do we know this is the true trough point? Because it's just created whenever I start that splining. There are issues with it, of course, but this might be the best thing we can do. So as long as we're consistent with it, it is an approach. So you could sit here and make an argument over a different approach. I can argue back and make a third one, but yes.
I mean, I think that's what I would kind of bring up, is like how to get like the team reliable in that case, because it's like, as you can see, that's very subtle, And
Yeah,
so I
absolutely.
think like maybe for consistency's sake, maybe just getting rid of that SCR. Like you mentioned yesterday, I know that we were just talking about kind of like if there's a lot of splining that you have to do, just maybe looking at mean rather than trying to phase it.
Something like that dropout though, that would change the mean as well. That's pretty
That would
dramatic.
dramatically change.
Yeah, so hopefully we just don't have to make dropouts, right? Like if we can stop that from happening, then we, people that are rating the same file or different files, it would be the sort of very muted small effect of them not agreeing essentially. So hopefully we just don't have that many of those instances. But
My sense on that one is that peak was marked prior to
Right.
sliding the trough.
right,
So I don't think, I think it's appropriate to mark the new low point of trough for that peak. It's not increasing the number of SCRs that were gonna be counted. It's still reflective of SCRs that were present.
it's just the magnitude essentially,
Yeah, that's,
And we haven't been looking at magnitudes of SCRs, we've just been counting numbers.
right? Which I would recommend.
well,
For our purposes.
Yeah.
I was mostly concerned with tonic, right? Because tonic is like everything that's not included in the phasic component. So if just that amount of time is increasing, that would be my only concern. So I mean, I agree. I think it's more about consistency about that point, right? And what we want to do as a team. But my whole thing would just be about it's increasing that tonic period, decreasing that tonic period if we set it to the lower point. And so I think if we want to really get into the nitty gritty,
I mean,
But at the same time, like if we look at this though, right? So we have a phase, we're having the SCRs, it's dropping back down even to lower than the normal mean for the section, and then all of a sudden it's shooting back up. Like why? Like there must be some basic activity at that point, right? So is it improper though? Like
I mean, it's more about like where it starts and where it begins.
this is where, like, we could all forever.
Exactly.
Right,
Philosophical
exactly.
debate on WTF2 with EDA, and you might just have to accept that there is not one true approach, because it's not like a QRS complex where there's true or spike.
Yeah.
Get the team consistent. And if you're worried about, okay, and something that's unique and really difficult, how am I going to get reliability amongst my team? What I've done before with during attention is I've gotten them reliable on identifying very difficult things to edit. And then they flag me, and then I review that as like the master decider. So that could be an approach is we'll probably never be able to get, a large team of RAs to consistently identify when it's flying at a trough. We're all consistent, but you could probably get them to consistently identify. This is hard. And I would like a spot check.
What you're saying is
Yeah.
just what my approach is.
Yeah. And then
These questions are just to
it should speed it up though, it should hopefully make it so that you're only getting flagged for really difficult ones, that the easy files get edited.
Yeah.
And then the criteria for assessing the inter-editor reliability becomes number of SCRs, non-specific SCRs, and mean SCL for a point.
Exactly.
And there might be one or two differences. If what they're consistently seeing is from epoch to epoch, are there fewer?
And one thing also is another approach I've seen groups do is more focused in on intra-operator reliability. Like, are they reliable to themselves over time? Because if they can be, then you can have one person editing the same kind of data, and they're more likely to make the same decisions every time.
The extent to which I had very poor intra-individual reliability on the first data set I ever tried to edit.
Yeah. Yeah, there's not.
There was 104 preschoolers. I think by standards, shift.
Yeah, the based on how much sleep you had, your mood, and everything here. Yeah, of course. But anyways, with all that said, good luck with it. But just a couple more examples here. I wanted to show you, and also a different method in which we can check for that more experienced data cleaner, verifying sort of edits. Is so let's say we have multiple segments. So let's just use our pretend half a second that this is okay. Of course, it's not. If we look on the Y scale, we're at negative microsiemens. It's not possible. We want to be between 2 and 20. But that is one issue. But let's just say we were comfortable with number 1. Number 2, we didn't have. We had a question about. We don't know how to edit this one. We're going to wait for you to come by and check it. But number 3, we're comfortable with as well. And let's just say we continue on. We're good. So when we're done, though, we have created that output file, and see if I can do this quickly. So here is our output file that we have here. So it's leaving that column blank for that one that we don't have a question about. So you could very easily, you could load this into the application. You could say search for the next unwritten segment. That'll get you going through there really quickly. But you can also do it from this level of how many segments I had questions about as well. So when you do this, let's say that then the next day they get their advice from you on what you need to do, and then they can open that file again. They're going to want to load any edits they had if they made any, and so there was an edit file. When you get to the analysis screen, we can then open that output file. And then again, like I said, you can search for the next unwritten segment, put that in. We got our advice. This is how we clean it, write it out. And then when we go back to that output file, it will go back and fill in all that data on every single book at the bottom for us. So just to let everyone know how it does work, you can write over those segments or segments that were missing. Okay, cool. Anyways, that's that file. It's just, certainly it doesn't look like skin conductance just because of the sort of jagged nature of it all. There's also the page that's just looking on the Y, making sure that we're within that 2 to 20 range. Outside range being 0.535, but we're still at a negative value, which is not really reportable anyway. So this is an example. That's a nice example. Everyone's like, oh, that's obvious. And then this last one, which is the first one here. So this is actually a pretty nice file here. I'm going to do two approaches. One is like breaking it up to 60-second segments. And I'm going to look at the entire condition as we talked about earlier. One of the advantages of keeping it as, let's say that we have a segment, which is again like 5 minutes or something, that's 300 seconds. So we could look at it all at once. And the advantage of that is situations like this, where we have a synchronous response that's occurring right in the middle of the window. What's going to occur in a lot of cases is that we're just going to miss that one, or you're going to get one that's partially identified with a trough peak that's obviously wrong. Because we know in time that occurred here, so that's what a trough could be. So you're going to have to, you're going to be underestimating or overestimating something, synchronous level or the number of SCRs by doing that kind of thing. So you could take the approach of, again, looking at all the data at once, and then we don't have these windows that are separating the two things. One benefit though, if let's say that we're not looking for SCRs, if we're just looking for mean synchronous level, this does make a certain thing easier, which is differentiating the sort of behaviorally created SCR responses and or synchronous responses, and then those that are just due to a very large respiration. So as you saw before, when he had that sort of straight line going from the second, fourth quadrant, I said that he's not really responding too much. Let's have him take a deep breath and create an SCR. So it's showing that we can actually do that. And so look at a smaller section. It's a little bit more digestible to come through and look at these very large respirations to see if there is a skin conductance response that follows it. And again, the sort of criteria on that would be, is it 2 or 3? I would pick 1, but that's kind of the range for most groups. I usually pick 3 is that respiration 2 or 3 times the magnitude of the surrounding respiration. So this one's kind of in that middle range between there. But again, we could check this by looking at that total range of the respiration with that delta being 1.67 volts to this sort of normal one that is around this range. So it's about double, but regardless, if we wanted to look at it a little bit closer, the editing tactic we would have is to put one of the X cursors at the trough of respiration. So respiration being in orange, and then putting the next one at the trough of the next skin response, which would be here. And so then we could look at the window, the X cursors. That window that we care about is 1 to 3 seconds. So if it falls within there, that would tell us that we probably want to get rid of the skin response that is on that edge right there. So then we would want to likely remove that right there. So that is a little bit easier as we look for sort of windows. If we don't, then we just see a lot of respiration. We have to go into the editor, move things around so we can actually see it a little bit clearer. But if we were looking to report an SCR or something, that's a little bit better of a method here because you're going to keep consistently missing out on SCRs as part of the data set. So this is pretty much it. Here's another example. That one also would go in. There's that range that we would like to remove it just because the timing of it all. And there's some that are right on the edge of it, which makes it difficult. But in most cases, it's pretty clear. This one's right there, and I could probably move it a little bit to the left to get that actual lowest point. As far as these points are concerned with, they're not millisecond accurate. Like it's like the actual change in moving the sweat out of the pores is very slow. It's not always this perfect transition, and the sort of difference between this point and that point that could just be due to motion impact, honestly. So using that with a little bit of grain of salt, but we're right on that edge. I would remove this corresponding, I think it is, skin temperature response. I have removed 2 of those down there, so I probably should zoom in and get the correct one and delete that corresponding cutoff there. Oh, that's it. That's a little bit easier than all the other stuff with skin conductance, of course. But I will show then the same approach, not using that edit file of expanding the window up to something like 300 seconds or 300 seconds in this case. And so this is what I'm talking about before. It's a little bit more difficult to see every individual respiration, but we can still see them as they come out to here. But when we go to the editor, you can't look at it all as a whole. You're going to have to set a smaller window in there. And then in the same case, you're going to have to make it not look as distorted by doing those different changes. So you're having the students, multiple students, do all of those things. They're zooming in, they're setting the window. Let's say it's 10 seconds. They have to then zoom in on the other axes to make sure it looks like this. Like it just adds another sort of layer of complexity there. But I think the trade-off, if we could find a consistency, is still worth it if we're looking at SCRs.
Would it make sense? I haven't fully thought out my question, so it might not make sense. Could you just add respiration rate as a covariate and then not deal or, get into this world of, is it an SCR in response to respiration? Is it SCR in response to mounting a sympathetic response? If you control respiration rate, does that maybe cut out some of the human error of the editing while acknowledging that respiration can impact?
Like different pace breathing.
I wasn't thinking about a pace breathing. I was thinking about just taking the respiration
Oh, it's covariate.
as a covariate when you do analysis.
I would say the biggest problem I would have with that is just the magnitude of the respiration and that of the corresponding SCR, which would not be encapsulated, right?
That's okay. But I guess if you're just doing numbers,
Exactly.
I'm not trying to look for cheat codes. I'm just trying to look for ways to get consistency in editing.
But I've been looking for a lot of years. I mean,
It's been really hard. So I'm like, if you could control for respiration, if you were just looking at number of SCRs, does that account for that?
yeah, it's tricky.
I don't know.
General rule overall is do as little as possible. That is the best thing I can tell people with skin conductance.
Yeah.
And then that's kind of the best thing to aim for.
There is a lot of nature in here. We should.
Yeah, I see people poking around. They're like, oh, they're still there. Okay, all right, we'll go ahead and end here. As far as the other electrode configuration arrays, is this something